OMDP, Ocean Model Development Panel, and said, oh, we have COMMODORE happening. It was first time it's happening in the United States. And should we team up? And yes, let's team up. So that's how the whole thing happened. It was the united effort of these two entities. And the goal, the motivation is to improve dynamical cores and parameterizations in numerical ocean models used for a wide range of scales from coastal applications to millennial global climate change. So very broad within the ocean modeling realm. The aim and objective is to bring together all of you, so scientists from ocean modeling, ocean processes, machine learning, to review the advances in dynamical core numerical methods and parameterizations, including, which is new now, this machine learned data-driven models. The outcome is we will put together a report from the workshop where we'll summarize the state and perspective for developments in ocean modeling and machine learning. And to achieve that, we have the volunteers, so big thanks to the volunteers that will help us during the discussions to take notes. So Spencer, Dhruv, Teresa, Manita, Dan, Anna, Luke, and Kate. Thank you so much for helping with that in advance. I'm not gonna go, we have 8 sessions. I'm not gonna go through all of them. You all have the agenda. If not, there's copies outside. You can also scan the back of your badge and get the agenda right away. So these are the 8 sessions.
But if you can leave a few minutes, if you want to have questions asked to you, that'll be much appreciated. If not, we can actually delay the questions to the discussion section. So on purpose, we have longer discussion sections because this is a workshop. This is not a conference. And that's why we want to have as much discussion as possible. And at the end of the workshop, we'll end up writing sort of a report about the outcomes and future directions, whatever comes out of from these discussions and from your contributions. So those discussion items and any ideas or other topics that come up will go into that report at the end of the workshop. So I don't want to take too much time. So our first speaker is Peter Korn, and he's from Max Planck Institute for Meteorology. This is an invited presentation, and he'll be talking about from virtual Navier-Stokes flows to numerical ocean models.
Can you hear me? Okay, very good. So first, thanks to the organizers for the invitation. Very happy to be here. I think I'm one of the COMMODORE seniors, so I recall the first meeting in Paris, the lovely meeting. Second one in Hamburg, and now we are here. I think this is a very important platform to exchange ideas between Europe and the US, even if it's coming at the price of having one half of the audience perfectly awake and the other perfectly jet-lagged, but we have to do that. I want to share with you some ideas, some recent work that I did when I started to think about to move from hydrostatic to non-hydrostatic. This is a purely theoretical talk, so no fancy pictures or animations, just equations and a couple of lousy illustrations that I made. You recall Richard Feynman in his lectures on physics, and he speaks about hydrodynamics. He distinguishes 2 categories of scientists. One for which water is dry, and the other ones for which water is wet. For Feynman, the wet was, of course, the people who think about let's say, the physical properties of hydrodynamics, and the dry ones were those guys who see hydrodynamics as a playground for nonlinear PDEs. Here's a point, but I would disagree with that. I think you can't understand the physics of water or of ocean dynamics without looking at PDEs. But I hope the talk makes clear that what I present on equations is for the purpose of understanding our models and those understanding the dynamics of the hydrodynamics. So let's get started. I will discuss incompressible dynamics for the ocean. It's more ocean related than compressible dynamics, and also the relation between these 2. And I will conclude with some lessons learned. So what I do is always finite dimensional. So also I said PDEs, strictly speaking, I'm talking about ODEs or or fully discrete systems. And let me situate you and start with the primitive equations. This is what we know. This is what we all use. This is the background of our models. Hydrostatic, Boussinesque. So we have the velocity field. This is a horizontal velocity, hydrostatic balance, free surface, and the traces. The question is, if we now go from hydrostatic to non-hydrostatic, let's save some space and skip the buoyancy dynamics for a moment. This is gone. We don't need the free surface. What we retain is the incompressibility. And in the end, you start with, you end up with this equation here. This is the horizontal velocity equation. And most models start from, they do a triple step. So shallow water, hydrostatic, and then potentially non-hydrostatic. And they retain, if you have shallow water, you have this part here. That's the vertical component of vorticity. And here the pressure gradient. If you then go hydrostatic, three-dimensional, you add the vertical advection of horizontal momentum. And then the question is how to proceed, how to go to non-hydrostatic. And many codes I see, they add just the vertical velocity equation in that way. So they operate with a three-dimensional velocity vector and with the vertical component of vorticity. And I think this is not the right way to do, or I think that this is suboptimal because it breaks some symmetries in the equation. So I call it route A. The route B would be to use a fully three-dimensional vorticity vector together with a velocity vector and to discretize this exterior product here. And this is what I want to explain. Route A is easy to implement, but it breaks the beauty of the system. I don't know how to do really consistent vorticity equation in that setup. And in the following, I will focus on the inviscid case and look at conservation properties we get. So first, we have this equation here to discretize. And if you spell out the vorticity, the cross product, you see this here. And from what we know from the hydrostatic dynamics are the blue parts, and what we have to implement are the red parts. And the first step is getting a three-dimensional vorticity vector. The second step is discretizing the cross product. And for the vorticity, this is pretty simple. We do that by Stokes' theorem. So this is just the continuous form of the vorticity, and then we recall, we have prismatic grids. So we have some rectangular, triangular, whatever horizontal cell, and we have in the vertical we extended by some vertical coordinate direction. And if we work with a primal and dual grid, we have a dual prism associated with the primal one, and there's in the horizontal plane there's a shift by 1/2. So you shift it in the rectangular grid, you shift it by a half of the distance, and you also shift it in the vertical. That means the three-dimensional dual prism is shifted, has its bottom where the primal prism has its center. That means the vertical component of vorticity is sitting at the bottom of the dual cell, and then the half level of the primal cell. And the trivial observation is important. The vertical faces of these things. This is here a triangular thing, but regardless which geometry you have, the vertical is always a rectangular face. So that means when we calculate the horizontal component of the vorticity, this will be associated with this vertical face here. And if we discretize that, then it's pretty simple. We do it by Stokes. That means we have a loop at that face here. And here it's for a rectangular cell, but it's the same. It would be the same for a triangular or hexagonal cell. So you go up, you go left, you go down, you go right. This is your loop. And you can write that in that case, that's just identical to the classical finite difference discretization of the vorticity. So once we have that, there's nothing fancy, nothing new in that. Once we have that, we have a full vorticity vector. Now we have to combine that with the velocity vector for the cross product. Here you see the continuous expression in Cartesian coordinates, but for the grid we are using, I want to have the general. I don't assume Cartesian coordinates. So what we do here is we operate with some reconstructions, and this is the stuff that we implement in icon O. The blue thing is the following. You take the horizontal velocity, you apply this p hat here. This is a reconstruction that gives you a vector at the dual grid, at a node of a triangle, let's say, or a node of a rectangular cell. And that's the place where the vertical vorticity lives. You can multiply that, and the product is then mapped back. And that's this structure we use in all terms. So you reconstruct one component, you multiply it, and the product is then mapped back. You see that also in the other terms here. Here, for example, we map the horizontal vorticity to the place of the vertical velocity, to the product, and map that back. And here's also this P subscript set. Here's a vertical averaging. And in the same manner, we discretize the second line here. So these operations. So we have a P here, we have a P hat, and you have a P tilde. This is what I call Hilbert space compatible reconstructions. This is what you have on a rectangular grid. It's your classical averages that you do. What we can show now is with this three-dimensional vorticity, which means with the three-dimensional curl, it has some decent properties. For example, the curl is zero if and only if it comes from a gradient field. This is what we all know from vector calculus. We retain that. So you have also a Biot-Savart law. That means if I have the vorticity vector and I want to recover the velocity vector, I have to invert. So I've given the right-hand side, and I have to invert some elliptic equation. And I'm coming to this M operator in a second here and explain what it is. And this is the virtual finite element thing. So let me continue one. So what you do in virtual finite elements is similar to finite elements. You expand something in a basis, but you never compute that basis. This is the virtual thing. In classical Galerkin, you expand something in a basis function, and these basis functions are given as solutions of, let's say, eigenfunctions of Laplace operator, of some equations. Then you get your basis, this determines your basis functions. In this virtual case, what you do is you say, my basis functions are coming from an equation, and this is a local equation on a grid cell. So let's say you have a grid staggering, a seek staggering, you have your vertical components on the boundary of your cell. Then you reconstruct a continuous field by solving a diff curl problem. So you want to solve an equation, the divergence of the continuous field equals the discrete divergence, and the curl is zero. You can vary that. The curl of zero is you can discuss that. But this gives you a unique solution on an individual cell. And if you then impose some additional technical conditions like small stencil and so on, then you can write down these continuous reconstructions in an explicit way. You don't need to solve a PDE per grid cell. You have an explicit expression of that. And luckily, these are the P tildes, P hats that I mentioned before. So behind that is a certain machinery that is coming from virtual finite elements. This is something that Franco Brezzi invented in 2014, 15. And it's a kind of evolution of the mimetic discretization idea with the goal of going for very, very general geometries. And I think that all secret models can be cast as a kind of virtual finite element. So this is a very generic thing. It really does not depend on the cell geometry. It depends on the staggering. This is this example that I gave here. So if you have, you say I've given a discrete velocity field on the boundary of a cell. I say I want to have a V tilde, a continuous field that has the same divergence. This is the discrete. This is the continuous divergence. Curl should be zero. These are the boundary conditions, and then you can solve that. And with that, with these reconstructions, you can then you can then, this P is the solution of this guy here, you can then define a certain scalar product, which is very similar to the scalar product that we actually use. So this is a abstract thing that is going in the background. If you look at what you actually compute, this is pretty similar to what we are doing. I think I don't need that, so I've said that. Okay, so what you need to have in mind is we have three reconstruction. One is the P. This takes, let's say, a velocity field and reconstruct something in the interior of a prism. We have a P hat that reconstructs something in the interior of a dual prism. And we have some P tilde. This is reconstructing some tangential information. And this M that I mentioned before, this is the product of the transpose of P with P itself. So it maps the velocity field in itself. And in case of a rectangular grid, this M is the identity. So it's a diagonal matrix. It just contains the volume of your grid cells. Let's continue. With that terminology, I can write down the incompressible Euler equation in that form here. So this is our discrete exterior product. Here you see the M operator, gradient, nothing new. So this is straightforward. What you can show is that if you know the velocity field, you can recover the pressure, as in the continuous case, by solving this Laplacian problem here. You can show that these discrete equations with a continuous time, that they are well posed. So they have a solution for all time, a unique one. So this is an exercise in Picard's theorem for ODEs. And that translates also to the Navier-Stokes case. That means if I add dissipation in that form here, I know again this thing has a unique solution. I can show some other conservation properties. Linear momentum is conserved, so we have constant density. It means the momentum is just the velocity, and here it's this P transpose P mapping of the velocity field that is actually conserved. This is the field to which we impose the continuity. Angular momentum. It's a long time that I have thought about angular momentum, and I was wondering, how can I define angular momentum on a staggered grid? I mean, what does that mean? And the observation is simply, I mean, if I can discretize vorticity cross velocity by this discrete thing, and I can apply that to this cross product here, I just replace the vorticity by the position vector. So I take a position vector that points to the nodes of the cell, so to the place where the vorticity lives. And then I can show that the global integral of the angular momentum is conserved. We can show energy conservation, so kinetic energy is conserved. And if you go to 2D, you can show that energy and entropy is conserved. This is already included in an older paper on shallow-water equation that contained the basic ideas, I think 2018 in JCP. Helicity is a conservation property that for the Euler equation, so that's the inner product of velocity and vorticity. How do you do that on a staggered grid? You do that by these reconstructions. So you see the continuous helicity here, and the discrete one is then just the product of the reconstructed velocity at the place where the vorticity lives, multiplied. And here we reconstruct the horizontal vorticity and multiply it with the vertical velocity. With that definition, you can show that the helicity is conserved in time. So I still have continuous time. And the proof is exactly how you would do it in the continuous case. You deal with the vorticity and velocity equation and plug it into each other, and in the end, it drops out that this thing is conserved. Now I'm going for discrete time, fully discrete time. I do it in implicit time stepping. So the nonlinearity, this is the decisive part here. This is discretized implicitly. So what I have is a staggered discretization in time and space. And for that, you can show that this discrete system has a unique solution. It's called this UN, superscript N and Pn here. It has all the conservation properties that I mentioned in the discrete setup: kinetic, momentum, vorticity, helicity. And finally, it's reversible in time. The Euler equation you can run backward in time. You can run that with that algorithm also. And again, you can add dissipation and you get, let's say, analogous properties for the Navier-Stokes case. This was incompressible Euler, so constant density. Now let the density vary, but be still incompressible. These are the Euler-Boussinesq equation. So we have the usual components. You have a right-hand side here, and we have a transport equation for the density. And this is the discrete version. What we have here is the new part. This is what we already implemented in the Icon-Ocean model. This is the transport operator that again uses this construction of reconstructing a velocity field to a tracer point, doing the product and then map it back and then apply the divergence operator. And for that, I can also show continuous time. It has a solution, a unique solution. It conserves energy, which in that case is the sum of kinetic and potential energy. It conserves helicity. So there's a right-hand side here in the helicity equation that depends on the potential. And there's a new thing that is interesting. This is PV. So we have density. We can create a PV, and in that case, it's the mass-weighted PV or density-weighted PV. I found that in some papers of Peter Haynes, who was working with that concept. And it is the product of vorticity with the density gradient, and we can rebuild that. And again, we split that in a vertical component and in a horizontal one. That's the product of vertical vorticity times the density gradient reconstructed to the position of WZ. And this is the horizontal vorticity times the vertical gradient of density. And can show we conserve that quantity in time. And again, it drops out by combining the discrete equations in the similar manner as you would do it for the continuous ones. I'm working on getting rid of this density weighted thing here and include like the division by rho, but currently I cannot show that. This is, you have then to manage 3 quantities, and that's challenging. Again here, with this implicit time stepping, we can show that the fully discrete setup retains all these discrete things. Now I have a solution for the non-hydrostatic one. How is that related to the hydrostatic one? And there's a limit connecting these two. So in the limit of a small aspect ratio, these two things should converge to each other. So what we can do, you have a thin domain. So here, I take it for simplicity -1 to 1, and in the vertical you have this -epsilon to epsilon. And you transform that by this transformation here, and what you get is this is a continuous setup. These are the scaled Euler equations. You get this epsilon squared that is applied to this part of the vertical velocity equation. The question is now, if the epsilon goes to 0, so if the small aspect ratio is going to 0, what happens to the solution? Do the solutions of the non-hydrostatic converge to hydrostatic or not? And in fact, they do. Right? So I repeat here, this is the scaled Euler in continuous coordinates here. This is, and this is the hydrostatic Euler. So we expect that this converges to that here. So from the only survivor from the vertical velocity component is this guy here, and there's no density on the right-hand side in that configuration. So this focuses just on the behavior of the velocity equation, and I can remap that to the discrete setup. Then I get a discrete scaled Euler and a discrete hydrostatic Euler. The difference between these two are the red terms. So this is the nonlinearity. And again, what happens is epsilon goes to 0, and you can show that this for epsilon 0, the non-hydrostatic solution converges to the hydrostatic one. And the point I want to make here, it's not just that some operators or some terms in the equation get small. I'm talking about the solution to this equation. This is what is approaching each other. And I want to skip the ideas of the proof here. This is but this theorem here is a discrete version of a result that was derived 2019 by Jinkai Li and Idris Titi. They did that for the continuous case, and this is a much more involved thing because in infinite dimension, different concepts of convergence. But I found this is interesting, or interesting statement about the computational part. If we go back, these are the icon O equations. So this is now the full primitive equations in a semi-discrete setup with continuous time. And what I said before is if I say I add a vertical mixing scheme of PP type, so a very simple one, and the discrete icon O equations with a free surface and all that have a unique solution, and that applies also if I include the GM Reddy discretization. So, and finally, sorry, and go back. And what I can also show is that the hydrostatic version of the Icon-O algorithm converges to the non-hydrostatic converges to the hydrostatic one if the aspect ratio goes to 0. So this is translated. And then I went into the compressible case. So now the density is not only allowed to vary, it is also allowed to compress. And there you can basically two different forms of the equation. One is the momentum form, and the other one is the velocity form here. I stick with the second one, and I'm still not quite sure this is a good idea. I did that because this was somehow the form that the Weather Service uses for their model for the Icon A version. But it might have some impacts that I don't understand. But I mean, this was just for being compatible what we have in the other model component. And I can write down then the discrete compressible Euler equations. The new term is this guy here. So the gradient divided by the density. And we handle it with a similar discretization philosophy that we applied before. And then we have a density transport equation, and here then the energy equation. And we can again show that this system has a unique solution. There's one thing we need to impose, and this is this guy here. So the advection has to be upwind, or more precise, the advection has to be positive. Otherwise, you run into trouble with this density here. So if you say the density is initially in a certain range, then it has to be in that range for later times. And that is the easiest way to guarantee that for this theoretical analysis that I'm doing is to assume upwind, but you can replace that. It's strictly about, it's really just about being positive. Then these equations, they conserve now the sum of the three energy compartments, kinetic, potential, and internal energy, and they conserve helicity. And finally, if I restrict that a bit and go for the isentropic Euler equations, where the entropy is not changing, and you use these pressure equation here, this is the usual gamma here, the specific volume at constant volume and constant pressure. Then I can discretize that again. So this is the discrete version of this here. And then there is the question, what happens if the Mach number goes to 0? But before I address, this is this here. So if I denote by this U epsilon, P epsilon, the solution of the compressible equations, and by the same notation without the epsilon, the solution of the incompressible equations, and I assume well-prepared initial conditions. That means conditions that are close to the incompressible case. And I can represent the solution of the compressible one as U plus capital U. This is a slow part. So the U is the one from here. And the capital U is the solution of the linearized Euler equation. A U tilde and some remainder. And the same decomposition for the pressure. And this U tilde here, these are acoustic waves. So these are the solution of the acoustic wave equations that you see here. This is the acoustic equation called free. So this is a discrete version of classical stuff from, I mean, singular limits, there's a huge body of literature, but probably the first one did it, and I was following that was Kleinerman-Meider in the mid-80s, crisis done work on Stephen Chouksey and others. So that means if we let the Mach number go to 0, the solution of the compressible converge to the solution of the incompressible case. So much about these results and some lessons learned. How do I do in time? How much time do I have?
Maybe.
Okay, perfect. I mean, the first observation, in all what I said, I mean, you saw some picture about grids, but this is really not, this is applying to triangular, hexagonal, rectangular grids. This is the same results. We can even go for mixed grids where we mix rectangles with triangles. These results will be valid. In the case of a rectangular grid, so the differential operators that we have, diff, grad, curl, they became what your classical finite difference stuff. The reconstructions that I mentioned, they became the classical averages. This is what we is currently doing. So in the non-hydrostatic case, we get the MAC method that was done by Harlow and Welch in '65 for the Navier-Stokes equation. If you go for hydrostatic Boussinesq, then our velocity equation looks like the velocity equation in NEMO. With the discretization of the nonlinear term that conserves in 3D energy and in 2D restrictions conserves energy in entropy. And again, this is grid independent. Remark for the 2D case, rectangular. So this is a 2D incompressible Euler in stream function formulation, and assuming as a rectangular grid. So we know Arakawa's work. He discretizes this guy with the famous Arakawa Jacobian. These three terms here. And here you see how they are defined. And Arakawa's Jacobian is related to this operator that I mentioned before. So this p hat times vorticity times the p hat dagger. And one can show that the Arakawa Jacobian is equal to the curl of this operator here, applied to the stream function and the Laplacian. So if you spell that out, and if you do, it's a matter of arithmetic. It is this guy is of the same type, and this is the explanation why we get in 2D energy and entropy conservation. The difference is that Arakawa is valid for rectangles, and we can do it with that operator k here. We can do it for more general geometries. The second lesson that I learned, so for the C-staggered models, there's a preference of using this vector invariant form in that way. And if you ask yourself, how can I destabilize my model? And there are two ways. So one has to do with the kinetic energy, and I see that some secret models struggle with this formulation of kinetic energy. And there's, when we discuss grids, we talk about structures versus unstructures. I think the appropriate distinction is orthogonal versus non-orthogonal grids. So if you're on an orthogonal grid, which is a rectangular grid, so your boundaries align with the coordinate lines, what you then have is there's a result from harmonic analysis. It's called Plancherel's theorem. So if I define the kinetic energy by squaring the components of the velocity vector and adding that, then this will give me a decent, or this is equal to the length of the vector. And this Plancherel theorem is an if and only if. So this is valid for orthogonal grid and only for them. If you're on what we call an unstructured grid, so triangular, hexagonal, you don't have that. There is no orthogonal basis in the background from which these components arise. So if you then square your components, your velocity, normal velocity, this has nothing to do with the length of the vector because Plancherel is valid. So then you're on your own. The solution I would recommend is work with a reconstruction. Could be the one that we make. Reconstruct first, compute the length of the vector, and then you are fine. There is a price to be paid, and this is you get a mass matrix. So if you want an energy conserving system, you have to have this P in the time derivative, and that gives you the P transpose P, this M here. But using the sum of squares on non-orthogonal grid that creates a source of energy. And this is what I mean, this is our experience. We see that in the icon atmosphere component. They have not done it. They have done, they thought they found some workarounds, but it's really destabilizing. The second way to destabilize your model is, I think it has to do with these vector invariant form here. So as I said at the beginning, there's some mixtures of forms, advective versus vector invariant, and to close budget in that setup is really difficult. I couldn't manage it. I don't say it's impossible, maybe it is, but I think it's much more natural to work with this, to discretize this cross product. And then you get a decent vorticity equation, and that's the route to the conservation properties that I showed you. And when it comes to that algorithm that I described, it's not really a model, it's more a class of models. It has some, what I call a template character. So there are some ingredients that are not negotiable. And this is the definition of the kinetic energy and this cross product. This is important, but apart from that, you can play with a lot of things. So vertical coordinate, different reconstruction, lumping the maze matrix or not, flux limiters, high order, that's all possible in that framework. I'm not saying this is, I'm not singling out a single model and say this has to be done like that. I'm just singling out some ingredients that I would say this is recommendable to have them. And apart from that, the world is open. So, and if I summarize that, and that explains my subtitle. So we can show we have the compressible Navier-Stokes in 3D. We can do some vertical averaging. We get the 2D equations, and they have some nice properties. We can have the small aspect ratio limit, and we end with the hydrostatic compressible equations. And on the other side, starting from the compressible ones, we can do the Mach number limit. We end up with the incompressible ones. We can then do the small aspect ratio limit, and we have the hydrostatic Boussinesque, so the primitive equations. What I do not know, and maybe somebody in that room has an idea, is there a relation between hydrostatic Boussinesque and some equation set that includes Chen McWilliams? I guess there is something, but I don't know it. Then it would be interesting to have that limit also. And that's the end. Thanks.
Any questions, Steve? I need apparently we opted not to use the ceiling phone microphones, so I'm going to pass the.
Yeah, great talk. Thank you. A lot of beautiful equations, which I love to see. More equations that I wonder if you could comment on. Do your methods for discretization have a variational connection or variational analog perspective, a la Hamilton's principle?
I guess, and I hope so. But I'm not quite sure. But I think that this form of the kinetic energy, I mean, one should be able to formulate that part of that. I would guess so. I'm very interested in showing some discrete equivalent of a beautiful theorem of Arnold that you might know. So Arnold showed that Vladimir Arnold, he has a famous book on classical methods and methods of classical mechanics, I guess. They showed that if you look at the solution of the Euler equations and you look at all functions functions that are incompressible and have size 1, so they build a sphere in an abstract space. And if you look at the geodesic curves of that sphere, then these are exactly the solution of the Euler equations. And he used that geometric picture to make a statement about predictability, because he could show that these curves has a certain curvature and that limits the predictability. So it's a beautiful work. And I think with that, if I use that kinetic energy, I can define a sphere in a discrete space. And the question is, does these geodesic curves have the same properties? I guess so, but I'm not quite there. and developing the more geometric picture or the variational picture. I think that connection is somewhere in the background, and that might be the deeper reason why this stuff works. And it all has to do with this consistent energy, kinetic energy definition. If you have that, you have good chances to get there. But I can't make a definite statement about that and roll the picture out. Maybe next COMMODORE meeting.
So we could take one more quick question. Are there any early career scientist questions? Andrew. Sorry, Alistair.
Thanks for the talk. This is more of a clarifying question. So I think a lot of the diagrams that you showed were based off of C-grid staggering, and you made the comment originally that you think that you can form the transformation, the reconstructions for any C-grid. What about for a B-grid? Like, because like, does that just collapse the projection down into two because the U and V are the form, or do you have a different form of how you need to construct the underlying element?
I haven't thought about the B grid. I don't know. I could imagine some connection to the A grid, because you see this P transpose P. If you then shift the transpose to the second component, you get a reconstruction time, a reconstruction, and these are living both in cell and in prism centers. There might be a link. For B, I don't know.
Okay, thank you. So in the interest of time, let's move on. And then Alistair, and if anybody else has any questions, we'll have them during the discussion session. So we'll switch over. Our next speaker is Manita Chouksey from Leibniz Institute for, well, that's an ocean, right? For Baltic Sea Research, sorry. That tells you how much German I know. So, okay, go ahead, Manita.
Thank you, Gökhan. I hope I'm audible. Am I audible? Yeah, I didn't realize I put the German title, and it's a very long one. It also doesn't fit on my badge. Right. So how can I change? Can I actually see it here somehow? All right. And it's next. All right. Thank you. Right. So my name is Manita, as Gökhan introduced. Thank you. I'm from the Leibniz Institute for Ostseeforschung Warnemünde, in English as the Institute for Baltic Sea Research. I'm also part of this project, the national project TRR, here in Germany, which is also working on energy transfers in atmosphere and ocean from a lot of different perspectives, particularly using modeling from mathematics, meteorology, and oceanography perspectives. Peter is also one of the PIs in that project, and I'm also a member of the OMDP panel. I don't have the logo here. Right, and I'm going to talk about representation of balanced state in the models of geophysical flows, and with the work has been done with my collaborators, Carsten Eden, Dirk Olber, Silvano, Rosenau, and Marcel Oliver. So when I say balance, here I refer to motions that result from some combination of balance of forces, for example, geostrophic balance, and that would be the large-scale, slowly evolving motions. And when I speak of the balance, I also have to talk about the unbalanced motions. And in this case, I would refer to internal gravity waves, which evolve at much faster scales. So these are the balanced and the unbalanced scales. And to understand them, I like to refer to these motions as what I call as game of notes. So there is a letter that Jules Charney wrote in 1947 to Philip Thompson saying that we might say that the atmosphere is a musical instrument on which one can play many tunes, and nature is a musician of more of Beethoven and Chopin type. I don't quite understand that analogy, but what it means is that the low notes tend to refer to slow rotational motions, meaning the balanced motions. And on the other hand, you have the high note or high frequency motions, which are equivalent to, for instance, internal gravity waves. So the reason I'm showing this is because I want to refer to from your flow field to the slow part and the fast part. I'm going to use this later to be able to separate these motions. What's also important to know here is the bulk of the energy is actually contained in these slow rotational motions, and the high frequency motions that we're talking about, they tend to be on the other side of the energy spectrum. So speaking of energy, I want to just show this a rather simplified schematic of major energy regimes in the ocean. So you have on the x-axis increasing spatial scales, and on the y-axis you have increasing time scales downwards. So you have at the larger scales the mean circulation over here, where the energy enters from winds and tides. This energy is then lost to mesoscale eddies, primarily by baroclinic instability, and that's this part of the energy regime diagram also is known to transfer energy to larger scales. So that's the typical upscale energy transfer, inverse energy cascade, as we call it. However, if you move to the other side of this diagram, you have a smaller scale motions. You have internal waves. There's a spectrum of motions which transfer energy within the wave spectrum by wave interactions, for instance, but then also by wave breaking to small scale turbulence, where energy finally dissipates. And this is the downscale energy pathway. And the question is, how does the energy from this large reservoir end up at these smaller scales? And of course, there are other processes that have been proposed. But what I want to refer to here is this route between the eddies and internal gravity waves. And of course, there are other processes that have been explored previously, theoretical studies or idealized studies, for example, light yield radiation, ageostrophic instabilities, and so on. I'm going to focus on the process of spontaneous loss of balance, or the nonlinear generation of waves from eddies. But I'm also going to compare to or show how it compares to symmetric instabilities, because this is something which was not explored before. This also relates to the concept of, I already mentioned, spontaneous loss of balance, which results from the nonlinear interactions between eddies and waves, but also the mathematical concept of the slow manifold. I'll talk about it a little bit. And the other thing is the scale separation, and in particular time scale separation, which, so I mentioned the fast and the slow motions. The fast would be the wave part, and the slow motions would be the eddy part. And this time scale separation is dependent on the Rossby number, which also determines the nonlinearity of the system. So I just want to give you an impression of how complicated and confusing this topic has been in the past. So if you were the slow manifold, I think you would be thinking, to be or not to be, that is the question. So from the series of papers I just want to show you from the 1980s, the first paper by Lawrence on the existence of a slow manifold, and then on the non-existence of a slow manifold, and then again on the existence of a slow manifold, and then the slow manifold, what is it? And a couple of years later, there's still some more stuff going on with the slow manifold. However, this problem is actually not solved yet. So even today, we don't have a mathematical proof of whether a slow manifold exists or not, particularly for complex dynamical systems like the ocean. The problem continues to persist, but I think we agree generally that there is no strict slow manifold, it would mean that if you're on a slow manifold, if a particle is in a slow manifold, it will always be there. And with slow manifold, it means on a balanced state. However, because we see the generation of waves in atmosphere and ocean, we can agree that there is no strict slow manifold. So I just want to show you what it looks like in a model simulation. So we have a balanced jet in the beginning. So this is balanced. There is no wave to begin with. And when you let it evolve, you have this jet which meanders, which then generates these eddies to the pinch off from the meander. And eventually these eddies evolve with these large coherent structures. But at the edges, you can see here small scale features which are related to waves, but are they waves or not? This is also what we're going to address next. So that's exactly what the slide is about. For example, here I'm showing model simulation results that are from, for example, this classical paper by Sullivan and Dunkerton from the atmosphere. So on the top, you see the horizontal velocity divergence. And on the bottom, you actually see the geopotential in the upper troposphere. So these velocity divergence here is supposed to indicate the generation of waves coinciding with the troughs in the pressure in the geopotential here. And then you have here in the middle idealized simulations of baroclinic instability, again showing vertical velocity, and you can see these well-manifested wave trains. On the right, you have from an ocean model, a realistic ocean model, the picture of the Gulf Stream. So what you have is the pressure, contours, and high-pass filtered vertical velocity. And you see these waves, which are diagnosed or interpreted as waves, but the question is, are they really waves or apparent wave signals, which are referred to as slave modes. So to understand a little bit more about slave modes, they are the motions which show up as the waves, but they're actually tied to the balanced motion. So what it does to our understanding of the slow manifold is the following. So yeah, so if you were to imagine your subspace or your flow space in orthogonal terms, so you have on the x-axis the slow part, on the y-axis the wave part. The fact that you have slave modes would mean that your slow manifold is not on the balance axis and freer waves, but it's somewhere here where you have some contribution from this part, but it's not wave, but it's a combination of wave and the slave mode. So this is a slow manifold, and ideally, if you're here, you would be there forever. But because we see the wave generation, there's divergence from the state, and that's what we called the fuzzy manifold. So what you see here is actually, if you have a particle here, it will oscillate fast around this trajectory of slow manifold, and at the end you don't have a strict slow manifold, but a state which is oscillating around it. So to deal with this complicated concepts in complicated systems like the ocean, we go to what's called the nonlinear flow decomposition to actually dynamically decompose and separate the slow and the fast part. So essentially, you can write your equations in this way. So the Z here indicates the state vector. You can write it for shallow water equations, primitive equations, hydrostatic, non-hydrostatic configuration. So as Z is the state variable, then A is a linear matrix, consists of all the linear terms, and N vector is the nonlinear vector, which consists of the nonlinear terms, and R is the Rossby number, which determines the nonlinearity of the system and also the scale separation. So what we've been working on in the past is on the higher order balance, which is based on Rossby number asymptotic. So you expand in Rossby number, and you can go up to any order, but up to fourth order, you see good results in convergence of the balance state. And the other method is optimal balance, which is based on different concept, based on iterative forward-backward integration. And the aim is to get an optimal solution to balance state. So I'm going to compare these two methods later and show you the results. And as I mentioned, they have been implemented in different models, codes, configurations, different discretizations, methods, and also for a range of Rossby number regimes. So this is just an indication of what you get on the top. You have a full state, which you see is rather messy. You have slow part and a fast part. And then when you separate using this decomposition, you get these slowly evolving eddies, and then the fast parts here. And of course, these methods are precise, but they are also based on Fourier transformation, which restricts the application to situations where you have boundaries, for instance, or beta effect, and so on. And for that, we have a new method, which is called optimal balance with time averaging. It's actually a modification of the optimal balance here. And it has similar accuracy, but no Fourier transform, so it expands its application. I'm going to show some results from it later. And I think I won't go much in detail, but I just want to go very briefly how nonlinear decomposition works. I'm only going to talk about the higher order balance here. So this actually began the concepts from in the past from the numerical weather prediction methods. So what's called a nonlinear normal mode initialization. So I'm going to show here example of the single layer model only. So you have here the equation for the velocity and the height field. In the Fourier space, it takes the following form. So the Z vector is consisting of U, V, and H, and the matrix A looks like this. It's just the linear terms. So you can actually now use this matrix to write the eigenvalues and eigenvectors, and you get 3 eigenvalues. One which is related to 0, which is related to the balance part, and then you have 2, which is related to the gravity wave part. It also resembles the dispersion relation of the gravity waves. Right, and then you can get the eigenvectors, and then you can project these eigenvectors back to the state vector and get the projection matrices, and then you can have your parts. But now we will go on to expand it in Rossby number. I just wanted to mention here that this is based on the secret discrete operators, and it's important that it's consistent when you discretize it based on the grid you're using, otherwise you won't get efficient results. So just very briefly how the higher order expansion works. So I mentioned the fast and the slow parts. This is what you actually do here. You introduce a fast and slow time scale. So you have 2 time scales in the equation then. Then the slow part, which is your slow mode or the balanced mode, evolves only on the slow time scale, whereas your fast mode evolves to the fast and a slow time scale. So the slave mode evolves to the slow time scale, and the wave part evolves to the fast time scale. And this is based on this assumption of a weak interaction assumption, which was also in the pioneering work of Hasselmann, for example, assumed, and you expand, for example, the work of Warren. So now when you write your equations like that, you have this Rossby number showing up here again. IS is just interaction term, which is interaction terms between the fast and the slow mode. But for increasing order in Rossby number, you can then write your equations like that. So for the slow mode, you would just go on to substitute them for subsequent orders. And for the fast modes, you can also do that. And what I want to point out is this F mode, which is actually the slave mode that I spoke about earlier. So what you're doing actually with every order, you're actually suppressing this slave mode, and you're going to a more precise balance state and at the same time more precise wave signal. What I also want to mention is that this first order slave mode that you see here is actually equivalent to quasi-geostrophic balance state. This was shown by Leith in 1980, so it's equivalent there. So what do you get from by doing this decomposition? So what we do is you use that to initialize a model with a balance state and then rebalance it with this higher order balance, so to maybe second order balance state. And then I use two different unstable modes. So on the left is actually a superimposition of a geostrophic unstable mode, and on the right is the ageostrophic unstable mode. I just wanted to show you what it results in. So the left one is a situation which is the classic spontaneous loss of balance, and the right is a case where you actually see the occurrence of symmetric instability. So there's a change in sign of potential vorticity. I'm not showing it here, but it does occur for a high Rossby number, particularly 0.3, and that's where it occurs here. So right, what we can see here on the top is the vertical velocity here, which is just an indication of the wave signal, or traditionally it is. And on the bottom is the balance signal that you get. So it's the first order balance state. And what you see for these even larger Rossby numbers, there is actually no difference between the balance state and the vertical velocity, indicating that this velocity signal here, which is equivalent to wave signal here, is actually consisting of slave modes rather than waves. And you can see waves only at higher orders, although in this case, it's still very weak. But if you go to the situation where symmetric instabilities occur because you have superimposed the ageostrophic unstable mode, you can see that already at the lowest order, you can see here, particularly for Rossby 0.3, these wave signals appearing, which is not so clear for 0.2, but at least already at lower orders, you can have waves appearing more prominently than it is for spontaneous loss of balance. So what happens when you go to higher orders? So this is a figure showing that. So what is shown here is the diagnosed imbalance. So you take the difference of the evolved state, which is starting from an already balanced state, and then you take the norm of it, and this is what's plotted here. So that's the diagnosed imbalance on the x-axis, on the y-axis, and the x-axis is the Rossby number. So you can see that the colors indicate increasing orders, and you can see here then on the top is the lowest order, which shows a lot of wave energy. But if you go to higher orders, you get this exponential scaling, which is consistent with theoretical results. But you also see that this energy has gone substantially down because we have removed the slave modes at higher orders. And I talked about discretizations earlier. So we also tested these, the methods that I mentioned before. So the optimal balance and higher order balance in finite difference schemes and spectral scheme. And this is what is shown here in the blue and the red. And you can see that they're, of course, not exactly the same, but they have similar scaling, and qualitatively, they're quite similar. And this brings me to this preservation of balance, because there has been a question in the literature if whether the quality of preservation of balance depends on the numerical scheme that you use in the model. So here, actually, if you do change the schemes, there is a good preservation of balance, but if you mix the notions of balance across schemes, for example, if you use one of them to initialize the other model, then you actually won't get good results. Right. Yeah, so I will skip that because I basically wanted to show that if you use cross-balancing with one method and the other, you still get the same results, which is a good news, because then again, the balance is kind of preserved. And here I wanted to show in two different cases from Chet-like and random cases, when you rebalance the code and let it evolve, you actually get very, very small diagnosed imbalance, which is good news. And it brings me back to the concept of slow manifold, that you cannot have a strict slow manifold, but you can have a nearly invariant slow manifold, which means that these methods are quite precise in achieving a balanced state. Now, I want to very quickly mention new stuff, which is about wave generation at boundaries, because until now I've been showing the idealized cases without boundaries. But because you have boundaries here, you can see a meandering jet. So you have north-south walls here, and you have this meandering jet hitting the walls. And on the bottom, you have vertical velocity, and this is indicative of Kelvin waves generated. This is just a wall, and you see these waves propagating downwards, high mode numbers. But the question is how to diagnose it, because they have boundaries, and the methods I showed before use Fourier transform. And for that, we have this new method, which is optimal balance with time averaging. So you can see here that with the new time averaging, it converges to the exact solution with sufficiently long averaging period. And it gives same results as the other ones, but then you can apply it to the situation with boundaries. So the black lines here are boundaries. This is the full state with the wave and the balance bar, but then you have a separation between the balance eddies and here the Kelvin waves. This was implemented in a new model, which is called Freedom, or Framework for Idealized Ocean Models. So this is also a kind of work in progress, but it's based in Python and JAX. It's very fast. It runs on GPUs, but it can also run on your computer if you use Jupyter Notebook, for example. The key thing about it is that it's modular, so everything is based on modules, and if you want to include a new parameterization or a new model you can just include it without modifying anything. It's also generalized for the same reason, because you can interchange modules from different models. And therefore, it's also user-friendly, it's easy to install and run, and I'm running out of time, but I want to still show just one more thing. This is just a teaser related to machine learning for SWOT. You've probably heard of this SWOT satellite program, which is going to take high-resolution pictures of the surface. This is not a picture from SWOT. This is actually a picture from Icon Ocean that Peter was talking about just a while ago. This is very high resolution, about up to 500 meters, and SWOT is going to be much closer. But what I wanted to point out here is that you see this rich variety of features. You have these eddies, you have filaments, you have wave features, and a bunch of other features which coexist together, and which you will see in the surface snapshot of SWOT. And to address this challenge of a regime where you have no scale separation and only 2D information, we're trying to use machine learning to achieve flow decomposition there. And we have first results from the shallow water model. I won't go into the details, but just to show what it looks like. So here you have a balanced state, you have full state, which is then there's a truth and a prediction. And would anybody like to guess which one is the truth and which one is the prediction? Which one? That one, yeah, exactly that one. So, all right, so they look pretty similar, which is kind of promising, but of course we have a long way to go because you're only the shallow water model. I will actually leave it with the summary by saying that although I talked about the spontaneous loss of balance and that it's weaker than symmetric instability, there's still a long way to go to understand how these processes work, for example, particularly at boundaries and at equator, and they have implications for both eddy and wave parameterizations, and of course, revisiting the representation of balanced state and also eddy dissipation in models. Thank you very much.
So we'll move on to the next speaker. So we'll take questions for Manita during the discussion session. So our next speaker is Hussein. I think he's here, right? Yeah, okay. Hussein Aluie from University of Rochester, and he'll be talking about global scale transfer of the ocean's kinetic energy and the role of the atmosphere.
Perfect, thank you. And I'm probably going to be gasping for air because of the elevation. I used to live in Los Alamos, and I used to think of myself as Superman when I used to travel places. But now I'm having difficulty breathing. Also, I'm a new dad, so I'm out of shape. So the work I will talk about has been going on for years, and recently it's been experiencing fruitful results thanks to a nice collaboration with these good people here that I'm showing. Let's see. Next, perfect. So flow in the ocean is inhomogeneous, anisotropic. It's obvious, but also there's a notion of scales in the ocean. There's different scales. And the question is there a way to have a formal framework to analyze these different scales in the ocean? Usually we work with Fourier, and Fourier implicitly assumes homogeneity. And therefore, it's not clear how applicable it is in the ocean setting. And so this is a backdrop, the broad backdrop that I want to start with. And it's good to be able to have this formal framework to talk about scales and analyze them, understand where the energy resides, how it's being driven, where are the sources and the sinks, how different scales couple to each other. So the wave number spectrum is the first order goal or result that we would like to have for the ocean. Now, of course, there's been a lot of important work analyzing spectra in the ocean, and we've learned a lot from those works. And usually those works use Fourier in small regions. Let me see. In small regions by taking boxes and doing Fourier analysis on these boxes in the ocean. But there's shortcomings or limitations to this approach that we need to keep in mind. Even though we learn a lot from doing this type of approach, there's things that we cannot do with this approach. And one of the main limitations is the box itself. So by picking a box, which doesn't exist in the ocean, we are already restricting ourselves to a certain scale, that of the box. There's nothing bigger that we can look at. We're already limited by the box. And so that introduces an artificial scale. There's some assumption, implicit assumption about flatness of that box. There's no curvature effects. You need to do some massaging of the data. This is typical in signal processing. To do Fourier analysis, you need to do something to be able to do Fourier, such as tapering. And also important for the ocean, and if you want to look at global budgets, you cannot tile the ocean with boxes. So geometrically, it's not possible. And so that's something we're interested in, many people are interested in, and this approach is kind of a hindrance. And so the approach that I've been pushing forward and being excited about is a coarse graining or a filtering approach. It's common in LES, in the analysis of partial differential equations, and it's basically a filtering. So you filter a convolution, let me see, a convolution, and you filter, just like you have a picture of a flower, and you filter it, it becomes blurred. So that's the basic idea of coarse graining. But the reason I like to call it coarse graining as opposed to filtering is because we're not just analyzing pictures or signal processing. We're analyzing the equations. So we want to apply this operation to the equations of motion. And so by applying it, I use the word coarse graining to emphasize the difference from filtering, because coarse graining has a long history in physics. If you think of Boltzmann's derivation of thermodynamics from statistical mechanics using coarse graining and many other examples in physics. So this equation here is a coarse-grained equation for the flow when you have multiple scales. And it looks like the original flow or the original equation with the term that represents the scales that you removed by this filtering operation. And so great. This is a subjective perspective of how I got into this, how I got indoctrinated into coarse graining. Tony Leonard is considered by most people one of the forefathers of large eddy simulation modeling. He put it on a firm footing. At Germano in 1992, he derived a rigorous way to analyze large eddy simulation equations, LES equations, that allowed very important advances later on. And then at the same time, just a couple of years later, independently, Eyink and Meneveau realized how important or how powerful this approach is to analyzing the physics of turbulence. So Meneveau is a world-renowned LES expert, and Eyink is a world-renowned turbulence theory scientist. And so they started using this approach in different ways to analyze the fundamental turbulence, physics of turbulence. And then they worked with Chen and Eki and did very nice work in that time. And then when I did my PhD, I had the fortune or the pleasure to work with these three people who were at Johns Hopkins at the time. So they were my mentors. And then when I went to Los Alamos for my postdoc, Bob Eki was one of my mentors. And actually, one of the earliest talks about applying this approach to ocean was in 2012 at NCAR here for a workshop. But at the time, I did not realize how, I did not appreciate the difficulties that are inherent from using this approach to apply to the ocean. And one of the main difficulties is that the ocean is on a sphere. And so the tools that were developed in LES, the machinery, were in flat space, not on a sphere, not on curved spaces. And the question is, how do we decompose scales on the sphere? the basic definition of convolution is not the same on the sphere. So a convolution based on translating the kernel does not work on the sphere. It's accomplished by rotation. So that's just the starting point is different. There is a rich body of literature in applied math, harmonic analysis on spherical surfaces that I had to learn to make progress on this problem. But even that is not enough because the harmonic analysis on the sphere only allows you to analyze flowers on the sphere, analyze signals. And that's not what we want to do. We want to analyze the equations, the dynamics. And for that, we need to make sure if we apply this operation to the equation of motion, the PDE, that it commutes with spatial derivatives because the PDE has derivatives. And one example is, okay, if the flow is divergence free, is the coarse grain flow divergence free? So basically, do you retain the physics at different scales? That's important to be able to make tractable progress or to have the equations be tractable to make progress. Just to give you an example, what am I doing? 10 minutes. Okay, great. This is turbulence on a sphere on the left. You filter in some lazy way. It's coarse grain, great. Looks blurred. But let's look at the divergence. Before it was 0, after you have huge errors. Yeah. So it matters how you do the filtering on the sphere. And so there's a lot of work to figure out what's the right way to do filtering that allows to commute with the spatial derivatives. And I'm just gonna flash some math on you, but the basic idea is that, okay, there is a solution and that generalized filtering and generalized convolution on the sphere ensures that it commutes with spatial derivatives, such as divergence. So here the divergence with the generalized filtering is 0, practically. And so this is implemented in a public code we call Flowsive that anybody is welcome to use and explore. And what about the ocean? So we started talking about the wave spectra and analyzing spectra in the ocean and dynamics of scales. In 2014 or so, we had the idea, okay, if we coarse grain at different scales and take, in a way, a difference or a derivative, you can get something equivalent to a spectrum. The idea is, okay, you coarse grain at 500 kilometers, at 100 kilometers, and you subtract, you get the energy between these two scales, take them arbitrarily close to each other. That's what the spectrum is supposed to reflect. It's a very simple idea. And does it work? Yes. The black is the Fourier spectrum, and the other two are obtained by filtering using these two kernels. So it seems, oh, that's too good to be true. There's some things, it's not as trivial as it seems. There's some things you need to make sure, because there's energy, positive spectrum, you don't want negative energy. But there's also a caveat about when it works and when it doesn't, and that has to do with the order of the kernel. So these two kernels can detect spectra well if your Fourier spectrum decays not too fast. If it decays too fast, like here, then the filtering spectrum doesn't represent the actual spectrum anymore. And that's important to make sure that they agree. It's important for it to be meaningful, this filtering spectrum. And so anyway, there is some conditions on the kernel that you are using, and you can use more complicated kernels if your spectra decays too fast. So what about the ocean? Here I take a box just to compare with the Fourier, and we analyze the Fourier spectrum. Well, we don't analyze. Chouksey analyze the Fourier spectrum in the green in this box, and using this filtering method or coarse graining method is the orange, and it agrees with the Fourier up until around scale 300 kilometers, but then starts disagreeing with it. That's when you start feeling the box size. And the thing with Fourier is that, with coarse graining is that you're not limited by a box. You're not reliant on having a box. And so we can start thinking out of the box. That's how I like to pitch it. So let's go all the way to larger scales. And then this is the global spectrum of the ocean circulation. So what you immediately stands out to you is that you have this peak at 10,000 kilometers due to the ACC. We know it's from the ACC because we retain spatial resolution. So we know how the flow looks like at different scales. And we also have another peak at around 4,000 kilometers due to the northern hemisphere gyres, specifically the western boundary currents. And at 300 kilometers, you have another peak due to the mesoscales. And you can see them, these are mesoscales. And so for a long time, people were saying, oh, the peak of the spectrum of the ocean is due to the mesoscales. That's because working with boxes, that's what you can see. And even with that, it was not clear because this is the review of Ferrari and Wunsch. They say spectral peak is uncertain. Spectral energy is largest, where at the smallest wave number, and that's affected by the choice of filter, and by that they mean the window or the box that you're choosing. And so the peak is evident only in a small fraction of satellite tracks that they're mentioning. Here I show some examples from different papers. You can see the peak here, but you don't see it in the other two papers. And so to what extent is this peak exists or not affected by the box? That's one of the limitations of working with the box and doing Fourier analysis. And another advantage of doing coarse graining is that you integrate the area under that curve, you get total energy over the entire globe of the mesoscales. Where with boxes, even if I were to tile the ocean with boxes, you still don't conserve energy because you're doing some massaging of the data. With tapering, you're getting rid of some energy, some artificial detrending as well. Okay, and on a log-log scale, this is how the spectrum looks like at scales larger than 1,000 kilometers. You have a power law that wasn't seen before, k to minus 1. What does it mean? What is the dynamical significance? To be determined. So, but one of the things that also stands out from looking at this plot is that you have this gap, this what do you call it, valley between the mesoscale peak and the gyroscales. And this suggests that there's some scale separation between the mesoscales and the gyroscales. And it could be useful, could be interesting. I will use it in a little bit. But we can start talking about energy transfer between these different scales in a consistent way that wasn't possible with Fourier in a box. This is work that was published late in 2023. And this is an analysis of the energy transfer. The cascade here, I use it loosely to mean energy transfer in general. And what we found is that the energy transfer globally integrated in the ocean, 300 gigawatts to larger scales. If we look at things not globally average, so here the x-axis is length scale. This is 1,000 kilometers here, 100 kilometers here. And the y-axis is latitude, so it's only average. What sticks out are these alternating bands of blue, red, blue, red, blue. These are due to the atmospheric circulation cells that induce Ekman flow that result in an energy transfer between the gyroscales and the mesoscales, which hasn't been seen before because you cannot see it when working with a box. And this energy transfer is significant. It's 25% of the upscale cascade due to the interaction of the mesoscales with each other that generate larger scales, which I said gives rise to 300 kilometers, 300 gigawatts. And the way to think about this transfer between the gyroscales and the mesoscales is via a piston effect. I said there is scale separation, which you can think of the mesoscale eddies as being point vortices or point particles, and you're pushing with the Ekman flow, you're pushing them, you're transferring energy, they exert a stress, pressure, effective pressure, and you're pushing them, you're transferring energy to them. In the subtropics, that's when the Ekman converges, Ekman flow. And then in the subpolar regions, it's the opposite. Ekman flow is diverging, gets energy from the mesoscales. And so here, this is a global map because we can look at things globally. You can see these bands of blue and red. Again, blue means upscale and red means downscale. And 2 minutes, okay. So here, if you're thinking about what about spherical harmonics, I'm emphasizing a lot Fourier in a box. Why not spherical harmonics? The thing with spherical harmonics is people haven't really used it in the ocean. It's common in atmosphere. There's no boundaries. But in the ocean, people haven't used it, and for good reason. So here, it is possible to use it in a way that's consistent with the coarse graining that I'm describing. And here it shows a comparison between the two. They agree on a global average. They agree reasonably well. The spherical harmonics is more noisy, which is expected. But more importantly, there is no spatial localization. So you can see here at 1,000-kilometer scale, the spherical harmonics goes over all boundaries, all continents, versus with coarse graining, you only go into the continent 500 kilometers for this case. And people have tried in the early days of altimetry winch to use spherical harmonics, but it wasn't clear how to deal with land. And it seems that people abandoned using spherical harmonics in the ocean since then. Anyway, on wavelets, we would say, what about wavelets? Wavelets rely on convolution. So in a way, this generalized filtering allows for using of wavelets. So replace the G that I was showing you with a wavelet kernel, and you can do wavelet analysis on this sphere. Great, so FlowSafe is a public code to use coarse grain on a sphere. You can measure spectra, you can measure energy transfer, and I'll end with how can you explain mesoscale eddies in the style of Donald Trump? And nobody knows mesoscales better than I do. These are the greatest, most tremendous ocean features you've ever seen. We are talking about swirling ocean masses in the ocean, all right? They're big, they're powerful, and move all around, never seen before. Believe me, some people, so-called experts, they didn't even know they existed until we really started looking into it. But I knew, I always knew. And let me be clear, America has the best mesoscale eddies. The Pacific, the Atlantic, they're full of these things, just doing their job, making the oceans great again. We're going to keep them spinning, folks, because that's what winners do. All right.
Well, on that great note, so again, I think we'll, it's 10 o'clock right now, we'll postpone the questions to the discussion session. So we'll take a break, 30-minute break until 10:30. So please come back and we'll start sharp at 10:30. Thank you. Okay, well, let's get started. So our next speaker is Lizzy Barnes from Australian National University, and he'll be talking about energy pathways of the Tasman Sea internal tide beam at the three different model resolution. Ashley has been also one of our visitors this summer, so he has been at NCAR for 3-4 weeks. Yeah.
Great, thank you. Yeah, can everyone hear me? So this is, sorry, can I? Yeah. This is going to be a fairly interactive talk, is the hope. So we've made a lot of progress. We've got a bunch of results, and we'd really love some feedback as to some next steps. So we're partway through the study, I guess. So this is a 80th degree MOM6 run of the domain of interest between in the Tasman Sea between Australia and New Zealand. The talk is about internal waves, but because this is Andy's favorite GIF, I included it instead, just showing sort of surface features. And so first question is, what are internal tidal beams? So the focus of this study. Returning to Manita's musical theme, if you recall the different modes that make up notes on a musical instrument, you can use that same analogy to imagine internal waves, where we talk about vertical modes. So different internal waves that have 1, 2, 3, etc. Oscillations from surface to the bottom. And then when those different modes combine, you can get these features that look like beams, as you can see when you sum them up. And then in the ocean, so one particular prominent internal wave beam is in the Tasman Sea, which has been studied pretty extensively. It propagates from Macquarie Ridge, just south of New Zealand, across the Tasman Sea, and then sort of crashes into Tasmania. And so this particular beam has been studied with some field campaigns in 2015, the T-tide and T-beam experiments, where there were a bunch of moorings along here. This is the same plot again of the beam from satellite altimetry. And then what we've done is we've set up our domain in MOM6. And you can see just with the isopycnal displacements, the beam sort of pops up, generated from Macquarie Ridge. And this schematic here is just to show you, so another interesting feature of this particular domain is that the East Australian current extends down the coast of Australia and kicks off eddies. And every now and again, one of these eddies goes down the East Australia current extension and can actually cross into the beam. So the motivation for studying this area was there's already field campaigns. It's a place where you can see eddy beam interactions potentially. And it's also just quite a nicely defined beam, sort of starting from the bottom of New Zealand, going straight across, dominated by M2. And yeah, it didn't take much massaging of the model to really see the beam. And yeah, this green box here is helpful to look at because a lot of the results that I'll show through the talk are on a rotated grid between, yeah, just along this green box where all the model outputs have been remapped to. Yeah, so this is when we run the model. On the top, we're showing potential vorticity, or relative vorticity at the surface. And you can see this eddy train that makes its way down Tasmania every now and again. So the dotted line there shows the transects in the bottom panels. The one on the left is one of the perturbation experiments where we've basically removed the kinetic energy and potential energy from the initial condition, flattened the isopycnals, and sort of removed everything else in the model except for tides. So you can actually see that without any filtering or anything fancy, you get the generation straight from Macquarie Ridge, and you can see it propagating through to Tasmania. So yeah, importantly, some properties of the beam is that it's fairly similar to the Rossby radius. So like our eddies are going to be of a similar horizontal scale to the wavelength of the beam. And on the right-hand side, this is the unfiltered full model output compared to the sort of more idealized case where we flattened the isopycnals on the left. And so you can still see the beam making its way across the Tasman Sea, but you can also see all of the other flow features involved. So a challenge with this study is we want to pull the beam apart from all the other flow features. And because it's a fully eddying case with surface forcing, bathymetry, we've sort of tried to make things as realistic as we can. Some of the more idealized flow decomposition methods that have been, I guess, talked about so far, it's challenging to use them in a domain in a model that's so fully featured. So we've been spending a lot of time pulling the wave signal out of the rest of this mean flow. Sorry, not the mean flow, the rest of the flow features that we're not interested in. And yeah, the motivation for this study and the reason we chose the domain is what happens to the energy of this internal wave beam. So we know it's generated at Macquarie Ridge, it propagates across the Tasman Sea, and then it's going to dissipate through topography, mean flow interactions, the continental slope, reflection, all these things can happen to the beam. And we're trying to figure out what happens to the energy, and does the answer to this question depend heavily on the horizontal resolution chosen by the model? So I guess when I started my PhD, I was interested in, I've been learning about how there's been this transition between like eddy resolving and eddy permitting models, and seeing what happens when we really have a lot of the detail of the mesoscale eddies in the models. And then I was interested in figuring out, well, having a look at what happens with internal waves. As we increase the horizontal resolution, you're going to be able to resolve more of the internal wave spectrum. And then would that change the energetics? And yeah, so internal waves cascade into smaller scales before dissipation can occur, which we've, so I guess the higher modes that we talked about before, as you have scattering to higher internal wave modes, you're getting to smaller scales, which are closer to dissipation. And of course, if your model is able to better represent these smaller scale components of the internal wave beam, then potentially you're going to have different energy dissipation outcomes in the domain. And yeah, so this is a cartoon I drew in first year, so ignore the whether it's physically accurate or not, but I guess the idea is that, say in this sort of cartoon world, you have an internal wave beam that will refract as it passes through a region of changing stratification. And maybe in this cartoon world, the beam will break, if we could imagine that, at the green star. But if the model resolution only permits it to propagate to the yellow star, where maybe it's sort of constricted down or scattered or refracted down to the model resolution, it will break at the yellow star. And so then we might have this sort of spatial dependence on where we might find internal wave breaking or dissipation. So that's sort of the motivation for the study. And so the research questions were, what portion of the energy scatters to higher modes, dissipates, or is transferred to eddies and other non-wave features? And then, of course, does this picture change under different model resolutions? So what we're trying to figure out. So what we've done so far is we've set up 12 different models. So 3 different resolutions at 20th, 40th, and 80th degree in MOM6. I'm only going to show you some results from 20th and 40th. We're sort of waiting to run the 80th properly until we know exactly what we want to do with it. And the 4 scenarios are all forcing, all the bells and whistles. We turn off the tide. The quiescent case is the one I showed you before, where we flattened the isopycnals and the only forcing in the entire domain, the only energy is coming from tides. And then the final one is we flattened the bathymetry along the path of the beam. So notice that we don't flatten all the bathymetry, but we leave Macquarie Ridge in, and then the region over which the beam propagates is flattened. So then we can sort of rule out topographic scatter. So it gives us a way of comparing empirically how important topographic scatter might be for the dissipation of the beam energy. And then, yeah, the quiescent case I showed you before. Okay, and so our method, we have to isolate our waves. And so the way that we've been doing it so far is we start off with a very messy flow field with the stuff in green we don't care about. And then we've got our waves hidden in there. We start off with a Lagrange filter from Shakespeare et al. 2021. And this isolates our waves on temporal scales. And as has already been talked about, this enables us to do coarse graining in a temporal space rather than spatial, which we'll come back to later. Then the second step is we want to, we've removed the stuff that's of the wrong temporal scale, I guess. And then we do vertical modal decomposition after the temporal filter. So this will split things up into the different vertical and horizontal spatial scales as informed by the dispersion relation. And as we learned, it's quite fiddly to get right in a big, messy model. So if you're interested in, if you're doing this problem as well, let us know, and if we've got some code that should work in this case. So then finally, we have the model, we have the output split into all the different vertical modes at the right temporal scales. So just to show you some brief results from just using the temporal filter, this here shows you the M2 energy, so the semi-diurnal tidal frequency energy, and then we split the domain up into these different boxes. So the generation site, propagation, the area where the eddies mostly pass through the beam, and then also the shelf. And what you can see is that there are differences in the energetics in the frequency. So of course, this isn't filtered, this is just the raw frequency data. So yeah, notably when you in the blank case, the quiescent case with no other forcing, we seem to have more energy at higher frequencies compared to where everything else is involved. And I guess, yeah, there's just also a lot of qualitative differences between different cases. This is telling us that where our energetics is changing, but yeah, it doesn't tell us why. And so another thing we can see from the spectrum, or compare with the spectrum, is just straight up comparing the eddy versus the no eddy case. And again, so the dotted line is when there's no eddy in the beam, and the solid line is when there is. And this is the M2 peak, and we don't see a significant difference so far. So I guess just simply doing filtering and nothing else hasn't, yeah. Okay, no real difference. So we used the coarse graining method, so which has already been talked about, which saves me a bit of time. But the difference is that we've done because our spatial scales are fairly similar for the waves we care about and for the eddies, spatial separation won't help us here. So we've done a temporal separation, given that eddies and waves have different, like these eddies and waves have different temporal scales. So this is the energy transfer term that was talked about in the previous talk. And so, yeah, I'll skip over this because it was already covered. Thank you very much. But using the energy transfer between faster and slower temporal scales is what we're looking at here. So this is just an animation showing the phase of the M2 beam down the bottom. You can sort of see it propagating with a bunch of other stuff going on. And you see this really messy pattern of energy transfer between faster and slower terms. So blue is transfer from wave to sort of eddy scales at 1.2F. And you can see the eddy really lit up here. And if we then time average that, then you get this sort of net positive transfer where the eddy is and sort of nowhere else except some little stuff around the generation site. And if we turn off tides, then that disappears. So this is sort of indicating that potentially there's some energy transfer that we could investigate at the different model resolutions. So that's one analysis method. The other one is modal decomposition. Again, so we split the flow into different vertical eigenfunctions at every grid point. And then, so this is an animation showing the vertical mode. So mode 1 at the top, 2, 3, 4, 5. So we're going to smaller horizontal scales. All we've done is decompose vertically in each water column. And what's interesting here is you can see realistic topography on the left. And on the right, what we found is that we expected that topography would be generating or scattering higher modes. But what actually seems to be the case is that higher modes are generated at the generation site, and they simply just continue to propagate rather than getting generated here, which sort of surprised us. We thought that maybe it would start more with high mode and then get scattered and churned up later and produce the high modes. So then this is just looking at the energy case of the different, some of the different experiments. And so we have the generation site on the right, Tasmania on the left, and you can see there are some energetic differences, but we also find that the seasonal variability, just taking 6 months apart, you do see differences in energetics in the domain. So I guess another next step we need to do is pull apart these effects we're interested in from the seasonal variability. So that is one challenge. But we do see some what look like significant differences in the energy propagating along the beam. And then almost there. So this is kinetic energy decomposition by vertical modes. So the black line is the total full field M2 energy. And then the colored lines show you the contribution from different vertical modes. And as you might expect, the 20th degree case has much less energy in the high mode. So this is a cumulative sum. So space between the colored lines means that you've got more energy in higher modes in the domain. And in the 40th degree case, yeah, we see much more separation in the energetics. So I guess we are resolving more vertical modes, or more energies in the vertical modes in the 40th, which is what we expect. And then finally, if we flatten the topography, you do see a similar sort of thing where there is more energy in the higher modes, consistent with what we saw in the animation before, but it does seem to be coming from the generation site rather than being scattered along the beam, which is something we're investigating. Yeah, so next steps in this study, just basically continue with the different analysis we've started with the different perturbation experiments, and analyze the way the modal structure changes and whether this is affected by our perturbation experiments with topography or eddies. And yeah, compare the energy pathways under different resolutions. And yeah, very much a work in progress. So we would all appreciate feedback, thoughts, insights, criticisms, etc. And Andy's favorite GIF again. Thank you.
Any questions for Ashley from early career scientists first? Okay, I'll go with Eric here.
Very quick, what is your vertical resolution?
We have 100 vertical layers in ZSAR.
Across all the
And
horizontal?
we've made it a study of the horizontal resolution. We've left the vertical resolution consistent across the experiments.
Yeah, thanks for the talk. Really nice. You have W equals 0, W at 0 equals W at minus H equals 0 for your boundary condition for your vertical decomposition. Have you played around with different vertical boundary conditions? I mean, it seems like you're filtering all bottom waves with W of 0 at the bottom. I'm wondering what you might be missing by that.
Yeah, true. I guess we were sort of following the Sturm-Liouville approach from other studies where I guess that is fairly commonly done. We haven't played around with like a free surface and allowing, so we are assuming a flat bottom at the, no sloped conditions at the bottom. Yeah.
Thanks. As you change your resolutions, there are two separate things that are going on. One, you admit more modes, but the other is we change how much grid scale like closure is applied if you consider it a fixed spatial scale. In other words, we have a resolution dependent Smagorinsky viscosity and maybe a biharmonic viscosity. Have you considered which of the two is more likely to be more important in the dissipation of the internal waves? And have you considered using a higher viscosity appropriate for a lower resolution in a high resolution model to kind of tease these two separate effects apart?
Yeah, that's one of our intended next steps. So we're really hoping to speak to people like you at this conference and sort of figure that out. So yeah, thank you. That's something we'd really like to do.
Any early career scientist questions? If not, oh, there you go.
Hi. So you are using 1.2f as your separation timescale between the like waves and the non-waves, and I can see that lots of work has been done on figuring out what that separation timescale is when I read the previous work. But do you think that looking at the transfers, thinking about 1.2f is the right timescale, and how do you know?
No, quite possibly not for the temporal timescale. So for the course, the energy transfer, we're using 1.2f. And then for the other, so when we're doing the filtering, just to separate the waves, we're sort of doing 1.2m and 0.2m, so just a band around m2, I guess, when we're just trying to isolate m2. So the 1.2f was just to make sure that we were definitely removing the eddy scale. So it was very rough. It's just you have to pick a point, I guess.
Last question. So you said you were surprised you weren't seeing scattering from topography, but I was wondering whether in the model and in observations you see deep flow, that you would imagine there was a topographic interaction generated by flow. Yeah, not entirely. I guess our expectation was that the beam would hit the bottom and scatter, I guess. We haven't looked too much in the so deep sea observations as well as model. Yeah, we haven't looked too much in the observations just yet. Mostly focusing on getting the model sensible first, and then yeah.
Let's thank our speaker one more time. So our next speaker is Liz Maroon from University of Wisconsin at Madison, and she'll be talking about upper ocean bias development and AMOC in OMDP simulations. Good morning.
Yes, don't start the timer till I got this thing on.
I've already started.
That's especially great since I have time to talk for like 18 to 20 minutes. So I'm going to be skipping stuff on the fly and talking faster than I intended. So hi, I'm Elizabeth Maroon. I'm from University of Wisconsin-Madison. Very happy to be talking about upper ocean biases in the AMOC today. And I'd first like to thank my co-authors because this has been a very collaborative work. So while the figures are actually all mine for a change, the processing that went into them has been very much a collaborative effort with Steve Yeager and Feng Zhu here at NCAR, and Tadra Lowe, who's a grad student working in my group at Wisconsin. So I like always kind of stepping back and taking a look at where we've been. So let's go back through the CMIP archive to look at biases in the North Atlantic. So this is going to be a North Atlantic focused talk, but here I've got, oh, that went too fast. Do I have a pointer? Cool, but that's kind of slow. Well, we'll just do it this way. So let's go back to CMIP1 and take a look at what the SST biases looked like in the North Atlantic. You can say, hey, that don't look too bad, right? I mean, you got some, maybe up to 2 degrees C, particularly in the Gulf Stream region. CMIP2 is pretty much similar, but it's important to remember that CMIP1 and CMIP2 were flux corrected. So you weren't letting the ocean just go off and do what it wanted in a fully coupled system. Let's take a look at CMIP3. And this has got what is very colorfully called in a paper by Anna and Edgeskin, the blue spot of death. So you see this big blue blob in the North Atlantic, over like 2 degrees. There's also, you can see that some of that Gulf Streamish issues along the North American coast also. And you're saying, well, that's CMIP3. Clearly, we have to have done better by then, right? Nope, we still have the blue spot of depth in CMIP5 and CMIP6. You can also see that that red-blue dipole that comes from the Gulf Stream along the North American coast. And so this is, still a problem in our coupled models. This comes, however, not from the coupling, but from the ocean models themselves. So this is a figure from Zagino et al., the OMIP1 and OMIP2 simulations, SST on the top, sea surface salinity on the bottom. Just focus in on the Gulf Stream North Atlantic current region. There's biases are still there. And the reason why they're there is because this is a region with really strong gradients. The Gulf Stream and North Atlantic currents are a front. And so if you move around that front just a little bit, you're going to get big errors just from moving it in the wrong location. And this has consequences for the downstream climate. So here's a paper from Keeley et al. 2012 that shows the difference from 2 AMIP, atmosphere-only simulations. So you take a simulation with the ocean model's biases in it and a simulation without, see how the atmosphere responds. And that's what we've got here in the differences. We've got SST on the left and sea level pressure on the right. And so I want you to look at the sea level pressure one. Those are errors, not errors, those are differences of up to 4 hectopascals. For the atmosphere, that's pretty big, right? So if you're thinking North Atlantic oscillation, the North Atlantic oscillation for a +1, -1 type event is a magnitude of about 3 to 4 hectopascals. So we've got errors potentially in the atmosphere coming from these biases that are on the same order of magnitude as the natural variability in the atmosphere. So this is a problem. So the goal of our project is to understand what's the relationship between these upper ocean biases and the Atlantic meridional overturning circulation. And we're going to use OMIP simulations. I very deliberately used the word relationship rather than causality because these two, the AMOC and the upper ocean biases, are probably coupled in kind of confusing ways. Because if you have a sea surface salinity or an SST bias, that could affect the buoyancy forcing and the stratification. And the AMOC can affect the biases through transport. So it's really hard to disentangle them. So this is part of a project that's funded by the NOAA MAP program in collaboration with the Model Diagnostics Task Force. So part of the project is we're putting together process-oriented diagnostics. So grad student working in my group, Tadra Lowe, she's been putting together model agnostic surface force water mass transformation code that'll go into the MDTF package. Do check out her poster. She's got it run on the OMIP simulations. And then I've been translating some CSM code to calculate AMOC and density coordinates in a model agnostic way so that you can apply it to CMIP or OMIP simulations and then compare them and do some fun stuff with it. The second part of the project, we've been trying to process OMIP simulations in a way that we can do more than just cursory analysis. So we can look at these biases and we can look across cycles, we can look in different regions. And it turns out that actually most of our work so far in this project has been in this second part. And this is where I will get on my little soapbox and try to pitch to the OMDP panel folks here that this has been a lot of time-consuming effort for me and Steve trying to figure out how to get all of the OMIP simulations into a format where we can do analysis quickly, efficiently, that's more than just means or boxed averages. It turns out there's a lot of little issues in the data set if you download it straight from ESGEF that make this difficult. So for example, the OMIP protocol for internal forcing has cycles, but if all your models start at different points, figuring out where the cycles are can be difficult. And to do something like an AMOC and density coordinates calculation, you need to be able to tell if it's a B grid or a C grid, which means that you need to be able to back out the coordinates. And if you can't back out the coordinates because they have names that are confusing, for example, there's one model that has I as its Y coordinates, or just if you can't tell what the U and T grids are because everything got saved on an A grid, perhaps erroneously, all these little things become very time consuming. So if you want to, I have a lot of ideas for OMDP folks for the next OMIP based on Steve and my experience trying to get this processed. Happy to chat after this. The third part, looking at the relationships between the AMOC and the biases is what the talk's going to be about today. Go check out Tadra Lowe's poster for some of the preliminary results trying to connect the water mass transformation part in. As a reminder, the Ocean Model and Comparison Project had two protocols. So these are ocean sea ice only models that are driven by different atmospheric forcing. The first was the core forcing, so based on an n-step reanalysis. Time period 1948 to 2009, 5 cycles that go through 1948 to 2009, then repeat to give the ocean some time to spin up. And then the OMIP2 is used the JRI 55DO reanalysis, the driving ocean version of the reanalysis. Slightly different time period, 1958 to 2018, cycles 5 to 6. For a review of the protocol and the summary, I point you to Griffiths et al. 2016 and Sugino et al. 2020. So let's look at some of, I've got all of the biases now. This is upper 200-meter temperature, so the mean from the surface to 200 meters. You can see the blue spot of death in varying magnitude in pretty much every simulation. There's actually one model, the CNRM one, where both of its entries actually have a warm bias there. So that's kind of interesting, but pretty much all of them have this blue spot of death, and almost all of them have some issues in the Gulf Stream region from the detachment coming at the wrong place. So you've got warm bias along the North Atlantic, the North American coast. OMIP2 is pretty similar. Just a really quick glance, blue spot of death is in most of them, and you've got issues in the Gulf Stream region. Unsurprisingly, you've got the same issues in salinity. So if you're going to have, the issue is that warm and salty biases go together, whereas fresh and cool go together. So here you've got a fresh spot in the same location where that North Atlantic current isn't getting the meanders right in most of the models. And you also have 2 salty water along the North American coast where the Gulf Stream isn't quite right. So this is OMIP1, this is the mean for CMIP cycle 5. Here's OMIP2, pretty similar. And again, I've also had the contours for E and 4, which we're using for our climatology there to sort of give a reference where the fronts are. So let's just summarize real quickly. Here's the multi-means for OMIP1 on the left and OMIP2. So this is upper 200-meter average temperature. On average, you have a blue spot, an error there, because it's just the models just aren't getting the North Atlantic current in the right spot. It's getting the North Atlantic current's meanders way too far to the east of the Grand Banks when it should be much closer. Can't really tell the difference between OMIP1 and OMIP2, even though there are different entries. So these 2 multi-model means aren't identical models that go into each of them, but this really does suggest that the forcing isn't playing a big role in the differences between them. Here's the same thing for salinity. Again, if I took all the labels off and switched them, you probably wouldn't be able to tell which is salinity, which is temperature, which is OMIP1, which is OMIP2. They all really have the same kind of patterns. So issues with Gulf Stream attachment and issues with the North Atlantic current. And so here's just another representation of that. I've got a scatter plot here of salinity bias on the x-axis, temperature bias on the y-axis. I've got all of the OMIP1 and OMIP2 simulations in there, and I've got the average for each cycle. And I've done it just for this box where you've got that greatest error in the models. And you can see that for the vast majority of the models are in the negative space. So, salinity is too fresh, too cold. And then there's a couple of models that aren't. They're on the other side of things, a little bit too warm. And there's some models right in the middle there. So now this is where it gets really fun, where having processed all of the OMIP simulations, we can start to do some slightly, more than just means of fields. So what I've done here is I've taken empirical orthogonal function analysis in the model dimension. So what I've got here is the first 2 modes of relative to the multi-model mean. What do these biases look like? Or what does the temperature variability across model space look like? So this first EOF says that in this location, relative to the model mean, which has a bias there, the models either vary and they have too cold or even colder or slightly less cold. But as we saw before, most of them have a cold model bias. The second EOF says that across model dimension, the models tend to have, this is kind of like a Gulf Stream type mode, and it's also coupled into the Labrador Sea. So when you have it's too cold along the North American coast, you tend to be too warm in the Lab Sea and throughout much of the subpolar gyre. Interestingly, the variability across model space for salinity is kind of different. Salinity has this very either EOF1 is all basin, too warm, too cold. And then EOF2 is kind of a dipole. And you could imagine very easily that there's something going on with the AMOC in here, AMOC transport or AMOC state, more with salinity. So now let's move on to what AMOC and sigma coordinates looks like. I've got the OMIP1 cycle 5 mean for all of the simulations that I was able to get processed. There are a few I had to throw out because I didn't have all the variables needed. So I need temperature, salinity, UO or UMO, so the fluxes, and VO or VMO. And there were a couple that didn't have all of those. And then I had to throw out a couple for non-closure. And so we're going to go back to those non-closure ones and see if we can get them working. But, you know, a 12 out, I think, is 17 isn't bad. So I've got the multi-model mean on the left and some arrows to remind ourselves of what the circulation looks like in density coordinates. So you can see the upper subtropical cells there at the top. And then I've stretched the y coordinates to look at the bottom cells, since that's the focus of our interest. And you can see if you just look at each of the entries, there's a huge range of AMOC strength across all of the entries. You know, you've got some that are in density space have AMOC in excess of 30 sphere drops as a max stream function, and some that are, you know, way much more down towards reality, closer to 15 to 18. 3 minutes, thank you. Here's OMIP2, pretty similar, maybe slightly weaker. So here's something also fun. I've got because I have run the AMOC and sigma space code on all of the simulations myself, they're all on the same grid. So I can do an empirical orthogonal function across model space and show that the main variability across these models for AMOC, so black is the multi-model mean, the red is the EOF. When you have a stronger AMOC, the deep western boundary current tends to be at a denser class. And in the subpolar North Atlantic, you also shifted all of the isopycnals down towards denser densities. So that's pretty cool. So now what we can do is we can start connecting these biases as a kind of parameterized by these EOFs with AMOC. So on the x-axis, I've got the two temperature PCs, so the strength of the, you know, that cold spot, with AMOC on the y-axis. So what you found, there's strong relationships between each of them. Models that have a stronger cold spot are associated with a weaker, lighter AMOC. This suggests that there could either be a connection between the AMOC circulation and its transport. You know, for a weaker AMOC, maybe you're not transporting as much salty, warm water poleward, or it could be the cold bias impacting the AMOC itself. So you have surface heat fluxes that are too weak, so you're not getting as much buoyancy forcing. You can make similar arguments for the second EOF. In the interest of time, I'll just briefly say that salinity, you can also do the same thing, similar relationships. Another way you could have gone about this analysis, however, is applying maximum covariance analysis. So taking an SVD of the covariance between the bias and temperature and the AMOC. So what this shows is you get a mode that explains 86% of the covariance, where you have a AMOC that is weaker and at lighter classes, except in this everywhere, is covariating with this cold spot of death combined with some of the Gulf Stream biases. And just to sort of say, so that's the EOF1 for AMOC, and here's the left mode pattern for the MCA analysis. They're the same thing, just you switch the sign. So this really does say that for the AMOC, that variability across model space, models that are stronger are really linked to that pattern of bias. So models that have greater, in this case, greater cold spot bias are also going to be the weaker ones. So one last result before I get the hook. So here I'm tying it all together for the temperature part. So I've got the two EOFs on the left, the temperature right mode from the MCA on the right, and our multi-model OMIP mean bias pattern in the middle. Something interesting, so you can know that the two EOFs, if you kind of like do a linear combination in your head, that's what you're going to get for the MCA mode. That MCA mode really combines those EOFs together into one thing. So we could have just started with this analysis and, you know, combined it that way. You'll also notice, however, that the temperature right mode is not the same as the multi-mean bias pattern. What this is saying is that models that have a greater expression of the cold blob tend to have that it's a little bit further to the north of where the bias is located. So it says that the variability isn't in the exact same location as where the multi-model mean is. So I think I'm not going to get the hook. So a quick summary, we're processing OMIP simulations for easier multi-model comparison. I have thoughts and opinions about if there's going to be future OMIP simulations, what might make that easier. Subpolar temperature at salinity biases covary, not surprisingly. Models that have a weaker AMOC have a deep western boundary current and North Atlantic current that are at lighter water mass classes. This is really connected to those temperature and salinity biases. So where we're going from here is we're going to look into development in the cycle one of, what's causing the biases first? Is it a development in the AMOC, really quickly as it adjusts from the initial conditions, or is it the development of these biases? And we're going to see if that helps us disentangle some of this issue. Thanks for your interest.
Thank you.
Hi, Liz. Great talk. Two things. One very quick one. CANISM 5 and CANISM 5 Canoe are exactly the same physical model, so they should be bit for bit identical. So choose one or the other. Don't use both.
Cool. And I'll just mention that was one of the easier models to get processed into AMOC. It worked out of the box and had no closure issues.
Good. I'm glad that happened.
Thank you, Andrew, I think.
Second thing, so I'm kind of wondering what the role of mixed layer depth bias is in these results, because if you take a strict 1D look at it, right, you're essentially doing a form of flux correction because you're forcing your prescribed atmosphere infinite heat capacity, no variation there. So I'm kind of curious to know. We know that the Gulf Stream affects where the mixed layers form. So is that us? Yeah, what is the role of the mixed layer bias and how does it map on to these temperature and salinity biases?
I'm very curious about that also. So Steve Yeager over there just processed the OMIP simulations for mixed layer depth last week, and I didn't have time yet to put it in this presentation, and I only have 15 minutes, but that is definitely something I'm going to follow up on.
Early career, one more story.
Technically, I'm still early career. That's surprising me.
So thanks for the presentation. I have a question because so we've been talking all about the physics, but have you tried to relate maybe the differences between models to the numerics? I don't know, do a list of every single feature of the model. I guess it's pretty difficult to do, but and then try to see if there's a pattern between, I know this model is using this scheme and this combination of stuff, and this explains maybe this and that. Or,
yeah, that's definitely something that's been on our mind. As you said, it's kind of difficult because you have to go through the papers for all of the models to figure out exactly, okay, who's using this GM number, that GM number. Certainly an easy thing that I'm planning to do is partition the models by resolution. There's some indication that maybe some of the higher resolution eddy permitting to eddy resolving models might do a little bit better or have different dynamics. So that'd be an easy first step. But yeah, certainly that'd be something we'd like to do if you can figure it out. Or another easy thing is B grid versus C grid, because that's something I have to calculate anyway.
Paul and then Arnie and Steve.
You might have just answered my question. I wasn't. Does the blue blob of death diminish at higher resolution?
Sometimes. So I think that's the Chassagne et al. Paper has high resolution models, and it seems like for some models it does, but it's not necessarily improving in all of them. But I think I'll defer to the person who wrote the paper, who's sitting here in the room, for that question. Does resolution improve the SST biases? I think the answer is sometimes.
Maybe.
Maybe, yeah.
Well, all the simulations that we did were forced simulation, therefore they were prescribed atmosphere, therefore the SST bias is now. Yeah, so it's a bit harder to answer your question this way. It's not coupled.
So Steve, I guess, and after that we'll move into general question discussion.
Yeah, thanks for the talk. This may be coming from a couple model perspective, but most of the models that I recall, the heat transport is weaker. And so you basically juice up the AMOC to get a stronger heat transport, and the AMOC then goes outside of what we think from rapid. Have you looked at the heat transport in these simulations, and is there any correlation with the blue spot of death with weak heat transport?
I haven't yet. That would be a great thing that we could do. I haven't processed that one, and I'm not entirely sure. I mean, calculating all of these things for OMIP simulations consistently is tricky because you have to find all the correct diagnostics. So that would be a less easy one to do, but certainly it could be fruitful going in that direction. Unless the models all, it depends like which models contribute to which diagnostics and who has heat transport.
So about your concern about OMIP, from my recollection in the Griffiths et al. 2016, we asked for heat transport, we asked for AMOC on density coordinates. So Don't put the blame on the OMIP designers, put the blame on the model suppliers, right?
Absolutely, I agree. Something I'd also, might also be an interesting thing is if there's funding somewhere where somebody could put together a little package to say, if you've got a data catalog of all the OMIP simulations, read them in and then provide that to the community so that there's, somebody's already gone through the efforts of, finding these issues with I as J and getting the cycles right. But you've got to find the funding and the time for somebody to sit down and do that time-consuming work. But I agree, this isn't this isn't the experimenter's design's fault. This is how it just ended up.
One last question.
So most climate models have shallow AMOC compared to what we think the AMOC should be. If you're saying that there is a different water mass classes depending if they are deep or shallow, can you speculate a little bit on how important or what is it, the issue of having a shallow AMOC on climate modes or climate interaction between the atmosphere and the ocean? How much does it matter?
I think to do that, I would need to rerun the code and for depth space, because this isn't necessarily shallow, it's in density coordinates. So they could be higher up than we think they are based on the density coordinates. Is that kind of, or are you thinking like shallow in terms of density?
No, I was thinking about shallow as in depth. Most, several isopycnic models are able to get a very deep western boundary current and a deep cell of the AMOC. Most current climate models have a very shallow that does not go below 3,000 meters for the AMOC. So is the response time or the TNS property of that AMOC, how does it impact the atmosphere? Maybe it's a question beyond this.
Yeah, I think that's a question beyond what I've done
For the
here.
AMOC meetings.
Yeah, that's next week. Yeah. I'd have to rerun the diagnostics for Z-space so I can see which ones are actually shallow or not. But yeah, it'd be interesting to look at that.
Let's thank our speaker one more time. So before we start the discussion, since we shortchanged the questions for this morning's speakers, I just want to ask if you guys have any questions for Peter, but particularly for Manita and Hussein. Any specific questions? I know that Alistair had a question for Peter and then Manita. Okay, let's start with Alistair and then Bob. Okay, Alistair's thinking still. Go ahead.
Okay, so Manita, you had a beautiful analogy of there being two tones in the ocean. There's the low modes and the high modes. But when we run numerical models, we also have the equivalence of the audience crackling their gum wrappers in the audience and bad acoustics and all the numerical noise. In your analysis of model simulations, where does that numerical garbage show up in terms of your two modes? And have you thought of good ways that we can kind of separate out the numerical artifacts from the real physical processes that you're actually trying to study?
So the assumption to begin with is that a geophysical system is composed of these two motions. But of course, you're right. The thing is, it's also difficult. So just as difficult it is to define a balanced motion, a balanced state, it's equally difficult to also define what is unbalanced. So in this context, what I showed, of course, I interpret this as a residual signal equivalent to the wave signal. But of course, it consists of other unbalanced motions as well, which is another level of complexity to resolve. And if you have a model, of course, you have a certain cutoff resolution, and beyond that, you have numerical noise, as you say, which of course needs to be tackled differently for different models, how you tune it and what is your dissipation and so on, for example. So the spectrum of the wave, that's like at the higher end, that's not explicitly resolved. So there's also probably other secondary instabilities, because we see in some of the simulations that when these waves are generated by these processes, it leads to partly wave breaking or other instabilities, but that's not explicitly separated at this stage. Of course, that would be interesting to do, but for the concerns that I showed so far, that fits. But of course, I mean, but it does still resolve part of the internal wave spectrum, maybe not all the way to the breaking, but still parts of it. And you can see this, like if you do frequency wave number spectra, for example, it does go above F, frequency, and if you have Doppler shifted range, you can also see how it follows the dispersion relation. So yeah, there's still some things to do, but what we have so far is still indicative of the wave signal, and it's more precise than what is typically or traditionally assumed to be a wave signal in a model.
Okay, so this one was for Peter, and I have a very concise note here, which I forget exactly what it meant. But basically, it was the same question I spoke to you about in the coffee, but for everyone's sake. So lesson 2, you had several lessons lit up there, and lesson 2 was about the vector invariant equations, and it wasn't quite clear, needed some clarification whether you were advocating for the vector invariant equations or against them. There was a lesson there, and you would only use the vector invariant, and so just if you'd like to just clarify for that for us.
I think I would argue for the vector invariant, and in particular, if you do the vector invariant, then do it properly. And that concerns the cross product itself, which is fairly easy if you're in a hydrostatic context. It's a bit, and it's often wrongly done in the non-hydrostatic one. I mean, I saw it in atmospheric codes, and I was surprised what I see. And yeah, the other part is the kinetic energy definition, which is for me a part of the vector invariant form. And there are also a lot of ad hoc choices that destroy the energy conservation, and that is to me equivalent as instability. So you put that into your definition of the model. You make it unstable, and you might get then wrong variability for the wrong reason, and you have to damp it again, and so on and so forth. This is what I see in the literature, and which is done by many groups, in particular our ICON group. This is not done properly.
Any questions by early career scientists?
Questions for Peter. I was wondering about explicit time stepping, and if you can say anything about stability or conservation properties in your system if you used explicit time stepping.
It's easy, you lose it. I mean, if you go explicit, then you will lose the conservation properties. I did this implicit here for the fully implicit time stepping here for, let's say, for beauty. So you can show that all these properties survive, but that might not be an efficient way of doing that. So, but this analysis gives you a hint where you have to do compromise, for example, to be efficient. These large matrices that would occur in a fully implicit scheme. I mean, we cannot. I'm not aware of a method that does efficiently invert that. So that is the that is the problem. So then you do compromises. But this is, I mean, I think that's fine as soon as you know, as you do that with some consciousness, and then you are. I think the most important lesson is probably for the spatial discretization, how to set these things up to close budget. And then if you use a practical explicit or split explicit method, I mean, then you are within the time truncation error. You lose something, but you have I would hope you have a better control as if you do some mistakes in the spatial discretization.
Steve?
My question is for Manita. You showed a line diagram in which you had Rossby number on the X, and I think it was balance or something like that. The higher order asymptotic theories that you showed started to get less balanced than the lower order asymptotic theories when you got to the larger Rossby number. There was a crossover. Most of what you were focusing on is that the higher asymptotic models got more balance at higher Rossby number, but there was a crossover toward around 0.2 or 0.3 Rossby number, and I just wondered if you could comment on that crossover.
Yeah, right. So what I showed was diagnosed imbalance as a measure for how good the balance is, and the crossover is a good point. I'm not quite sure what exactly might be triggering that, but I know that for as I showed in one of the plots, if you go to higher Rossby numbers, you have other instabilities which can occur. on top of what you provide, for instance, symmetric instability or convective instability. And that might lead to secondary interactions, which of course we're not explicitly looking at here, but that could change or be the reason of this this crossover. But the main thing is that if you go to large, first of all, if you go to large Rossby numbers, you have more wave emission. That's just going to more unbalanced regimes. So you have a less balanced contribution. And if you go to higher orders, you can see more wave emission, but only for higher Rossby numbers. So but that also means, so a higher imbalance means that you have less balanced state. But for higher orders, because you extract more imbalance, you means you have a more precise balanced state. So it could also be related to this equilibrium point. So just if you think in terms of slow manifolds, so it's not clear if you have this jump or this trajectory shifting around from the slow manifold trajectory, where exactly they go. So because they just oscillate around, it could be, it's not clear if it always is below this actual trajectory, the slow manifold, or above or below. So, and the longer you the flow evolves, because there are other things changing with the flow, the balanced state and the imbalanced state at that point. So that could trigger this kind of swapping of up and down of this crossover.
This is a question for Peter about the conservation laws that you were showing. It was not clear to me if any of them pertain to material conservation, Lagrangian conservation. For example, PV, is it conserved in a material way? And if so, is it any function of PV conserved?
No, it's not conserved in a material way. It's the global integral is conserved. All the conservation laws that I showed were global integrals over the whole domain. I guess one can break that up into some local statement plus what goes over the boundary of some local region, but I haven't specified that. I haven't formulated that for the potential vorticity, for example. This is, I think, each exponent of that quantity is conserved, again, globally, but not in a Lagrangian way.
So this is another question for Peter. The way that you were describing basically your mimetic properties, you have all these nonlinear conservation rules that you're satisfying. When we're discretizing things on a regular grid, we're often worried about computational modes, the checkerboard null mode on a B grid, the kind of the streaming velocities on a C grid. A lot of those, at least naively, might seem to be inconsistent with kind of the beautiful properties that you have. Are there any computational modes with your discretizations, and have you managed to completely control all of the computational modes on the grid?
I'm most familiar with the computational mode on the triangular grid. There you have a divergence mode, and this you can in fact control with the mass matrix. So you saw in the continuity equation you have divergence of m of velocity is 0. This is the part that controls the divergent mode, and it's at the same time it's compatible with the conservation law. It does not destroy the energy conservation, for example. Maybe one remark what I didn't say in the talk, for a rectangular grid, you have two options for defining the kinetic energy. You can do it as it's usually done by the sum of squares. This is fine on that grid. You can also go for a reconstruction, of course, and that could be an additional way or degree of freedom to filter some modes, because also on that grid we have noise in the divergence mode, and that would be an interesting experiment to see if that is controlled by a different formulation of the kinetic energy. The price, as I said, is you have a mass matrix, which you have to invert to get the full conservation laws, but you don't have to invert it to control the noise.
So I just want to give a chance to the online folks, but I just want to make sure that are there any questions for somebody other than Peter? Online? Paul was first, and then Mats, and then Steve. Okay, so then Mats, let's just give it to Mats.
Yes, this is again for Peter. Sorry. So the Arakawa schemes, they typically assume, at least in my understanding, center differences to achieve the very nice conservation properties, which has issues with very dispersive solutions, and maybe you want to go to higher order or up in the biasing of flexes. So in your framework, do you need these kind of simple discretizations to achieve your conservation properties, or can you allow higher order up indifferencing, for example?
I think our scheme is in the plane, it's second order, and I wish I would know how to go for higher order. I don't know that. So this virtual element might give some indications how that is done. But if you go for higher order, you have the usual problems of overshoots, undershoots, and so on. That's nothing different, and you have to insert additional measures to control these things. Arakawa was, Arakawa was, the beauty of this thing was that he showed how to control a blow up or a computational noise by satisfying an additional conservation properties, like the entropy conservation. It wasn't conserved in an older scheme, but he repaired that by showing that you get cleaner solution if you satisfy entropy conservation. This is a little bit my hope in the background, that the better you are in terms of conservation laws, the less numerical problems you have, but certainly not all. I mean, as I said, higher order means you have to deal with additional issues.
So we'll have one more question by Steve, and then I want to get back to these discussion questions because we have half an hour left. Go ahead, Steve.
So this is a question for Hussein. Lizzy Barnes showed a nice talk about coarse graining in time, and Hussein, I was wondering if you could comment on, are there any lessons that you might have about transferring from what mostly is used in space to time, or is it transparent? Is it really an issue, or is there no issues?
The quick question is, I don't know. I've thought about it, but I haven't gone far. In principle, coarse graining can be done in space and time at the same simultaneously. So in terms of looking at the cascade and things of the sort, the cascade was formulated thinking about the work of Kolmogorov and Onsager, Richardson, was formulated in space, spatial scales, not temporal scales, at least the concepts. And so I don't know, personally, I don't know how the cascade looks like when decomposing things in temporal scales. So that I'm still trying to understand or trying to get to grips with it. Yeah.
Thank you very much. So we have about half an hour before lunch. And as the organizing committee, we put down, since this is a workshop, we put down some discussion items or discussion questions for each session. We have about 8 of them, I believe. And then the idea was to sort of get your input with these questions. Maybe these questions are not necessarily relevant, and some of them maybe they may have straightforward answers we may agree on. Some of them are intentionally sort of more controversial questions than others. So we would like to essentially sort of have discussions on these topics that we listed. And then as your homework or workshop work, before you came to the workshop, I guess, we distributed these workshops so that you can essentially think about some of the answers that you may provide during this discussion on your whatever flight home or flight, not home, flight here. So I just want to make sure, also point out that we have volunteer note takers, and for this session is Spencer, who's sitting right there. Thank you for taking notes. So I'll just read the questions, but these are, I mean, we can essentially have discussion on any one of them and not necessarily in a particular order. So we put down sort of 4. I should also mention that some of these questions, when we actually listed them, can be valid for any other session because there is so much overlap between the sessions. And I unofficially call this session 1 as the hodgepodge session because any talk that didn't really fit well with another session got lumped here. So it was a bit difficult for us to come up with particular questions. But anyway, so one question was multiple questions there, I guess. How have the recent advances in ocean modeling helped our understanding of the ocean's dynamics and the role of the ocean in the climate system? Or how does understanding dynamics feed into improving ocean general circulation models? Second question was, how can we better use observations to evaluate and advance ocean models? Do we have the observations needed, including for evaluating high-resolution models? Is the ocean modeling community tackling the relevant problems, including model development efforts? And what are your thoughts on a hierarchical modeling approach from coarse to ultra-high resolution modeling, especially within the context of as many groups go to higher and higher resolution simulations? So, any thoughts? Any comments? Hopefully starting with early career scientists. If not, this will be like a 2-minute session. Yeah.
Thanks. My question is for Elizabeth. There. Specifically, question 3, you talked about diagnostics in terms of ocean model and OMIP and all that. But in terms of addressing the blue spot of death, I feel like you've shown it's very important, but do you feel like there's enough being done to address it besides just maybe higher resolution?
That's a tough question because I think I don't really know the answer of how you address it. I think it's probably a lot of problems besides just resolution. So I've got a totally other project where I've done something kind of wacky where I removed the entire Mid-Atlantic ridge and that improved the biases in the Gulf Stream by a substantial amount, like 30%, which is very strange. So that really suggests that there's some bathymetry far away from the coast that could be giving you a remote effect on these biases. So that's just to say, I think it's a really difficult problem to try to figure out what's going on there. And resolution certainly seems like one avenue forward, but it may not be the only thing.
So I think number 1 is a really interesting question, but I think there's actually a precursor to it, not how the recent advances, but what are the recent advances? Because I mean, like we're all working on 1,000 different.
That's a question in one of the other sessions.
Oh, okay. Okay, maybe that's what I thought about. Okay.
Just thinking about question 2, we work a lot in the Southern Ocean. I think I'd almost reverse that. And I think the ocean models are actually advancing the observations a little bit. Like we're actually telling, I think we're telling the people where to drive the boats a little bit more, which is kind of cool. But no, we don't have enough observations for high resolution model evaluation.
Steve?
So I'm going to comment on number 3 and 4. On number 3, I think that the Gulf Stream problem has been around for so long, and it's really something that, I mean, Ashley showed, even in OMIP, where you're forcing it with a prescribed atmosphere, you still get these issues. My sense is that the Gulf Stream is incredibly sensitive to the numerics of the models. I mean, we can change the way we calculate the Coriolis in MOM6 and change a whole lot of stuff around the boundary currents. I would like to see that there be, there's a lot of numericists in this room, but this is kind of where they are right now. And it's hard to find funding to support very, very tough basic questions which have a more numerical perspective than others. And students and postdocs, it's hard to do those kind of problems. So that would be my pitch for those that have the money and those that want to write proposals to do that, to tackle them. It's really important. Number 4, hierarchical modeling approach, I think highly of it. I'll talk about a hierarchy on Thursday. My sense is that grid resolution hierarchies are really valuable in the ocean, and more people and more groups are doing that, and I just think we should encourage that. Hierarchy is a term that's used across modeling groups in different ways, but I really think that the grid resolution hierarchy, where you have because it's such a mesoscale, and getting to this, even to the sub-mesoscale, is such a big deal, and we really want to understand what we get when we enable those pieces of our dynamics.
Yeah, I have a thought that perfectly fits to what Stephen just said. We tend to think about grid resolution in terms of increasing the horizontal resolution to the mesoscale, to the sub-mesoscale. But we are lacking, and that's a thought, I don't have an answer on that, we are lacking often the vertical resolution. So we have to think about how to come up with good efforts in what way we would like to enhance the vertical resolution as well, because sometimes it's a value, or let's say the ratio of vertical versus horizontal resolution that sometimes works in a different sense. For example, there exists work in the overflow, for example, where coarser vertical resolution produces a nicer result at higher resolution, for example. So there needs systematic approaches.
Anna?
Hi, yeah, that falls nicely into what a comment I would like to make. So Diego didn't want to speak. He's giving a talk on Thursday, and we are precisely, well, he is trying to address that issue. How can we increase vertical resolution? And it's basically the combined effect of horizontal and vertical resolution that seems to help. And yeah, a bit of mystery here. We kind of have the impression we are on track to understand that blue spot. And you are writing that it seems to come from far away. The effects of the biases you see that far north come from other places in the North Atlantic. And if I may add a comment to number 2, it's not just observations. I agree, yes, we need more observations, but it's also the tools we use to do the assessment. And I think I've mentioned before to Gökhan, neighborhood assessment, which has also already been used in the atmosphere. And we already have some tools to look at neighborhood assessment in the ocean. And it's only when you use those that you realize there is an improvement by going to high resolution.
So if you can introduce yourselves when you, for the first time that you speak.
Okay, so I'm Anna, and I think it's fair to say I'm an early career, only because I've only moved to climate science a year ago. So from that aspect, Met Office, yes, UK.
So is it about, we have quite a few, and is it about this particular topic?
Just to follow on.
Yeah, then Eric, and then I don't know your names, but you can introduce yourself. So let's Eric, and then you two.
Eric Rassignier, from my hair, you can tell I'm not the early career anymore. So I think for vertical resolution, often one argument is put forward that as you decrease horizontal resolution, you need to resolve more vertical modes. I think that's a red herring, because most models can resolve up to 5 vertical modes with a vertical grid that have right now. What we found is really important is to be able to discretize the water mass that you want to represent in the model, and how well they're represented, and how much numerically induced mixing the vertical grid induces.
Okay.
Hi, my name is Maheshwar Pradhan from India, and I am particularly asking about the second point, where whether do we have sufficient high resolution observation, like everybody is talking about like horizontal or vertical scale. So I would be highlighting the temporal resolution, whether we have sufficient data or like sub-daily scale data to evaluate whatever the model developments have been going on. And second thing is whether the existing data, whether the sub-daily scale data can be used like extrapolated to other time domain, like suppose I have a sub-daily scale data set for the year 2008, and whether I can use some tool to extrapolate those data set to another year and evaluate my model.
Yeah, hi, my name is Caroline. I'm mainly doing, also, I guess I'm a
young researcher. I didn't check the definition. So I'm a mathematician, so I'm into definitions. So I'm doing mainly numerics for CIs and modeling for CIs. So I'm not so, this is why I'm asking out the question, because it's to this numerics, which has popped up. So this is a question to the community, because I don't know. Is there interest in doing development in higher order numerical methods? Because what I'm seeing from CIs is that we can do the most advantages in moving from just first order approximation actually to just going to a second order and then acknowledging the physics. So the question to this more ocean modeling community, because I don't know, and this maybe is a super naive question, and I'm super interested in numerics. Is there attempts to doing high order numerical schemes for the ocean discretization, horizontal and vertical?
Takers.
There should be at least 5 people in the room.
Yeah,
Say
I
something
know.
here. Come on, either him, me.
You want to take it?
Actually, I think that some models go all the way to oh, sorry, Florian Lemarié, so in RIA researcher in France, Grenoble. Yes, I think that I don't know the details for MOM6, but still you are using at least second order accurate schemes. Yes. So in NEMO, it goes to fourth order accuracy, even in the vertical for vertical advection, for example. And but there are some terms, for example, for gravity wave propagation. It's more the accuracy in the continuity equation and pressure gradient scheme, for example. So it's more or less all the time second order accurate. And there could be a value of going higher order, for example, for those terms, for sure. And after that, you have the problem with the coastlines, of course, to handle if you have a very high resolution, high order schemes. But the value for global simulations, I have to admit that I don't know.
So this is in response to the same question. Yes, the answer is simply yes. If somebody wants to try contributing higher order schemes, better numerics, yes, please do. We have built community ocean models with an eye towards trying to make it as easy as possible to contribute while still doing the quality control to make sure you can do so without disrupting anything, so you can do it without fear. One of the big challenges I've seen over the decades is you get a lot of people come in, you have some nice ideas, but it's really hard to translate them into realistic models. Realistic models take a lifetime in a community to build, and the timescales for getting a paper published, getting a job, getting tenure are decidedly shorter than that. So if we as a community can mobilize ourselves to make it easier for people to try out new ideas, transcending the kind of the barrier from the idealized into the realistic, and see whether it has an impact on the blue spot of death if you have better numerics, I think we will be all doing ourselves a service, but it's also something that's been a real challenge. Recognizing ways, coming up with ways to properly recognize people who are contributing to model development, it doesn't really map onto the same metrics. It's really easy these days to pick up a model and use it, get some nice papers out, advance your career. It's a lot harder for us to recognize people who are contributing meaningful, challenging, difficult ways that may not lead to a huge stack of papers, but a few really key ones. We as a community, I think, need to do a much better job of trying to recognize that kind of contributions, especially if we're going to address the question of, are we doing enough? Well, the way we do enough is we make sure that all of the people in this room who are interested have an avenue for actively contributing and making that contribution. Thank you.
Just a very quick comment,
Let
actually.
Spencer catch up. Have you got all of that?
But so sometimes there is also the perception that higher order scheme, the computational cost could be a problem actually. But if you really analyze properly the schemes, so you can find time schemes that are very, that don't lose stability when you increase the order of accuracy, for example. So this is something that is achievable for a cost that is acceptable, I think.
Steve?
Yeah, so getting my names right, I'm sorry. Liz Maroon's talk prompts me to suggest she and others, myself included, with thoughts of model comparison projects and model, comparing across models and having headaches and nightmares about the difficulties of doing that. There's OMIP is going under CMIP 7 is ongoing right now with the development of protocols and diagnostics. So please, everybody get involved in that. Speak up, be co-authors on Fox Kemper et al. I think is going to be the next OMIP manuscript. You're welcome to come and do it. Others as well. And that's where, this passion that Bob has about model development can also be for those that are more inclined to model analysis. You can get involved, and the community is trying its best to open that up and not let it be, people getting frustrated and going off and doing other things when they can't get access to the data in the way they want it to be done. So so many of the early career people are much more better off at analysis than us older people. So please do get involved and make sure that we supply the data sets from CMIP 7, for example, that are going to be useful for community.
Okay, Andy?
Hi, Andy Hogg from Australian National University. Just coming back to Eric's point about modes, I certainly agree that vertical modes are not the only thing to worry about when you're setting the vertical resolution. And in our experience, it's really a big factor is the resolution very close to the surface. Seems to make a big difference to models in some areas, particularly in ice-covered regions. And that sort of brings me on to another general question relating to 3 that I'd be interested in people's opinion on, which is, do we need a revision to the sort of decades-old recipes that we use to force our models from a prescribed atmosphere, particularly as we move to higher resolution and particularly as we move to higher vertical resolution close to the surface? Are the sort of bulk formulae, do they need a revision or a systematic approach to improving them?
This has been a topic of actually US CLIVAR as well, and we have been actually discussing this thing. So what we are planning to do is, we don't know how we are going to do it yet, but in the US at least, we are trying to get an interagency group to revisit the entire bulk formulation, whether the assumptions behind them are correct or not. So there was a talk by Vijay from EMC, NOAA, and then he pointed out some of the deficiencies of the bulk formulations. And then NSF program managers are quite keen on essentially revisiting some of these issues as well, because those bulk formulations have not necessarily been revisited over the last 30 years. There are new observations, some new developments within the bulk formulation. So this is going to be, hopefully within the next few, I don't know, maybe 6 months or something, I'm trying to essentially get together a group within US CLIVAR, and certainly we can open it to international as well, because it's the purview of the C-Force project that we are redoing the forcing fields. But I think that you're absolutely right. I mean, we need to revisit not only create a new set of forcing data sets, but we need to revisit the bulk formulations, the assumptions behind that, and then any other, like the forcing. We keep cycling 5 times or whatever, right? Is that the right approach? And then there are also some ideas from GFDL in terms of, rather than using salinity restoring, using another approach to sort of constrain salinity. And Matt Harrison was leading that effort from GFDL. So I think everything is on the table. Andrew, and then is it directly? Okay, so go ahead, Liz, and then Andrew.
Sure, I'll just respond quickly to Steve and Bob and say happy to get involved. Definitely have thoughts, but also to just acknowledge that it's kind of the structure for a field where it's difficult to do numerical problems like these at a university, where you're really constrained by funding. And then you're also constrained by the time scale it takes to spin up a grad student and the kind of things you need to show on the grants that you can get funded. And so I think it really speaks to, we need to have like collaborations with the folks at the national labs to find the right people to work together with grad students or with postdocs so that it becomes feasible that you can do that. And it's a hard problem. It's just the way that, at least the US's modeling enterprise and academic enterprises are set up. I'd love to move in that direction after I get tenure and I'm less constrained by necessarily paper counts and things like that. But it's a hard problem.
Is it in response to this, Steve? Okay.
Yeah, so one of the reasons I took a job at GFTL 30 years ago is because you can address and look at the hard problem, the long problems. But I just want to say that the world is changing and it's becoming even harder at the labs to do the long problems. So for those that appreciate the big, tough problems in the universities, wherever you are, keep advocating for letting someplace in the planet do the hard, long problems. In the US, it's really the lab. So, you know, there's a lot of concern about the viability of that approach. So please keep saying what you just said.
Andrew.
Yeah, I just want to call back to the question about the higher order schemes and then also kind of tie it to number 4. So at the last Commodore, Julie had this really nice talk about, you know, what is the carbon footprint and energy footprint of doing these high resolution simulations, and is it worth it? And I think that there's 2 things that we try to do when we move to high resolution, right? One is we try to resolve better like spatial and temporal scales. The second one is we just simply are trying to reduce numerical errors, right? Truncation error. And so by having the higher schemes, maybe it's double the cost to do the computation. But when you go from 8th degree to 16th, 16th to 32nd, right, you're scaling those errors quite rapidly. So I think there's a large incentive to it. I think the metric of it almost needs to be something like scientific output per computational, per flop or something like that, you know, but there's some metric out there, right, that kind of justifies that higher order thinking of like, okay, just because it costs 3-4 times as much doesn't mean that it's not worth doing.
So I'd like to bring up something in terms of this hierarchy, which we've kind of ignored, but that Ashley presented in a really interesting way. The complexity of the models, the physical processes that we include or exclude may have as much to do with some of the biases we see as do the numerics. And so specifically, Ashley showed the internal tides and the internal tide beams. We decided collectively as a community something like 40 or 50 years ago, yeah, the ocean's pretty linear, the tides are high frequency, they're annoying, let's just ignore them. And yet, when we look at the blue spot of death, we have some regional simulations where we explicitly put in tides, and the details of how we handle the tides and the self-attraction and loading, they move the Gulf Stream separation. So it's entirely possible that one of the things that's happening here is that the ocean really is nonlinear, and when we exclude energetic, important processes, just because we decided once upon a time that, yeah, they probably were a secondary thing, maybe we're making mistakes. And so maybe one of the things we should look at, as well as the hierarchical modeling in terms of resolution, is also complexity and some of the details that we've missed out. The tides are the big, obvious elephant in the room. They're more energetic than anything else. And if it's nonlinear and you're energetic, probably it's doing something, but it's something that is decidedly underexplored in the climate community.
Thank you. Any other comments or suggestions or questions from early career scientists? Okay, go ahead. Introduce yourself first.
Hi, my name is Soo-kyung Yoon. I'm from Pacific Northwest National Lab. I'm mostly working with a regional model, which is called Salesi model, based on AFICOM. And I have a question related to the second. Since I'm working with a regional model, we do have quite good quality of temperature and salinity and water surface elevation observation data. And I would like to use it more than just evaluating our high resolution model. For example, data assimilation, like machine learning method, and I hope I can learn more about it during this workshop. But if there's any tips or feedbacks about when I jump into working on that part, I would like to hear more about it. Thank you.
Any direct answers, or but you can talk to people, I guess, throughout the workshop as well. Yeah, go ahead.
I'm Marco Reale from National Institute of Oceanography and Applied Geophysics in Italy. I was wondering about the second question, do we have the observation needed? I think we are confident in the way we initialize our model. So we have enough observation that allows us to initialize our ocean model in the right way. Because, for example, I'm talking about the Mediterranean region, okay, because my focus is on the Mediterranean Sea. Many times we have been suggested to use the reanalysis, but several times these reanalysis have several issues in the deep water, for example. So we are not sure about the direction of the deep water in the basin. We are not sure about the temperature and salinity data. So I think we don't have probably enough observation, for example, just for only initialize the model, not only for evaluate the model.
Yeah, I mean, do you want to say something? Go ahead, I can answer. Well, I mean, just last week, we were discussing at a meeting at GFDL with, again, US CLIVAR, value of Argo floats. As you know, they are trying to get funding for the next phase, and per year cost, including international, is $100 million. And so they're asking essentially, how do you use Argo floats beyond just initialization of models that are embedded in World Ocean Atlas, because Argo is in there also, and also just beyond comparisons? Do people use Argo floats, those data sets, for advancing process understanding within an ocean model and therefore leading to improved parameterizations? In addition to the reanalysis product usage of the Argo datasets, they are actually now about to publish a new Argo catalog. The resolution is 200 kilometers of the new Argo catalog. Is that useful information for us? What information do we want from Argo datasets? The core maintenance is 100 million. But if they want to go Argo with BGC, Argo with deep, below 2,000 meters all the way to 6,000, and Argo, what is it? There's another one. That is also another $100 million. Under ice. So they're at a crossroads right now. Should they discontinue some of the core aspects in favor of these additional capabilities, or should they essentially just continue with the core and don't bother with the under ice, BGC, or deep Argo? And so they're asking advocation from the modeling community, from us, sort of tell them how they, I mean, for data assimilation, you probably need Argo data sets below 2,000 meters, because to constrain AMOC, you need below AMOC. You need, or below that, and then you need probably the, for accurate pressure gradient calculations, you probably need coastal areas, which Argo floats have difficulties. Do you have the right temporal frequency with Argo? Can you use the raw data sets? These are all questions that they're asking us. Yes, I got the warning of 1 minute. So, I mean, that's what I guess I'm just providing information, but I mean, if you know of any work that used Argo data sets directly contributing to model improvement, I'm not saying that model comparisons to observations, those are routinely done, but any specific examples, that's the hard part that we are trying to figure out if there's any particular study. So please go ahead, yeah.
I mean, I would let someone else.
No, let's go ahead. You have the last word.
No pressure. Following on to something Bob said earlier about the hierarchy of models, I think it's also important to think as we go to higher resolution and we have more energetic models with more variability, thinking about not just doing like one high resolution model, but trying to get a better handle on the statistics of our high resolution models to understand whether we're seeing an improvement in the Gulf Stream position because of the self-attraction and loading, or if it's just random noise. And trying to keep that in mind as we go to these higher resolution, more variable, more energetic models, which I think are very valuable.
Maybe, okay, Bob has the last word.
So I'm coming at this from as an IPCC author, and we highlighted in the ocean special report that got kind of buried a bit, the importance of Argo for understanding not only how the ocean has varied. Before 2005, we had no clue how the ocean was varying. After 2005, we have pretty good statistics for the temperature, but also how mixing processes have changed, how the turbulence has potentially changed. And that's something that's just opening up. Work like Caitlin Whalen's work has been absolutely transformational in saying, we can't just treat mixing as some number that happens to fit our data. It is an evolving dynamic field, and that's something that is happening on global scales, i.e. you need an Argo-like coverage. It's happening over a large range of depths with different time scales. So that argues for the deeper range, it argues for the extension to high latitudes. without which we simply do not have an appreciation for all the ways that our planet is changing, and hence we will make bad choices in how to manage it. It's that simple.
Yeah, I should have mentioned Caitlin's work actually. So that's that's on the list that Argo has been used. Another thing that's actually Argo is quite useful is the determining the energy balance. And because we need those data sets, and as is, that's I think continuation of that thing. So those are actually two important aspects for Argo. Okay, so it's 12:01. Just a second. Yeah.
I'll stand up and. So we don't overload the cafe. We're gonna try and do a stagger for when we go. So I'm just gonna make a decision right now and say that this side of the room can go first. And this side of the room, and it's gonna change each day, so don't change where you're sitting. This side of room can go second, just wait about 10 minutes, maybe browse the posters, get a refresh of coffee, answer emails. And after about 10 minutes, then you're free to go to the cafe. 2 o'clock, we have 2 full hours for lunch. So lunchtime, work time, there's also some trails out there that don't stray far.
Is it safe to leave things in this room?
Is somebody going to be here?
I think.
The reason I'm saying that this is a public area.
Mm-hmm.
That's a concern. Don't leave things.
Yeah. All right.
So you know that Alan. Thanks for everything. Just we're going to be working a lot more on these formula.
Mic'd up. Good. Good. Okay, thank you everyone for getting back on time. We have a minute to spare. I just wanted to, Mommy. Just wanted to say, I hope you all enjoyed your little walk up the hill. And I know there's a lot of interest in going further. Just remember, you've only just arrived at this mile high altitude. So, take some caution when you go out there, because in fact, I don't think Bob's back. Where is he? I think he's halfway up a slope, stuck. Yeah, just a heads up. So it's my great pleasure. So this next session is going to be about machine learning for ocean modeling. And it's our great pleasure to have invited and introduced Lizzy Barnes. I'm sorry, I'm going to say, I said I would ask you, and we're going to use Lizzy Barnes. Lizzy Barnes, otherwise known as Libby, and who's going to tell us about what she's been doing in regards to some analysis of climate models and with machine learning. So we have a note taker for the discussion later this afternoon, which is Dhruv. So Dhruv has to stay awake. Okay, keep on board. And so remember, we have for the contributed talks 20 minutes, and as we found out this morning, it's not 20 minutes of talking, it's 16 plus 4 or 17 plus 3. So you can make sure you leave some time. And we have 35 minutes for our invited talk, and that will be 30 minutes plus 5, unless you want to have even more questions. Okay, thank you very much.
Okay, thank you, everybody. Can you hear me? Yes, I can. Okay, I've got thumbs on the way back. All right. So thank you. So I came all the way from Fort Collins, which is about 50 minutes or so north of here. And you'll see this is a new community generally for me. I'm more on the atmospheric side of things. And so today, I'm not here to tell you how the ocean works or ocean dynamics, but maybe give you a flavor for the type of work my group is thinking about in terms of how we can use machine learning, and especially the explainable part of AI to do sort of climate or earth system science in general. Okay, so that's the goal for today. I've been told that this is one of the first machine learning talks of the session, although there will be many. And so just as a big overview, I'm very much a physical scientist who uses machine learning as a tool in my toolbox. I think I'm going to come over here. Here we go. To do that science. And so in some ways we think about it as putting a lot of information about the noisy Earth in and getting something interesting out in the end. This is how we're using these tools. So why would you use machine learning? sometimes it's as easy as you're going to do something faster or cheaper that you already know how to do, but it's expensive. Maybe you want to do it better. You actually think that machine learning will help you, with a particular physical parameterization and improve it. Or you might want to learn something new. And you'll see in my group, sometimes this is the goal. The goal is not necessarily to do it better than we already can, or to do it faster and cheaper, but we want to learn about sources of predictability within the climate system. All right, so just machine learning is a tool with many different uses. And I just want to go over a few of my favorites. I'm not going to be talking about all of them today. But one way people are already using machine learning is just post-processing. We post-process data all the time. We've been doing it for as long as we could add numbers and talk about models, right? In terms of prediction of weather, climate, et cetera. And so here's an example predicting the errors of a forecast system. So not making the forecast itself, but predicting how wrong a forecast will be. Another example is improved parameterizations. There's a lot of work going on, and I'm sure many people in this room are part of that work. And this is something that's really exciting because we're already using in sort of empirical relationships in our models to try and account for small subgrid scale processes. Maybe machine learning and its nonlinear regression techniques can help. Another is combining disparate data streams, which I actually get really excited about. Yes, there's a cow in this image. I put the slide in there because it makes me smile. But also, I've worked with a graduate student at CSU that thinks about dairy production and wants to know on a given day how much milk, or in a given week, how many gallons, if you will, of milk will be made. Okay? And if you think about it, they know that the weather, the temperature, the humidity for these cows makes a difference. But how do you link those sort of physical values and physical variables all the way to a cow actually producing milk? There's biology, ecology, what the farmers are doing that day. There's so many complex things. And so in many ways, machine learning allows us to sidestep some of those complicated processes, or at least get around them empirically while we're still working on getting the right answers for the right reasons. And so what I mean by that is if you had to write down F equals ma to get all the way from the temperature to the gallon of milk, we would be stuck. We can't do that. And so machine learning is already allowing us to sort of cross the Earth system disciplines to talk to each other more easily than we were before. Another example is merging observations with model data. Data assimilation is very important and has a very rich history. Machine learning can help with this too. So you can imagine training a machine learning algorithm on climate model data and then just crossing your fingers and hoping it will work on the real world, of which you have a little data, and you test it out and see how it goes. And I'll show you some examples of that, crossing your fingers and hoping it works. And sometimes we get lucky and it does. But if you don't get lucky, or you already know, we have a lot of problems with our climate models. Actually, in most cases, I don't think it should work. All right, what do we do then? And what machine learning allows us to do with the way that it is trained is we can do most of the learning on climate model data that's imperfect but valuable, and then attempt to fine tune with the limited observations that we have. And in this way, we actually can try and get the best of both worlds, but ultimately the goal being to predict the observations, not just to predict our climate model output. Deep learning weather and climate emulators. I know Lorzana is going to be here tomorrow to talk about this. This is a big area right now, and things are coming out every week. A new paper just came out today for this, for weather forecasting specifically. And the idea here is just to replace the whole thing with AI from start to finish. They sometimes call this end-to-end forecasting. Okay, and we can talk about that later, but this is a big area of research. I'm not going to be presenting on this today, however. And again, you'll hear more about that tomorrow, I'm sure. And then I will say AI has played a big role in climate change communication. So it's really helpful for people to visualize what might my world look like under certain conditions. So this group uses different generative modeling techniques. You can type in your address in Google Maps and it will show you what it looks like on fire, underwater, or with bad air quality. So you can check that out if you really want to. All right. And then finally, learning new things. It's the idea that we can poke at our data and look at it in new ways. This is really what data analysis is, right? As we poke at our data, we poke at our numbers, we explore it to try to learn something new about the world that we live in. And so the AI is also useful for this, and I'll talk a bit about that today. Okay, so in my group, one of our goals is to develop and implement AI tools to leverage these imperfect but incredibly valuable climate models in support of Earth system prediction across time and space. My area of expertise is largely on the 2 weeks to a decade or two time scales. So, so thinking from sub-seasonal out to multi-year and decadal. And again, climate models, this group doesn't need to be told, they are not perfect representations, but wow, are they powerful? And so how do we make the best use out of that information and that data that we have? And how do we mine it, if you will, for the good stuff? All right, so I'm going to talk you through a few examples, starting at long time scales, thinking about climate change, and going to slightly shorter time scales for multi-year prediction. So that's the goal for today. All right, so we can talk about global warming. And this is an image from the IPCC report thinking about different thresholds. Now, these thresholds don't actually necessarily represent some tipping point of the climate system, but they've been used by policymakers to communicate certain thresholds being met as we move forward into the coming decades. But you'll see there's a bunch of question marks on the bottom, and those question marks, because we don't know when necessarily these different thresholds will be met. Right, so one of the questions is, when will the world hit 1.5 or 2, et cetera, et cetera? And there are many people working on this, and I'm just going to explore one way that we have attacked this problem. All right, so we can go, and first we can look at our climate model simulations and plot time series of temperature as a function of time under 3 different SSP scenarios. And the different colors are different climate models that are run, and the different dashed lines are those different thresholds that I just showed you. So the big point here is A, yes, they all, their SSP 370, they all hit the 2-degree threshold, but you can see that the width of that timing is very wide. And so if you use this straight out of the box, you would say we have a large uncertainty of when we might hit this 2-degree threshold. And same as going to the other SSPs as well. In some cases, some thresholds aren't even reached at all. Okay, so this is what my colleague and Noah Diffenbaugh and I attacked with some machine learning algorithms last year. Specifically, what we did is we took a bunch of CMIP6 output, specifically annual mean surface temperature. So imagine just a map like that of annual mean surface temperature for any given year in any of these models. So we have a lot of these. So we have lots of ensemble members, many different climate models, and we push it through a neural network, and we have it predict how many years until this world hits 2 degrees. From a forced response sense. So does that make sense? Okay, just how many years do we have? So it's a number, units of years. We do a bit more than that. We actually don't predict the actual year. We predict the parameters of a distribution. So we have some quantification of uncertainty. So specifically, we predict these 4 parameters of a distribution to give us, if you will, a Gaussian saying, hey, it might be 15 years plus or minus 3 is how we train it. All right, and we know there's uncertainties in this already. We already talked about those. From the climate model alone, we have uncertainties. So this is the setup, and we train. And here's the plot that people want to see, just how does it do? It does fine. It's not actually a terribly hard problem. The true number of years for our testing set is on the X, and on the Y is the predicted number of years. And what you want to see are the blue dots, those testing, those out-of-sample members that we did not train on. And we want to see it along the 1-to-1 line, and it looks pretty good, except when you get to really long numbers, and that's because we're back in the 1950s, 1960s, when the climate change signal is actually quite weak. So we expect that flattening on the far right. All right, so it works. That's not the interesting point. Honestly, nobody cares about me predicting when that climate model is going to hit some threshold, because you already knew it, because I already showed you in the plot before. Okay, the interesting part is, can this tell us anything about the real world, not the climate model world? So what we do is, once trained, we now cross our fingers and hope it works, because it hasn't seen observations yet, other than the fact that climate models are developed with observations in mind. And we put in annual mean temperature maps that we've observed over the past few decades, which we also have. So we put those in, and we ask how many years until we hit 2 degrees C. So first of all, you can do this using maps from many different years and end up with a prediction from 1980 all the way to present day for how many years until we hit, in this case, 2 degrees C. Now, a few things we're looking for. Each of these is its own prediction. So if this is complete trash, these numbers should jump around. The fact that they actually generally go down, give or take, by 1 year per year means that it might there might be something here. Okay, so that was the first good test. Secondly, you'll notice, I'm sure you're going, what about the bump? So that's Pinatubo erupting. And our training was we did not have enough data and enough representation of Pinatubo for the network to learn that that's just a volcanic eruption. So because of the cooling of the eruption, it saw the global mean temperature map and said, oh, we're further away from 2 degrees than we were the year before. Once the volcanic aerosols and their impacts go away, we go back sort of on track for this, about 1 degree per degree. So this is just giving us a little bit more trust in the output. So ultimately, we can go using these uncertainty predictions and ask, how many years, given the in this case, it was the 2023 map, how many years until we hit 2 degrees C? And we can actually come up with some predictions depending on which SSP we are on. And again, there are lots of examples of this already. One of the notable things about this particular approach, that is training on climate models and then actually making a prediction informed by the observations of the present day, which is what makes this interesting in my view, we end up with a result that we have a higher likelihood of reaching 2 degrees under this low SSP emission scenario, or low emission scenario than some previous assessments. Although our work doesn't rule it out, doesn't say there's a 0 chance. Okay. So that's one way to go about this. However, this was for the globe, and when the globe will hit these different thresholds. And so we continued this work, and this is very recent work, where we decided to do this once again, but regionally. So how many years until, say, I'm going to show you an example for Central North America, will hit different thresholds. Okay, and again, these thresholds aren't supposed to mean anything in particular, just different temperature values. Okay. Now, I already talked to you a little bit about transfer learning, which we just trained on climate model data and then predicted the observations. And again, you cross your fingers, hope it works. So what we do here is a little different. We're actually going to include the little bit of observations that we have in the past to try and update our network to be more applicable to the real world. That is, we're going to fine tune with the limited observations because this region has already, according to the way we've defined it, hit certain temperature thresholds already. So we can train on those and continue to update the model, the network here. And then we'll use that to predict observations. We do this for many different temperature thresholds. I'm not going into the architecture, which was really fun to design, so I can answer that during questions. But ultimately, what we can end up making is a time series based on predictions by the network. So let me walk you through this. We have year on the x-axis, temperature anomaly on the y. All the gray lines are the different CMIP models. So that's our sort of spread if we didn't have any other information. The blue is the base network that was trained just on climate models and just, again, cross your fingers, hope it works. And it looks okay, all right? But the black here is that Berkeley Earth observations. And by a little bit, and I mean a little bit of transfer learning, we're able to update our network to do a better job on the previous observations and thus predict out into the future. Okay, and from there we can then make statements about when this approach predicts we reach certain temperature thresholds. So one question is what did this transfer learning approach do? Why did the blue line shift that way? Right, there's a lot of whys here. Okay, and another question is, does this work in every region? So I'll come back to the first question. First, these are lots of different regions. You don't have to look at them all, but what are the big takeaways? First, the gray is the range we would have said from the CMIP6 model spread, if that's all we had. The blue is what we predict before transfer learning. And the orange is what we predict for the observations once we've actually done even more constraining with that transfer learning process. And a few things you see is that the orange becomes slightly more constrained and often earlier. Not always earlier, but often earlier in the time period. And the black is regions that have already hit that threshold. So if our predictions are any good, our PDFs should overlap the black dots at least a little bit. Okay. All right. But how did the network update its prediction? How did it do this? How did it go from the blue to the orange curve? It would certainly be nice if we knew which regions of the globe were most important for this update, because it might actually give us a hint about how the network is coming to its conclusion and tell us something about discrepancies between our climate models and our observations. So this is where explainable AI comes in. There's a lot of examples of it in the literature, and there are many papers now written for an Earth systems and Earth science audience. You don't have to go into the computer science realm if you don't want to read about these methods. And there are many different types of methods out there. I'm going to talk about an attribution type method. I really like these because they work with sort of maps in the way my brain works anyway. The idea is, imagine you're going to make a single prediction of how likely there's a cat in the image. The cat image goes through the network, and you say predict some probability of 0.8. So this is some prediction. Okay, we're not predicting cats. Wouldn't that be fun? But this is an example. So what we'd like to know is, where did that 0.8 come from? And attribution methods, again, there are many of them, but they typically bring that 0.8 back through the network and give you a heat map that looks a lot like your input, but tells you which part of the input were most important or gave the most in terms of this attribution metric to that 0.8. In this case, it's really boring. It says the place there's a cat told it that there was a cat, right? Like, we know this. But it's far more interesting if we start to think about the problem we posed earlier. All right. So why should you care about explainable AI? I think with this audience, I could just say, because you probably care about why, and then we could be done. But just in case, you need to convince somebody else, even if you don't care about why, and there are people who have told me, I don't care why, just give me the answer, they should still care about this. And the first reason is, how are you going to gauge your trust? I'd like to know the decision-making process, or at least a bit more information about how this decision is being made before I put all my eggs in that one basket. So that's number one. That's really important. Number two, to fine-tune and optimize. Maybe you learn that it wasn't using the cat at all, but it was using the boundary of the image to figure out if it was a cat. All right? Maybe somebody used a certain filter on their phone, right, to take all the cat images, and it goes, oh, this must be a cat. These are not reasons I want my machine learning to predict a cat, and maybe I'd go back and I'd change my algorithm. And finally, I want to learn new science. I want to learn something new, in this case, about cats. Okay, so here are a bunch of other reasons. So again, our ultimate goal, I want to be clear, is to understand causality. That's why I'm a scientist. This is not causality. I want to be very clear at all. It's not. But I do believe it's a step in the right direction. Okay. All right. Also, I will point out XAI has actually been quite a bit in the news and on Capitol Hill the last few years. People are actually talking about XAI at the national level. And so this is not going to become less important. All right. So we're back to this problem. What did our network do to go from the blue to the orange? What regions of the globe of these annual mean maps did it look at more or less? Well, we can make these attribution maps for the blue network, make them for the orange network, and then compare the two and see how it changed in how it made its prediction. And we get a map that looks something like this. So this is changes in that attribution heat map after transfer learning. And ultimately, what it starts to tell us is places that the network sort of unlearned or learned something different when it was doing the update with the observations. And in some of these cases, there are well-known issues with land atmosphere feedbacks that have been discussed. Sonia, on our paper, has talked a lot about those. And also this region, especially off the coast of Africa here in the Southern Ocean, has come up over and over and over again in a lot of the work that we do. And this is probably the audience to talk about with at a coffee break. Okay, so that's thinking about the forced response, right? Just the idea of how much will we warm over the next few decades. But there are other types of predictions we can do. So for example, if we live in one particular member, we're not going to live in the ensemble mean. We're going to live in one of these wiggles, right, of some large ensemble. Or we might live in this wiggle, which ends up doing something different. I had someone tell me the other day that I use wiggle every time I speak. So that is a check for that. I think we just got 2 of them. All right, here we go. So, oh, it just said, what does it say? Stop sharing screen? I don't know what happened. Okay, great. Thank you. Okay. Thank you. Okay. Oh, could you click back on the Fun. We need to click back on the slide or it won't let me advance. That's okay. There we go. Okay, so while global warming projections tell us things are getting hotter, we might be interested. Global warming projections are getting hotter, and we're using AI to better constrain future projections. So that's one example where we actually can initialize predictions and projections based on the world we live in today. But we might also be interested in multi-year predictions. So could we have foreseen this drop in this member, right? So this has a lot more to do with internal variability than the forced response to, say, aerosols or CO2 forcing. I will point out, not only will this kind of prediction, if we can do it ever, prepare for weather and climate hazards, but new work that our group as well as others are thinking about is anticipating the masking effects of climate policies. That is, if humans got their act together and actually went and did something, and then it was the hottest ever over the next 10 years because of some particular warmer internal state than others, it would be good to tell them that it's coming ahead of time. Otherwise, it might look like we don't know what we're talking about. All right, so this is more reason that we care about multi-year prediction. And so here are some examples of doing that. So we're going to predict ocean temperatures in the next 5 years. I will point out we're using past sea surface temperatures as our inputs, and I'm certain all of you could come up with better choices, right? For example, ocean heat content, I know, has a lot of information for predictability. The main reason is it's hard to get. So right now we're going to use SSTs, but absolutely moving forward, there are a lot better variables to use. So this is by Frances Davenport, a professor now at CSU, and we're going to predict the future sea surface temperatures over the next 5 years. So she does this. This was trained on 3,630 years of data from the MPI model. And then we're evaluating on testing data from that same model. And here's our overall accuracy. The way she set up the problem, we have a 33% chance of getting it right by random chance. It's either cold, average, or warm. So it's a classification task. And if you look at this, and it looks really yellow, which is about random chance, you're right. This looks terrible. This looks like we can't really say anything. However, this is when we look over all predictions. Instead, this network also outputs a certain amount of uncertainty, how certain it is about its prediction. And if we start to look at the predictions that the network is most confident in, we start to see that it's actually making skillful predictions. Specifically, if we look at the 40% most confident predictions, we do start to see skill. And if we look at the 20% most confident predictions, we see a lot of skill. That is, when the network thinks it knows what it's doing, it does a pretty good job. Okay? When it doesn't know, it sort of says, I don't know, and maybe we should ignore those predictions. All right, so this is training on a climate model, evaluating on a climate model. But again, what about the observations? So this is taking that same network and just applying it to the observations and seeing how it does. And the first thing I want to note is that looks like random chance on the far left when we look at all forecasts or all predictions. But when we look at the confident predictions, there is skill. Okay, and so again, suggesting that there's this state-dependent predictability in the system, especially in the network's ability to realize it. Okay, so that's for observations. She's done this now where she trained a different neural network on a bunch of different GCMs. So every GCM gets its own network. Okay, and then all of those networks go and make predictions on the same observational data set. And the question is, are there certain GCMs that are better for the network to learn from and apply to the observations than others? And if you look here, there are certainly differences. If you're looking for some baseline, the persistence baseline is in the upper right. So we have to at least do better than that at the lowest bar. And you can see certainly there are some regions that some models do better than others. Could part of this be random chance? Absolutely. We only have the one observational period, but this is at least apples to apples. And we can go and evaluate, especially in the tropical Atlantic, you'll see two particular models are better in their training and better in their observational accuracy. Okay, so what about XAI? Well, this is for a slightly different task, but we're still going to predict temperatures over the next 5 years. This is using the CSM2 model. And again, we're going to input lagged SST maps to give some sense of history of time tendency is really what it's doing, and predict the temperature over land in the coming 5 years. And when we do that, we can then go and make heat maps of the most relevant regions of the ocean for that land temperature prediction in the coming years. So these are 4 different heat maps for 4 different predictions over land. And we can see one that the same network here is able to learn different patterns and sources of predictability, right? But secondly, even for the same prediction, depending on what's going on in the climate system, it uses regions like the Kuroshio extension or the sort of PDO type horseshoe pattern, depending on the state of the climate system to make its predictions. So once again, this is how we're using this explainability technique to try and gain trust in our network. All right, so given the time, I'm going to pick and choose here, but that was work over the last few years, and explainable AI is very powerful, but has some problems. Mainly, it tells us where. Notice how I just pointed to plots on the places on the globe, but I didn't actually tell you how it's using that information. I just said, look at this part of the ocean, or look at that. So this is where a new phrase, sometimes known as interpretable AI, comes in. This is building AI models that explicitly incorporate the decision-making process into the algorithm. If you're familiar with a decision tree, that's often called interpretable AI because you can see every step, and as a human, I can understand it. I can understand a yes-no tree. The second you put a bunch of them together and make a random forest, I'm not so sure how interpretable that is, but the tree itself, I can follow. All right, so these are interpretable models by design. This is just showing how these heat maps, you can ask, well, how did you know it was a Siberian husky? Because I looked at the husky. And you go, wow, I trust you. And then you go, why did you think there was a tiny probability of it being a flute? And it goes, I looked at the husky. And you go, oh no, this may not be as great as I thought it was. Okay, so one of our big goals that I've been very excited about is working towards building AI models that mimic human scientific reasoning so I can better understand the process of decision-making from start to finish. And so I want to talk a little bit and then end here about talking about the method of analogs that's been around for a really long time. What is the method of analogs? There's no AI yet, by the way, if you're like, oh, I've heard of this before. This is just analogs, as Lorenz described it in 1969 here. Okay, so let's say we want to make a prediction, and this is what today looks like, this map at the top. We go into this big library of other maps, and we say, which maps look the most like that one? We say, oh, those two look a lot alike. Maybe those are potential analogs. And what we do is we look at how they progress in time. And the assumption is that however the climate evolved in those very similar like states might be a good prediction for how our world right now will also evolve. That's the argument. Okay, so let's say we want to use SSTs to predict the North Atlantic SSTs in the next 5 years. We can go and ask, well, how do these two maps look similar? And the one question is, how do we define similar? And the standard way is we just take the whole box and we take the mean squared error and we just look at how similar they are with that as a metric. But it feels like, why every box? Are they all important? Maybe some are more important than others. And so what we're only going to do here is use machine learning to help us know where to look when we compare these two maps. So I'm not going to, this is the network, we can talk about that later, but ultimately we end up with a mask that just tells us where to look when we take that mean squared error. Otherwise, there's no AI involved, okay? We're only using machine learning to use this mask. So here's an example. Let's say that on the left is today, and we want to make a prediction for the next 5 years over this box. And the right is actually the best analog over a suite, a large database of maps that we're looking at from climate model output. So you might say, well, the Atlantic actually looks pretty similar in these two, so that's why it was the best analog. But if you look in the Pacific, they're almost opposites. So the idea is we're not looking everywhere to choose what a good analog is. We're only looking where the mask is high, where it tells us to look. And in that case, these two maps look almost identical, which is why they were chosen as analogs. When we then just go and do standard analog forecasting, that is, we go in and look at this particular climate simulation and integrate it out and ask what happened over the North Atlantic during this time, we can actually make skillful predictions. Are they great? No. But so far, I think our bar is not random. All right. This is for testing on climate models, but we can also go into the observations and test and show that once again, even though there are many biases in climate models, we can still make predictions on the real world. And taking this further, we can actually interpret what's going on by investigating these different regions that pop out of the mask and taking them away and redoing the analog forecast to assess how important these regions are for the ultimate prediction, which is what we want to do, right? We want to understand the decision-making process. And these are just my final slides saying we're doing this also for climate projections. So this is a research scientist in my group, Martin Fernandez, that is using CMIP model projections to turn them into initialized predictions in the same way. And in fact, that we can constrain the CMIP6 range, initializing with observations, and then just using analog forecasts. So with that, I just want to point out, this is very exciting. You're going to hear about a lot from other people. Generative AI, I will say, in the next year is what we're going to hear about all the time. So a lot of exciting things happening there. How does climate change influence the performance of these AI models? That is a big unanswered question. And then again, thinking about AI for weather and climate model replacement is certainly a discussion. And with that, I will end. Thank you.
Okay, thank you very much. Questions for Libby? I have one, but ECRs first. You and I are not ECRs. Thank you. Right. Could you get the other mic? Okay.
Thanks, Libby. This was really interesting. I had a question about your SST forecast. You said that the network could judge whether its prediction was good or not. How does it do that?
Yeah, so there's a lot of different methods to do that. So in that specific example, where just using cross entropy is a loss, so it ends up giving, for better or worse, you can think of it as a scaled amount of uncertainty. And so whenever the network gives you a higher probability of a certain class, like it will be warm and it's at a 0.9, it means the other two might be 0.05, 0.05, and you might interpret that as a confident prediction. Whereas if it's, okay, now I'm going to have to do arithmetic to add to 1, 0.3, 0.45, and whatever the other number is to get to 1, then you might say, well, it made a guess, but it's not very certain. So that's how we're doing it there. However, earlier in the talk, I talked about actually making predictions of the parameters of a distribution. And in that case, we actually use the width of the predicted distribution. The wider the distribution, the less certain it is. We use that as our number to decide sort of what to consider and what to say it's not sure. Does that make sense? Okay. That doesn't mean it's reliable. To be clear, a ton of work has to go, is it reliable? Okay. The networks can spit out confidence all it wants, and they could still be wrong or useless. Yeah.
Great talk. You showed a lot of examples where you put specific reasoning for certain regions, for example.
Yeah.
In the morning, we talked how to bridge between the modeling and the observations.
Yeah.
Is that also a tool for something like experiment design to tell the colleagues where to look at, how to look at?
Yes, and there's now starting to be work too, sort of Aussie type experiments. So the idea of where would observations be the most useful to constrain X, Y, and Z, assuming your ocean model is good enough that you trust certain aspects of it, you can play with this the exact same way. So absolutely. Another argument is with the explainability side, saying, well, this is the region the network's using the most, looking at to make its prediction. Maybe we should go, get some more data there, or et cetera. I think I will say it's a lot more steps. I would not use a heat map and go, oh, let's spend $1 million to go take another measurement. There's still science required, but I do think it is one way to pinpoint important regions. Yeah.
Okay, I have a first question is, so when you say the model predicted parameter, parameters are number, not probability distribution. It's the deterministic, the model.
Yep.
And when you show that you use the LRP, layer-wise relevant.
LRP, I use many methods. Yeah.
Oh, okay, yeah, I was just wondering if you do a different method, if you take the same explainability.
Yeah, so the results I've shown you here are very robust to the XAI method. We have papers showing that they don't always agree. So to be clear, and that can be very confusing and bad. But in our cases, in the examples I've shown, I tend to use Shapley values myself. And also it predicts deterministic parameters, but then we use the loss function we use could be something like CRPS. We sometimes use negative log likelihood to train. And so in that sense, that distribution does have a meaning of a distribution, although the network itself, yes, is predicting the parameters of the parametric distribution.
I have a last questions. And how much do you think your results depend on the availability of how much data you give to the model?
So it depends on the problem. Some of these tasks are actually relatively easy in the sense that the signal and the noise separate. Making it even better would be very, very hard. In other cases, we have lots of examples of where we've tuned and taken the amount of data down to say 1,000 samples and then slowly ramped it up, and you can really see that information becomes important. So it depends on which example we're talking about.
Thank you.
Yeah.
Libby, thank you very much. That's a fabulous start to the session. Okay. Next up is Nicolas Ernout. You need to be mic'd up.
Okay. So, hello everyone. I'm Nicolas Ernout. I come from Toulouse in France. I begin my second years of my PhD, and I want to share to you some of the work I did during my first years of my PhD. I work with Lionel Renaud and Rachid Betsila at Lagos, and Ewan Simon and Xixing Sang at IRIT. And my thesis focuses on the use of a neural network for ocean atmosphere coupling. Return to the basics. Geophysical models reproduce a set of physical processes. However, in some cases, it's necessary to have a high resolution or to be coupled with another model to take into account certain processes. And the idea is using the machine learning to predict processes and improve the parameterization at ocean atmosphere interface for mesoscale ocean model. Two interaction affect this coupling at the mesoscale: the current feedback and the thermal feedback. The thermal feedback is the influence of the surface current on the surface stress. And the picture above explains why it's necessary to have a complete loop. The response is too strong. And the figure on the second figure explains why in the Gulf Stream case at the mesoscale, it's necessary to have a coupled model to the atmosphere model to consider the current feedback for transfer part of energy, kinetic energy from ocean to atmosphere. Second interaction, the thermal feedback is the influence of the sea surface temperature on the lowest layer of the atmosphere, and can be decomposed into thermal effects, where the temperature is correlated to the heat flux, and the kinetic effect, where the warmer the temperature, the stronger the magnitude of the stress, surface stress. So we have many ways to consider the current feedback and thermal feedback. through simulation coupled to an atmospheric model, but the cost is high. Just use a forced model if you don't need a feedback with the atmosphere. And you can use the forced model with parameterization for the current feedback to reproduce some effects, but we don't have thermal feedback to complete all the exchange. So we propose a new approach with use a forced model with a neural network like parameterization that reproduce the current feedback and the thermal feedback at mesoscale. Oops. So in the first step, and we have limited the variable to reproduce to the mesoscale anomalies of the surface stress, and you have considered the large scale variables from atmospheric parts and all that data furnished by the ocean model. First, we have just defined the data to learn, and we have tested a lot of neural network architecture. And after that, we have, after the validate the selected neural network, we have verified if the coupling effects are reproduced. So data, we have select the region where the energy is transferred from for the current feedback at the mesoscale is the most important on the Kuroshio and Agulhas currents for lining, and in red here, and then in green we have select the Gulf Stream for the validation. To verify this, verify the neural network can be transferred for other region. We have select two other region, in orange, the California coast and the Chile coast. For a variable, you have limited to current surface, UV, and the SST, and their mesoscale anomaly data with a prime. In blue for the oceanic variables, and for atmospheric variables, we have stress, magnitude of winds, and planetary boundary layer heights at a large scale, data with a bar. And so we have already said the output is the mesoscale anomaly of surface stress. And the data used is come from the pulsation project, is realistic mesoscale couplet simulation, NEMO, WRF, and OASIS. And to separate large scale and mesoscale, you use 1 degree Gaussian filter. So the first analysis of the data with a figure here, it's a table of the correlation, the table correlation table and the distribution. You have some correlation between inputs, but not between input and output, and justify the utilization of a neural network. So now I explain the context. I present the results, and first I want to talk of the convergence, where it's very fast at the top on the right, on the left. We have a loss and the epoch, and here we have 10 epochs, and it's just 50 minutes to learn a new architecture. So that's allowed to us test a lot of neural architecture, and I present just the selected neural network. So at the top right, we have the comparison of snapshots and we retrieve spatial coherence and intensity remains good. So we have checked another step time, and we have the same observation. For average, temporal average, you have same spatial structure, but with shifts, and you have a quite similar standard deviation. And when we plot the density distribution, we have good results, because here it's not a linear scale, but like logarithmic scale to see the spreads. If you use the linear scale, you see just an ellipse follows the identity line. So it's a encouraging result for the next. So to resume the neural network research, we have selected the neural network with the best error on Gulf Stream. The neural network have four hidden layer with a number of filter degrees, and the size of the filter increased 1 by 1 to 9 by 9. A good point is use spatial dimension in a neural network, but except this fact, we don't have find the logical to construct the neural network. So now we have a good neural network. We want to validate the coupling effect. So the coupling effect, we have used coupling coefficient, and the coupling coefficient is the slope between two variables. Here for the current track, we use ESTO. It's on a vertical, the surface stress curl, and the horizontal axis, the surface current curl. And in red, for the California coast, we see we have the same with from predict by neural network. And for the Gulf Stream, we have a little bit underestimate by the neural network. So it's a little bit because when we use on the whole map, and for each point we use you make the slope, we retrieve a similar map with some differences on east boundary upwelling system and Antarctic currents. And so we have a good result, and we have compared with parameterization as mentioned in introduction, and we have a similar result. So it's points, but for the thermal feedback, it's I present just STR. It's between sea surface temperature and surface stress magnitude, and we have a very similar map. It's a little bit lower for the prediction, but the error is very small. And we can compare because we don't have thermal feedback parameterization. Okay, so in conclusion. So we have good results. We can say we can use the neural network to reproduce the coupling effect and mesoscale for the ocean model, and the current feedback or the thermal feedback. It's like accuracy at some ocean dynamics that neural network don't learn. So we think to resolve this mistake by adding a new learning area. And what's next? Lot of things. Integration of influx to complete the exchange between ocean and atmosphere. And we have a lot of possibility of improvement like data augmentation, skip connection, physical constraints, or consider the time dimension. All results are presented is offline results. So we want to integrate neural network to see we have same performance of this solution. And thank you for your attention.
Thank you, Nicolas. Any questions? ECRs first. You're not an ECR, Bob. Nor are you. Anyone? Okay.
So thank you for that talk. That was interesting. I was just kind of curious to know, how were the fluxes actually calculated? Were they just taken from like the core routines, or yeah, the fluxes on which you were training them on? How were they calculated?
The influx?
Yeah.
I don't for the moment. I don't calculate it. It's the next step. I need to integrate this. So I don't.
Sorry. The stresses. Yeah, sorry. The momentum fluxes.
Yes.
Like, how were the momentum fluxes calculated? Were they from a bulk formula?
Yes.
Yeah. Okay. Yeah. Okay. So you're essentially training the neural network to replicate the bulk formulae?
No, just meridional superstress and the zonal superstress, and after that we calculate the curl. You have. Oops. We have two outputs, and for calculate the curl, you calculate the rotational.
Okay, so sorry. So maybe I'm misunderstood. You're not doing a point-by-point prediction. You're predicting the entire 2D momentum fluxes across each of those domains. Is that correct?
If I can clarify for you, he's filtering and he's looking at the eddy effect, the eddy coupling effect. So
the eddy coupling
A local
effect.
point-wise
Okay,
stress calculation is from the bulk formula, but when you average over it, there's a nonlinearity from the eddies.
Gotcha. Okay, that's the part that I was
Okay.
missing. All right, thank you.
Okay. Why that? Okay. Sorry.
So you've chosen a limited subset of ocean variables. There are other potentially relevant ones, some of which are present in the models but unobservable. Others are present in observations, but not necessarily in the model. So for instance, the ocean boundary layer depth might be the analog of what you've done on the atmospheric side, or the swell field might have a significant impact on the stresses. How extensible is this approach to incorporating new variables that may have one of these two problems? Either you can't observe it from space, or it's not present in the underlying model that you're training.
The variables are fixed on the beginning, and we have chosen just because we think it has an impact on the coupling. So it's why I said in the conclusion, maybe we add some new data or operation between data, and and for influx we need to add new data. I respond to the question, or?
He says, I guess. We'll take it offline afterwards. Okay. So thank you very much again, Nicolas. Next up, we have Iuri Gorenstein. Yeah, excellent.
slide, right?
So hi everyone, I'm Iuri. I'm a PhD student from Universidade de São Paulo, Brazil, and I'm going to present the ideas of my project mainly, which is how to model the ocean circulation using neural networks. So first I'm going to talk a little bit about the difference of my network and what's the core goal that I'm trying to achieve. Then I'm going to pass very quickly about how regional models work, how my network works, and then try to show you guys some very preliminary results. So, neural networks, they are models that fit high-dimensional curves and differential curves to data. So there has been some models already that were able to create long-term stable atmospheric and ocean circulation dynamics. Atmospheric and ocean circulation simulations. They mostly use the spherical Fourier neural operator. However, if you try to use those models and change the resolution they were trained in to make maybe more larger resolution simulations or of a specific domain, if you try to change the restraints to create a different simulation, you have to retrain the network, and they're very hard to understand how they're evolving the system, or they're not usually very explainable. And my idea is to train a neural network to integrate the discrete primitive equations the same way a regional model integrates them. In this way, we can use the same network to create multi-resolution simulations and apply them to any domain you might like to study specific parts of the domain. So first, I'll just talk very fast about how the ocean model works. The regional ocean model here that I use to train the network is CROCO, which is a model that has the same Fortran base code as ROMS. It's a split explicit two-step integration model. So first they have the barotropic integration. That's a two-dimensional field with the barotropic momentum and free sea surface height. That's called the fast step of the integration. We see here the equation. There is an intermediate step to integrating the zeta, which is the free surface, at times m present, the present -1 and present -2. The other Greek letters are just constants. And then the intermediate integration here. Intermediate step of the integration, which is the barotropic momentum here, is represented by u. And then the step 2 of the integration of the free sea surface, we have zeta at time m plus 1. That depends also on by default, the third order derivative in space of this nonlinear term. And tau here represents the discrete time. The barotropic integration, which is the fast step, it's usually some seconds. And then there is another intermediate integration step to integrate the momentum at the barotropic level. So that's called the fast step. Usually there are around 60 by default for each slow step, which is the baroclinic step, where the model evolves the baroclinic momentum and the other tracers. So how do we teach that to a neural network? The idea is the network will evolve each grid point the same way the regional model does. So we give to the network the different values of the, wait, I'm just skipping one slide here. So we're going to use the barotropic simulation to train the network. So the barotropic simulation, it has a equivalence for one barotropic step to one baroclinic step. It's not realistic. It's just to teach the network how the model evolves the dynamics. So we're using to train the network simulation from the South Atlantic circulation at low resolution, and then cross-validating the network with a high resolution domain to test if it will generalize to any ocean domain, just like we want. So to train the network, we're going to give them the input vectors that here represented by the x vector here at time t. So we will use the barotropic variables I discussed, the Corelli parameters, topography at present, past, and to past times, and the neighbor values until to give them the third order differential derivative that the model uses. So we're going to use the neighbors and the diagonal members at each grid cell point. And then we're going to use it to feed it into the network. The outputs of the network are going to be the barotropic sea surface height and the momentum. I'm going to show you guys the architecture of the network that I've chosen. So it's a pretty simple autoencoder. First, we enter the input, then layers we encode the data with 2 layers of encoders and to increase the dimension of our system. So we pass the system from state X, from a domain X to a system domain that's called Z here. We use a linear operator to evolve our system in time in this latent space that is higher dimensional space. That's also called the Koopman operator. It's basically a linear operator. And then we recover our system with the decoder. So we get the ocean domain we started with at time t+1. So just to remember once again, this is made for every point of any ocean domain, which can be evolved quickly if we just slice up the vectors and then pile them up. We can create a batch that will pass through the network, which will evolve the whole system and domain in parallel. And also, just a little detail here, we're going to train also we're going to train an operator that will evolve the system backwards in time also. So another linear operator that will go backwards, giving us 1 autoencoder, but 2 linear operators. How do we guarantee that the network does what I'm saying it's going to do? So we use here the squared error to train the network. This is the loss function that will be used. The first loss function appears is the identity loss. It's basically if you pass the inputs through the network and just encode and decode it without applying the linear operator, you're supposed to get the state back, your system, you recover your system. If you apply in the latent dimension, if you apply it in the latent space, the forward operator, the Koopman operator, you're supposed to get your system one step ahead. That's the second error. Then we have the backward error, which is analogous. Again here, x hat is the prevision and x is the actual state, the truth. And also we want the system to be consistent. So if we're getting a part of the loss function by multiplicating the 2 linear operators, we want them to be inverse. So the whole physics of the problem, it's consistent. Okay, so now I'm going to show you guys some results, which are very preliminary, but I trained a network that's pretty small with 1 GPU, and I trained it for 300 epochs. Took about 10 hours because the batches of training were pretty big. But this is a very small network compared with the networks that use, for example, the Fourier operator or the graph networks. They're way bigger. So here is the network encoding the system. This is the training data set, so the South Atlantic circulation system. We have on the right just passing the system through the encoder, and we see that it learns pretty fast for every point. In about 27 epochs, we achieve a very similar sea surface height. And this can be done with any ocean domain. It's the network has never seen any of these domains. This is the South Atlantic Circulation System at high resolution, so it never seen this resolution. The North Atlantic Circulation System or the West Pacific, it encodes well. And then evolving the dynamics, the problems start to arise. So here in the first line, we see the initial simulation state of the South Africa ocean, so the Benguela region. Also, this is the validation data set, so the network has not seen it during training. We see in the first line the truth value, then we have the neural network after applying 30 times the autoencoder, so just encoding and decoding the system 30 times in a row, and then the difference between them. We have the step 30 of this simulation, then applying from the initial state 30 times the encode, then advance forward in time, then decode, and then do it again 30 times in a row. We got already a lot of biases, and the state that our system arrives, it's not physical anymore. It's not that it's not stable, but it does not resemble the simulation we're trying to copy. And then we have the backward operator giving us basically the same biases. Here we have the loss functions. So we have on the x-axis the epochs of the epochs of training. On the y we have a loss function. For the black curves is the identity error that I showed some slides before. The blue curve is the forward error. The red curve is the backward error. And here we have the first column, for one application of the network, then for 5 steps, then for 30 steps, then for 60 steps. We see that the loss function for one step is it's not big. It has a small loss. However, it's stacking up as many times we apply the operator, mainly the forward and the backward operations. This is something pretty common that happens in neural networks. So one of the questions I had from this is the problem the dimension that I'm choosing the operator? So should I increase the dimension of the linear operator? Would this solve the problem? So just to check if it's the linear operator that's generating this stacking error, I train a pretty simple multilinear neural network, so just 3 layers of nonlinear activation network to do the same job of moving forward the system 30 steps. And we see this in the line, the top line. Oh, wait. Top line here. Pretty unbiased, much better than the linear operator. Which is good, but it's bad also. Because we want an explainable physics-informed network. And here we have the same plot I showed with the losses. The yellow curve is the loss from the nonlinear network. So it's 1 order of magnitude smaller. So if we allow the network to be nonlinear, it can pretty much embed the dynamics from the original model at ease with very few rounds of training and not very thoughtful architecture or guesses. So I know the results are not that. This is all just for the barotropic step. There's still the baroclinic step. And I know the results so far are not very breathtaking. However, if we can use the physics-informed architecture to train the network to simulate the barotropic step, we could analogously use it to evolve the baroclinic step and use furthermore reanalysis and observational data to improve the quality of the simulations that the network is able to do, making it more realistic simulations using this network. And more important, we are basically embedding the physics inside the linear operator in latent space. So we can learn about specific zones of eddy formation, for example, using this linear operator. We can decompose the system in eigenvectors and eigenvalues and retrieve some real physics from the neural network once it gets to the point that it is able to create realistic simulations. Thank you very much. That was all.
Thank you, Iuri. So questions for Iuri not from Steve first. An ECR, thank you.
Thank you. This was really interesting. If you apply your forward operator and then your backward operator, do you get back to your original solution? Were you able to show that?
No, because you see, the way you organize the input vector, it has to be smart enough to differentiate what you're inputting it. So the present is at one place, and then the past and the past minus 2. Remember that I showed it's strategically given to the network in a specific, and if you're trying to evolve the system backwards, you're replacing what's present and what's past, because it's going to go further, it's going to evolve the system. So it's probably a little different. I don't think you can just use both linear operators at the latent space, one after the other. I don't, but maybe. I'm not too sure.
Stephen Griffiths, thanks for the talk. I think I probably missed it, and I apologize after lunch. Is the goal to get a faster model? Is the goal to, what is the goal of?
The goal is to learn physics, but it is also fast. It's a very small network, and I've trained it all with one GPU. Right now, I can't say if it's faster than the original model, because I'm just doing the barotropic step. But the tests I did was with one GPU, it's very, very fast.
So if the goal is to learn physics, do you anticipate being able to learn more physics than just studying Croco?
Yeah, because I'm going to fine tune it with observational data, which at specific locations where Croco has difficulties in generating large eddies or mesoscale eddies. I hope to study that, yeah. But yeah, you can learn a lot also with the Croco model. Yeah. Sure.
So Bob Hallberg, GFDL. So you've demonstrated a nice ability of the barotropic solver to adjust to the density structure that's using to force it. But your barotropic model, or at least the barotropic model of Croco, also could propagate tsunamis. If you had an impact, it would radiate. Do you expect that your neural network would also be able to radiate kind of coherent tsunamis as a way of testing the high frequency dynamics of the barotropic
I hope that
solver?
I hope that the model does everything the Croco model does. That would be the main goal. It's just to find another way to evolve the dynamics the way Croco does. And I'm not sure if it won't be a problem if the model, if I try to make an unstable simulation using the network to generate an unstable simulation also. But
well, it's not unstable. It's forced linear propagation of a wavefront with a very distinctive pattern. And I suspect that if you would try it, the model will tell you unambiguously whether you have enough elements in your neural network to capture the radiation speed of information associated with the external gravity waves in your barotropic solver. So hopefully that might be another angle to help you figure out how to make a great model.
I see, yeah, thank you.
Okay, let's thank Iuri one more time. So I believe we now have a coffee break, and we are returning here. It's currently 3:15, and we're returning here at 3:45. 3:45. And could I just ask OMDP people to come here? And rather than sending me emails, I'd like to just ask you a question. So OMDP panel, including the emeriti.
Just go ahead and do your. Take that link. All right, this has a pointer on it. This might have fallen asleep. Okay, it just woke up. So it has a pointer. You can point it in any direction. And then the next slide and previous slide.
And I'll give you a 5-minute warning for the total, right? So 5 minutes includes questions. So when I say 5 minutes, you've got 5 minutes until the end of the whole session.
What are we running with a vertical resolution?
No.
That's why.
That makes sense. Like one of your very
Yeah.
He's going to be shoving stuff now.
Okay, welcome back, everyone. Let's have our seats. Yeah, my watch is a little slow, but okay. Thank you for coming back. So we have 2 more talks, and then we'll have a discussion for the midway through our machine learning sessions. So up next is Nabir Mamnun. Take it away.
Good afternoon, everyone. My name is Nabir Mamnun. I work at the Mercator Ocean in Toulouse, in France. But today I am presenting some results from my PhD, what I did at the Alfred Wegener Institute in Germany. And it's about the uncertainty in biogeochemical models. So, and in biogeochemical models, uncertainty problem is mainly the parameter estimation problem. And the ocean biogeochemical models we have include many parameters, usually several times more than the state variables. And the value of these parameters are not well known, or we cannot precisely measure the value of these parameters. And the uncertainty of the parameter value translate to the uncertainty in the model outputs. Usually, the available parameters come from the laboratory experiment or a limited field data, which is not actually in the context of the ocean. And in reality, the values of this parameter depends on the biogeochemical and physical context in different area of or different place and different season of the seasons. But in practice, we use uniform value all over the ocean and across the time. So the objective is to estimate spatially and temporally varying parameters in a global ocean biogeochemical model. So we use the regulated ecosystem model version 2, which is developed at the Alfred Wegener Institute. So in RACOM, so in the biogeochemical models, phytoplankton takes nutrient and sunlight, and they grow. So in RACOM, we have two groups of phytoplankton, nanophytoplankton and diatoms. Diatoms are easy so that they use silicate to build their shell, and rest in the RACOM is diatom. And the phytoplankton is consumed by zooplankton. In RACOM, we have only one zooplankton groups. In some models, both phytoplankton and zooplankton they have many groups. In some model, they have only one group. So there is no concrete agreement what is optimal. And when these both phytoplankton and zooplankton dies, they become detritus, and then they remineralize back to the CO2. So we get the build up. And in the numerical model, each of this arrow is translated to the equation with at least one parameters. So I would like to clarify that in this talk, with the terms parameters, I mean the model process parameters. For example, how quickly zooplankton eat phytoplanktons, like this. So we have many parameters, as I earlier said, and we don't know the value of these parameters, and they can vary, especially in different. So these models need a physical model to run for the ocean circulation and mixing, and we use MITGCM. So we set up a global configuration of MITGCM. In the right-hand side, we see the horizontal resolution of the model we built. So it's a Latlon CAP 90 model. We have higher resolution. Sorry, yeah. So in the high latitude, we have high resolution, and we have low resolution in the mid latitude, and in the equator, we have more or less fine resolution to capture the particle mixing in the equator. And the model have 50 particle layers, with the top layers is 10 meters, and the thickness of the layers increase with the depth to the bottom. So the available observation we have in global coverage is ocean color data or ocean color derived chlorophyll concentration. Here we use the ESA Climate Change Initiative ocean color data set, or the chlorophyll concentration. It's a 5 days composite data. So, and the data comes with the per pixel uncertainty information what we use during the data simulation process, the uncertainty. And we use an ensemble Kalman filter to estimate the parameters and the state. And we use the, in this study, we use 40-member ensemble, and the ensemble was generating by perturbing the model process parameter. That means we introduce all the uncertainty to the parameters of the model, and we assume that the uncertainty from the other sources is no uncertainty from the other sources. But we don't perturb all the parameters. We use selected parameters. So we select the parameters by a global sensitivity analysis in another study. So the selected parameters are the initial slope of photosynthesis radiance curve. That means how how efficient the phytoplankton is to use the light. So the parameter have for the both phytoplankton, and the another one, the next parameter is maximum photosynthesis rate. So if we have all the resources available, the phytoplankton can grow in the maximum rate. That is the maximum parameter rate, and it's also for the both phytoplankton group. And in the RECOM, the chlorophyll to nitrogen ratio is dynamic. So we selected also the maximum chlorophyll to nitrogen ratio. And chlorophyll degradation rate, the chlorophyll is degraded naturally, so but the rate we don't know. So we selected the rate, and it's very sensitive to the surface chlorophyll. And the another parameter we selected is maximum grazing rate. That is how quickly zooplankton eat phytoplankton. And with the data simulation, we updated or we update 8 state variables. So they are mainly the biomass content of nitrogen, carbon, and silicate in the both phytoplankton groups. So here we can see this is, yeah. So these 8 state variables we updated. And we implemented the data simulation in a open source software is PDA, Parallel Data Simulation Framework, which is freely available, and anyone can get the source code from the website, PDA website. And the experiment we conducted for 1 year. So we use multi-bearing or interannually bearing forcing. So we conducted the parameter for 2020. So here is in the left-hand side, we see the monthly mean of April surface chlorophyll concentration for the free run. Means we don't assimilate any data, but it's the ensemble mean for all this ensemble mean of the free run. And in the middle, we see the observation, the ocean color climate change initiative data set, and in the right, we see the joint estimation. So where we update both state and the parameter. So we can see is clear that in the pre-run we have actually the model is bad here or it's not optimal, but data assimilation improve the simulation significantly. So here it's look like how spatially bearing parameters look like. So it's the initial slope of photosynthesis irradiant curve for the nanoplankton. And if we can see that so here it was the bold value, it was the default value or initial value. And we can see that the value changes all over the ocean. And we check with the observation available in the literature and the spatial distribution of the parameter more or less agree with the observation. However, we can see that in the South Pacific and in the South Equatorial Atlantic, we have very high value, or in a sense, it can consider unrealistic value. Though here we don't have the light limitation, and the unrealistic value can come from the uncertainty derived by the other factor not in the parameters. So we estimate all the 9 parameters. We take the estimated specially parameter, and we allow the parameters very specially. We rerun the model. Oh, I have this. I have to. So here is we also monitor the temporal value of the parameters, how they evolve temporally in different locustes zone. So here is the spatial mean for the temporal zone, and we can see this from north to south. We do the temporal. We selected in the Atlantic, the zone in the Atlantic, and we can see that in the polar region, particularly the blue lines, it's very especially it makes sense because the parameter depends on the light limitation, and in different season we have different light limitation in the different areas, so they vary especially a lot. But in the mid latitude, we don't see much seasonal variation. And so we run the model, and here is the simulation from the 2017 to 2021, and we compare the model with observation through this Taylor diagram. If we see that when we give the parameters, the reference value uniform everywhere, we get the error is higher than the when we run the model with the spatially varying parameters. But we didn't apply actually the temporal variation in the model. We applied only the spatial varying parameters. And the correlation also improved a lot. We can see in the Taylor diagram. So the model run with the especially varying parameter is much closer to the observation than the default uniform value. So here we also compare with the net primary production. That is, so in the earlier, the chlorophyll is closer to the observation. It makes sense because we estimate chlorophyll, and we collect our parameters based on the chlorophyll. But how it's actually see to the other variables. So in the left column is the free run, is the uniform parameters, and in the middle is the net primary production estimated from satellite observation with the carbon-based model, and in the right, when we use our estimated parameter values with spatial varying. And we can see that like in the chlorophyll, we have the net primary production also in the uniform value. It's deviate a lot from the observation, but when we use when we use the estimated parameters, we get the spatial distribution much closer to the observation. Though I have to note that this observation also carbon-based model, and they also use some parameters that are not especially varying. So they also use the fixed parameters, and they also have bias. But the bottom line is that we go close to the observation. So I summarize my talk. We estimated 9 spatially varying parameters in a biogeochemical model by assimilating satellite ocean color data. in a global model. So in recommended couple model, and the dynamic range of a special bearing parameter value is agree more or less with the observation what is available in the literature, and the model when we run with the specially bearing estimated parameter, we get much closer to the observation, and we advocate to use especially bearing parameters for the biogeochemical modeling in a global or regional scale. Thank you.
Thank you, Nabir. Questions? I'll take Marco first. Don't mind.
Thank you very much for your very interesting talk. I was wondering, just a curiosity, did you also investigate if there are some significant changes in the vertical structure of the chlorophyll A, not only on the horizontal structure? Because I saw your comparison of the spatial distribution on horizontal scale, but did you also investigate changes in, for example, in the deep chlorophyll maximum? I'm just wondering. Because this is strongly dependent on the vertical mixing and light penetration in the water column. So
yeah, we actually haven't investigate the maximal chlorophyll depth, but we compared our when we done the special bearing parameter, we compare with some of the algo profile, and it's also closer to the observation, particularly in the Southern Ocean, but in North Atlantic or the polar region, like maybe I can, like this region, we actually see that in the mixed layer depth, the chlorophyll and the nutrient get bad.
Thank you. Thank you.
So these parameters you've estimated are varying in time. So if you want to make a prediction for the future, how do they vary in the future time? What do you do about that?
So yeah, in principle, in a changing climate, the values of the parameter will also change. But now I don't know, but we don't have any idea how can we estimate what we will have in the changing climate. But if we want to, the best we can do to estimate the temporal variation with a long-term simulation in the present day. But it's for the present day, and we have to use the present day values for the future. We have no way to estimate what will be the parameter in the future, because yeah, we don't have the. But I don't know. Maybe machine learning can help.
Probably. One quick question. Quick question, quick answer.
Thank you for the great presentation. I have a really quick question. So when you talked about parameters, you mostly mentioned about maximum variables like maximum photosynthesis rate or chlorophyll nutrient ratio. Is there a reason why you choose maximum rather than average or other statistic value?
So like the say for example photosynthesis rate. So photosynthesis rate depends on the use available resources it have. So the more resources, the more the nutrient, the more the photosynthesis rate. But in the maximum, it have a maximum value of the rate. So in the model, the equation is controlled by the maximum rate parameter that is the that control the equations, not the average rate or the rate. Yeah.
Okay, thank you very much, Nabir. One more time, thank you to Nabir. Fabricio? Oh, I can see you. Five minutes. Thank you. 5 minutes. Please questions. Okay, thank you. Hi, hello everyone. Thank you for being here. In sense of, my name is Fabricio. I work at the Max Planck Institute for Meteorology with Dr. Korn, and also we are in a big project with different institutes such as the Technical University of Hamburg with Dr. Jan Philipp Fries, Daniel Huprecht, and the DKRZ from also the Hamburg with Christopher Cadell and Dr. Maximilian Witte. In this, we are in this big project called Exa Ocean. So in this project, we aim to make the Icon Ocean runs faster on HPCs. And the idea is that we have two main branches. One, we deal with parallel in time discretization of the Icon Ocean. And the other branch, we deal with the machine learning part that I'm going to present here today. So basically, don't want to stay too much into it, but climate models have basically two most important components, which are the dynamical core and the subgrid parameterizations. Basically, the dynamical core is dealt with what can you resolve in the grid, and the parameterizations what you can resolve in the cells. Physically, the ocean itself has a very complex dynamics, and the energy is transferred across each different scale. So it's important that we can have at least some kind of estimative or resolve these different scales. So in a sense that to get more accurate simulations, we need a more high resolution models. Yeah, sorry, I forgot to mention this one because this is actually really interesting. This is from a source from Peter Korn. This is from Icon Ocean. And as you can see, as I said, the complex dynamics allows for many different eddies and phenomena to go into these cells. So to actually be able to have a bigger improvement of these climate projections, we need a more high resolution of these models. But this, in effect, has a bigger cost. So how can we actually reduce this cost of having more accurate models? And machine learning could be one of the solutions, as mentioned in a lot of the previous talks. It has many different applications, such as the parameterizations and also the physics informs. Also, we have one of slightly different approach that I'm going to present is called super resolution. This methodology is based on many different kind of technologies from the machine learning, such as convolution neural networks, general adversarial networks, and diffusion models. Here I'm going to go with the convolution neural networks. And these convolution neural networks were previously applied on what was called image inpainting. And the idea goes that if I mask these images and I ask for the machine learning, okay, what's supposed to be in these white spots? And he will give me an answer. And then the way that we can do this is that if we have, this is from one of our results, early results this is a temperature from the ground truths of 500 meters on the North Atlantic. This downscaling just means that downscaling in this size of the size of the image, not on the feature itself. So it decreased it to 10 kilometers and used machine learning to go back
to the 500 meters. And as you can see, using this technology of the imaging paging, we get some really nice results. We can definitely get, I mean, sorry if the image is a bit blurry, but we can kind of still manage to get a lot of the effects of the submassive scale. And so given this, can we aim to aid numerical models to simulate a low resolution model and correct it with the machine learning trained on a high resolution? That's basically our objective, that we have run an ICONO simulation model on a coarse mesh and correct it using this trained with the high resolution approach. So here I'm going to make a caveat that I'm not dealing with the full 3D case. Here I'm going to show a preliminary result using the shallow water part of the Icon Ocean. So to state briefly what is the Icon Ocean, the Icon Ocean dynamical core is based on this triangular spherical grid, as you can see here. It's a finite volume on C grids, and it also, I think Peter already mentioned that it's based on what is called the emission reconstructions. And it's really important that it kind of diminishes a lot of the grid noise of the divergence, as he previously mentioned. The Icon Ocean solves the invariant form of the equations. And for those of you who haven't heard much of this, is just taking this advective part here and changing to a product of the kinetic, the gradient of the kinetic energy and the absolute, and the product of the tangential velocity and the absolute vorticity. And to train, and our condition that we're going to test in the shallow water is based on the Galevsky test case. This is a geostrophic jet at the North Hemisphere. As I said, this is a shallow water, so aquaplanet, so we don't really have land, so basically go all across the sphere. This is a zonal jet, and we add a small perturbation in this jet so that it unstabilizes and creates a lot of different meanderings and eddies in it. It has a maximum velocity of 80 meters per second, so this is kind of more of an atmospheric initial conditions, but the dynamics itself is still present in the ocean in different scale. So the way that we did this is that we took two grids, one with 20 kilometers and one with 2.5 kilometers. We ran the 20 kilometers for 10 days. This is 8, this is a typo, for 10 days. And then when we run we take the low resolution, we take like one of the snapshots of the high resolution, we interpolate it to the low resolution, integrate it for 12 hours, and we take the difference between the high and the low resolution for this 12 hours difference. And this difference is what we fed into the machine learning and said, okay, so this is what is supposed to be, and this is what we get from the low resolution. So these are based on 12 hours integrating time. We only corrected the velocity fields, and the initial conditions, what we used for, we take this jet and shift it 5 degrees north, 5 degrees south, and maintain it to what's supposed to be. Also, the perturbation, we changed 8 different perturbations in my sphere, so that we have in total 23 different conditions. 22 of those we trained on the machine learning, and the one which is the proper Galevsky, we actually use to use the machine learning. So the couple run, what we did is at each 12 hours, we pick up the snapshot of the low resolution, gave to the machine learning, okay, so now you know what is supposed to be, so give me what I want to know about the high resolution information about this low resolution. And so it gives me, and then I assimilate it back to the low resolution and keep running for another 12 hours and do it again. So the neural network that we're going to use is called a UNet core. This UNet is a convolution neural network. The idea is that these mainly UNet was created for biomedical imagery. So it's that it takes a cell and try to get like the boundaries of the cell. The main idea of this is that it kind of get the features right of an image. So that's what it was developed for. Here we change slightly as we do not want to classify our feature, but we want to just get the specific value. So basically a bunch of convolutions that decrease the images into small features and then increase again and get our result. The problem of the UNet is that a convolution can only be done in a regular grid, which icon is not. So we have to interpolate it to a regular grid, put it in a UNet core, get the sampling, interpolate it back into icon. You already can see that this may cause a problem to these multiple interpolations. But that's how unfortunately we had to deal with. So how we did this simulation back, we just used nearest neighbors for simulating back to the coarse resolution. Our loss functions is basically an absolute loss functions between the velocities. So it's just L2, and then we used a regularization term here that minimizes this L relative here. So my results is that we have here, this is the top figure is the U. Here's the velocity, the zonal velocity, the meridional velocity, and the sea surface height. The dashed line is the error of the 20 kilometers. Oh, sorry, the dotted line is the 20 kilometer error. The dashed line is the 10 kilometer error. The red line is our coupled run, like when running the model. And the blue line is what we call the optimal solution. So what's the most that we can get of this technology? So it's just taking each snapshot of the high resolution and do that approach of going back to the 20 kilometers and back to the 2.5, going to the 20 kilometers and getting to the 2.5 of the high resolution. And as you can see that initially we have like a increase of the error. We get a low, we have a worsen of the error going back to the 20 kilometers. But as we get close to the instability, the error decreases and we reach like the same accuracy of the 10 kilometers for both the U, the V, and even the sea surface height. We were not changing. We did not change the sea surface height. We just changed the velocities. And this was, we got this also like the effect on the height. But anyway, we have this like blue line that we see that there's like room for improvement. We see that we can still achieve better in this one. And this is just a run, a 12-hour run was done in the 10 kilometers, it took 63 seconds, the coupled run 55, and the 20 kilometers 31. So we still are faster than running the 10 kilometers. So it's still like better to use our coupled run than only the 10 kilometers. This is the vorticity on the day 7, where we starting to get this instability going. This is the 2.5. This is what we want to achieve. This is the 20 kilometers. So as you can see here, where the 2.5 is less unstable, it has a higher instability here. So this is because this test case is actually very difficult, because the grid is very unstructured, this grid. So even the noise of the grid can trigger the instabilities. This is the 10. Ooh, this is the 10. It kind of gets better. This stability is more stable. And this is our approach. So we get more close to this 10 kilometers, and we can kind of solve this spurious instability of the grid. But a problem of it is that we have here, you can see that has a bit of noise. There's some small scale waves present in our simulation. 5 minutes? 4 minutes, okay, thank you. This is, so going to our energy conservation. By the way, icon itself is energy conserving, but we did not use the energy conserving part to save in time costs. So the 10 and 20 kilometer run, as you can see, they decrease in the kinetic energy conservation. But as you can see, this doesn't matter because our couple run actually violates this energy conservation slightly more. But as you can see, it does not grow indefinitely. It reaches a point that is large, then it decreases again. Unfortunately, it did not go further than that. We stopped on this. We don't know what's going to happen more in the future. The potential energy is not changed because we did not change the height on the machine learning. We did not get we did not get any difference on the machine learning part on this potential energy. When we look at the spectral energy, and the spectral energy that I did was on the spherical harmonics, because it's an aqua planet, it's easier to deal with this. As you can see, the machine learning can get the small scale, the large scales correctly on these kinetic energy, but going close to the small scales, it just has a slightly more complicated part because of this noise that we observe. We have like a similar thing with the entropy, but it does not seem to be very impactful on the entropy part. It's more problematic on the kinetic energy, but as I showed you before, this does not grow, and we see that a lot of this energy that is being inputted in my system is mostly in the small scales. Is that noise that you see on my domain. So in summary, just to be quick about it, our ML methodology shows potential to increase the accuracy of the grid. The use of this CNN, probably due to having to interpolate the regular grid, provides some spurious in the system, or because of the training, or because of the use of the velocities. I don't know, maybe this can be changed. Maybe we probably can mitigate these noises with lower filters in this in the result of the machine learning, or maybe we can use ML transformer network, which we're now changed for the more accurate ocean. So we're kind of trying to investigate if transformers are better. There's also the question if we should not correct for the velocity, if we should correct for the vorticity, and we should correct for the sea surface height, which like may be better, maybe not, I'm not too sure. Also, the assimilation could be like an issue. As I said, hopefully I said, I don't remember what I said. What we do is that we take the velocity of the high resolution of the ML and substitute back into the low resolution. So we just change the values. So doing a proper assimilation, like using nudging, may be better. I don't know. This also is being investigated. So that's basically part of our future work. Maybe investigate different frequencies of simulation and apply these results in the 3D. And just to show you the 3D, this is what we want to get. And this is just getting these small scale eddies would be like really nice. So hopefully one day I can be here and be like Dr. Chouksey just before me said, which one is the machine learning and which one is the case. Thank you very much.
Thank you, Fabricio. I see a question. We have time for one.
I think it's very quick. I was wondering, thank you for the talk. I was wondering, yeah, so here you're considering the spatial resolution, and I think that's usually what people are concerned with. But there's also the spatial resolution, like if you change the time step, it's probably going to change a bit the simulation. I wonder if you've been wondering about these kinds of things, or I don't know how it's possible, or yeah, but yeah.
So can you be like more clear in the sense that if I change the time step of the model, like doing the simulation, you mean?
Yep. Like
I investigated. So what we did, we investigated these accuracies that we did. We investigated using a cursor, because the idea is that when we compared these high to low resolutions, and we did it as 12 hours, we had to limit our time step of the 20 kilometer that fits the 2.5. So it's kind of doing, we just did it in a very slow time step, just it's the same as the 2.5. But as we changed the 20 kilometers time step to the limit of the CFL condition, we did not see any changes in our result. So we did get like nice accuracies despite being like a lower, higher time stepping.
Okay, in the interest of time, we have to get on because we have a shorter discussion session mid-vote. So
sorry for taking.
That's all right.
Thank you.
My watch was running a bit slow. But... Okay, so let's thank Fabricio one more time, and we're going to get the questions up. And Dhruv, could you just wave your hand? So this is Dhruv Paval. He's volunteered to be our note taker for this discussion. So hopefully he'll be typing away rapidly. Yes. Yeah. Okay. So we've got a few, actually, I think we've got quite a lot of questions on this one. So, but I think we'll try and focus on the ones which are most relevant to what we've just heard. We've heard a very nice overview of how we could apply machine learning in many different ways. We've seen examples of parameterization, and it wasn't machine learning for the parameter estimation, but so there's a lot of general questions, and I don't think I'm going to read through them. I think what we should do is see if anyone's willing to have a quick look and start a discussion. And if not, I know what I would like to ask. You don't want to hear my questions, so. And in fact, even the speakers can start up if the speakers want to sort of say talk to some of these big issues. Any questions? Thank you, Andrew.
Yeah, so I mentioned to Steve that I'm a little bit of a self-hating AI and ML research scientist, but because I have a lot of skepticism about how ML is used, skepticism how we do it. But I think one of the things that is really interesting about machine learning, right, is that it is an excellent way to brute force a solution to a problem. And I think even just taking that idea, right, like, is this problem solvable? Can we do something like what you just presented? And if we had knowledge of an algorithm that can map from a higher resolution, like a low resolution, understand what the impact of those terms are and map it back down, what you've kind of shown is that there is such a mapping that does exist. It's way complicated because it's a machine learning network, which has no idea of math or physics, but it's a solvable problem, it seems like, for under some situations. And I think even just having that as a direction helps filter out some of the things in the harebrained schemes of things that we might think about.
Any responses? Responding?
Yeah, maybe a response directly to that. In addition to the brute force, I think it's very important that we do physically consistent energy conserving schemes, first of all, to gain trust and to learn about reality.
I think trust is an important word. Yeah.
Yeah, so this is something we get asked a lot is, what conservation principles are in your loss? Like, are you conserving X, Y, and Z? And at least at the scales that I work on, there's almost nothing to mass. But really, many of our climate models don't conserve many of the things we consider important, and we still find them useful. And one of the challenges that for this is we want physics to be in there. We'd love it to be learning all the right things for the right reasons. How do we do that? And originally it was just put in a loss and you're fine. And now we're realizing it's more complicated than that. And one of the pieces, at least from my experience working with climate modelers, many of them are you, but also analyzing the data, is it's about the emergent behavior within the system that we end up building the trust. Because you can conserve mass, momentum, et cetera, and still end up with wonky climates that actually have no bearing on reality. And because of that, how do we assess whether these machine or data-driven models are actually have the emergent behavior that we want? And that is really tricky. And at least my understanding thus far is it takes a lot of humans staring at a lot of plots going, "Ooh, I see the jet doing what I think it should do," or "That looks like the NAO," or "That looks like a pretty good ENSO." And how do we make sure that's working? And I don't actually, I don't have an answer. So just building off of that, I think that's why it gets even more complicated.
Steve?
Yeah, Stephen Griffiths, just thanks for that, Libby, because it kind of was what I wanted to say. I think that brute forcing an answer is a good thing to think about, but is it an answer that corresponds to the laws of nature? And that's something that we really need to be concerned about as well. Just because you have an answer doesn't mean it's a physically relevant answer.
Okay. I think we're missing metrics that are correct. So, right, if you do numerical modeling, you kind of rely on that the numerics are right. You can prove that they're right, and so you have your tests and so on. But if you now replace some of your subgroup scale, like if you basically introduce new parameterizations by modeling smaller scales to machine learning, then you be lacking assessment skill in the quality of the model. Right? If you're lucky, you look at energy cascades, and they should be correct. But there's more equations in the system. Right? You somehow have to have better standardized metrics to see if your flow is correct.
Any responses? So with those metrics, would we actually, if we design some metrics and we were able to make those metrics come down to kind of 0 errors, would we trust the models at that point? Would that be enough? I'll answer my own question. That's essentially what goes into the loss function, and people can make loss functions fit really well, but they can still do very badly. That's the outer sample problem, for example. So getting a nod here from Libby. Another question from Bob.
Robert Hallberg, machine learning novice. So one of the things we often try to build into physics-based parameterizations is the negative feedbacks, the aspects that work to regulate the system. And one of the things that scares us if somebody suggests a physical parameterization that drives the model out of balance without something else to keep it in a physically sensible state. Is there an equivalent approach in machine learning looking at the response of the system as a whole when you perturb it, how it comes back into a new and sensible equilibrium in response to perturbations?
I saw an example of that today. So, no, I was going to say, two examples.
Yeah, so there are a lot of ways. So first of all, there's just the exploding model problem, which ultimately is just, in general, you have some feedback that takes off. And so this was originally what I think caused a few years ago for everybody to talk about weather, but nobody wanted to go beyond about 10 days or the thing exploded. And there have been some tricks to try to get beyond that. But I think in the one way that people have been approaching this is losses that don't just care about the next time step, but care about something far beyond, some quantities and metrics that actually matter, that are going to take many, many time steps to get to, and making sure you simulate that as well. And some of those algorithms, you think about like winning a chess game, and the AI is trained to win games. And if you think about it, it's not being trained just to do a single step at a time, but it actually is being trained to optimize, to actually get to the end. And so in that way, there are, at least from the ML perspective, this more CS side, but there are ways to start to make sure that we can incorporate that into the training process, rather than, again, I've said it 17 times, but rather than just hope it works, right? Which is not that doesn't make me feel very comfortable.
Can I add to that before Andrew? There's also been work talking about making sure that the machine learning is reflecting the symmetries of the system. Rose, you, for example, done a lot of work on this. And so just building the physical properties of they call it about physics-informed networks, but that has lots of multiple meanings now, so it's confusing. But there's people who have been making sure that they actually do work in the flux form or in the symmetric form. And when you start doing that, things get better. So there's the long rollout problem, and then there's the actually making sure that the model doesn't violate any of the laws we do know. Andrew.
Yeah, I was going to follow on with what Libby was saying, right? I mean, like the whole idea of the reinforcement learning, right, is to penalize on behavior or reward on behavior of a system, right? So you can even think about it like a classic numerical analysis problem, right, where you look at the eigenvalues and do they grow? Do the known factors of eigenvalues grow or not over time, right? And that's very difficult to just do when you're thinking about, oh, okay, it's just a standard regression model, right? But if you put it on a reinforced learning context, you can observe like, okay, do these modes grow in time? Do these modes decay in time? You know, do they decay with an appropriate rate that I want you to decay at? And we've seen in CFD simulations where they actually train turbulence parameterizations, like, you know, to try to do something Smagorinsky-like, that they end up doing really, really well when you train them kind of in situ, right? Because it's like they're modifying the system, they're doing something, be rewarded on the kinetic energy spectrum that's taken over thousands of time steps and done that way. And so whether, again, to get to the question, you're brute forcing an answer, you improve the performance of the accuracy of the simulation, but why is completely different. But there are some really interesting kind of applications of that. So you penalize in behavior and not just on the direct quantity of prediction.
Can I ask a question too? How are the machine learning techniques doing in representation of emerging properties of the climate system?
Yeah. So I guess there are some models that the goal is to reproduce the statistics that emerge from the mean state of the systems. There are some neural networks that are able to generate simulations that have those properties, mainly the spherical Fourier neural operators. They are able to do very long-term stable simulations. The question he made it before, oh, that's better. The question he made before about whether they have equilibrium states and if you perturb it in a non-physical way, if it's going to stabilize at some equilibrium states. I have not seen any studies about it, like to search for those equilibrium states. And I guess that the main discussion also, it touches 2 points, that there are networks that have very high, a very high number of parameters that they are able to fit into generating a satisfying answer. However, these are not physically based. So you're achieving an answer because you're creating a gigantic polynomial representation of the data you're using to train these connections, these parameters. And it can be very useful to do that. But there is also the other need to represent the system with physical laws. And there are other networks that you can use for this objective. So it's two problems that are not fighting each other. They are both valid for study and to implement weather simulations or climate simulations.
Follow up on that. Are there any like studies looking into, say, AMOC stability with neural networks? Because that's a hot topic right now. And can it be trained to determine, rather than creating all these hysteresis loops for simulations, is there any work on that?
I know the group in Copenhagen in the Niels Bohr Institute. They are doing that actually. I think they are writing a paper, which is not yet submitted, but it's new work using machine learning. I think I forgot what the tool was specifically, but it was looking at AMOC.
Okay, I mean, so one thing that I've been thinking about when it comes to machine learning and a framework through which I read machine learning papers is thinking about the locality of the physics and, you know, so making climate predictions on different timescales. So for example, if you're only predicting things on a timescale of days and you're in the interior of the ocean, it shouldn't actually matter what information you have from a long way away. And I read a lot of papers where it seems like information is being incorporated and used about the situation in a different part of the ocean to make predictions here. And that shows to me that, right, that machine learning model is not actually doing, it's not representing the physics, it's representing some statistics of what the climate is like. I wondered if other people had thought about this, or like, how do we, is this a useful framework for thinking about the problem?
Any takers?
Yeah, I mean, I think it's kind of interesting, right? Because I mean, what Libby showed in a lot of those kind of sensitivity maps, like where does the predictability come from? You know, our brains kind of map some of those things onto known modes of climate variability, known teleconnections, right? So I think the question that you're asking is like, what if a machine learning model shows us a completely different pattern? It is difficult to falsify that, right? Because it is apparently making a prediction, or it has predictive power. Like for some reason, this cell in the Southern Ocean really correlates well to Colorado, but that's where the scientist still needs to step in, right? Is it how do you falsify? We consider that a hypothesis, right? Like we hypothesize at this point in the Southern Ocean correlates with Boulder. Can we falsify that hypothesis in some way? Because a priori, right, like it's just another hypothesis. So I think that that's one of the interesting questions is like, when will we come up with something that we don't understand and that we can kind of back out the solution from that? Or is it just kind of we take it on faith, you know, that sure, this one point correlates really well.
Going to hear me again, but okay, so a few thoughts. So one thing with the locality, I think, is a great example of the types of test cases that as dynamicists we've been running for a long time with our simple models. And I think this is a great example of making sure information doesn't travel faster than it should in the model. And that type of test case, I think, would be a great thing to add to some repertoire of a long list of dynamical test cases that people need to do before they've sort of put their model out into the world. So in my view, you're absolutely right. What you're looking for there is causality, not predictive power, because it could be it's super helpful for the prediction. And you know, if it's a understanding climate model biases, it really is helpful to know that the Southern Ocean tells you that the Colorado is going to be wrong. It turns out because the same person that wrote some parameterization in one part of the Southern Ocean also was someone that messed with the Colorado something or other, right? Like these are possible and they can be predictive, but they're not causal in the physical sense you're talking about. So I do think that's a great example. And there's a there is a small group of people that are starting to try to push these sorts of test cases that come from sort of that fundamental dynamic side and put them in a way and in a language into papers that the machine learning and CS community can understand so that they're held to that same bar and not just sitting around and waiting for, say, a physical scientist to do that test. And I think that's a great example. So I just wanted to say no, it shouldn't do that, right? On a 7-day time scale, that should not be helpful from a causal perspective. And then I was just, since I have the mic, I was going to offer to go to number 3. I was going to say, yes, I do think already there are examples of finding features that we didn't expect. And in some cases, there's a graduate student I've worked with who then puts that region and nudges it in a dynamical model to see if you can get a dynamical response from that, from the place that, say, XAI pointed him to, and it worked, which was amazing. So there are ways we can have the two work together to do sort of experimental causal tests. And the other thing, at least for me, oh, sorry, it was number 2 I'm excited about. I'm excited about all of them, but and there are folks here that are, I'm sure, more in the DA, so the data assimilation side than I am. But it seems to me that these tools are going to open a lot of doors for how we integrate the observations into the sorts of big, massive climate models that we're using to date. Because right now, it's really, really hard. And what you do is more turn knobs to try to make it look like the obs, but you're not necessarily ingesting them. And I do think that these tools are going to allow us to do it in different ways. And when I talk to my DA friends, they're like, oh, machine learning, we've been doing that for decades. So maybe it's not even that new anyway.
Peter.
So I wanted to ask what you think trustworthy data is. If we run a global ocean model at 10 kilometers, it's often called eddy resolving. But if we ran it at 1 kilometer, we would get a different solution and we get 100 times more data. So how do you define what is the truth? In the last talk, they said the truth was 2.5 kilometer resolution, but if they'd run it at 1, it would have been a different solution. So how do you define what is the truth that you're after?
And Peter was looking at me when he was asking that question. I don't know why. I do have a comment on it. In fact, Libby wasn't here for it, but I mean, there was a discussion in the last discussion session, the issue of Argo and Argo not being funded going away is a critical issue regards this question. There is not enough data about the real ocean already, and that we're facing a world where we may have even less unless something's changed. But that Argo data set is probably one of the most valuable things when it comes to actually learning about the real ocean. And using that data in the way that Libby just described with our best models is perhaps the only way we're going to be able to start having some trust. We'll be using the models, of course, in the DA world to fill in, but I think that's the best we'll be able to do. And so I think that strategy is something we have to be aiming for. That's my answer to that question. Whether we trust any of those data sets, I think we have to be realistic. There's always going to be uncertainties in the data itself, even if it's observational data, and even if it's high resolution model data. I agree with that. But I think that it's, we can't carry on without either of those. We have those are the only kinds of data we have. So we have to make progress with what we have.
Get nervous talking about machine learning. This question of truth, right? It kind of depends on the question you're asking. And I was thinking about it even with the first discussion session about how do we want to improve ocean models? What is our why? Why do we want to do this now? Why do we want to keep going to higher resolution? Or why do we want to, what are we really trying to improve? Are we trying to improve climate projections or fisheries or, I don't know. I guess what's our why sometimes?
Yeah, we are getting philosophical, aren't we? Does anyone want to answer the philosophical question?
Okay,
yeah.
No, I'm not answering. I wanted to say a similar thing, right? So we can verify with Argo, but Argo is an integrator over several timescales, where it gives you some mixed layer depth. But our models now give us resolution-dependent answers about how variable the mesoscale or sub-mesoscale is. And then it's very hard actually to verify which model is more correct than the other then, because you never really get the global data for doing that, or you hope for the right satellite to fly, right? But then the question is, does it actually matter if your high resolution or if your small scale variability is correct or not, as long as it gives you the right mean state? And then you also loosen the constraint on your subgrid scale parameterization. You can just tune it.
Maybe I'll come this at it from a slightly different angle. How much effort or how feasible is it to quantify the domain of validity of a network? So I'm thinking when somebody presents a theory or a model, there's assumptions that led them to derive that model or that theory. Even the conservation laws that we're talking about, those break down under some assumption. I mean, if some assumptions do not hold, these conservation laws break down. So we can understand that because we know what those assumptions or conditions are. And my question is there effort, or is that something people are trying to understand the conditions under which the network breaks down?
Any responses?
I mean, generally, absolutely. That's a huge whole branch of CS, is people doing the actual theory side of neural networks and how they train and where they're going to fail and where you're going to always get to, you know, some minimum you didn't want to get to. So like there's a whole branch of literature out there that we often think we're so smart, and then we go find out that they figured this out 12 years ago, and did it with math. So I do think whether or not that's going to be, and at what speed that kind of theory and background and deep understanding of these optimization problems is integrated into the earth sciences, I think for me, at least from my perspective, is the really hard part. Is oftentimes the people working in one space are not reading and incorporating the information from an entirely different field. And I think so that part's really challenging, and I think is going to be slow, to be honest. And I know that's not answering your question directly, but I will just say the more and more I read from the CS side, the more I realize they understand a lot of what's going on in these networks before they ever hit go, if that makes sense. Yeah. Yeah. Yeah, I mean, I guess, I mean, on the one hand, no, we're still figuring out how these work and how we use them in physical science. But on the other hand, I can tell you already when my loss function is going to break down and be a poor choice for the physical problem that I've tasked it to. So with that in mind, I think to a certain extent, yeah, we already have some intuition about when this will be a good model and when this will be a bad model. And I'm going to stop talking now. So anyway.
I was going to say that I think maybe we are asking, or I'm not sure whether we're asking the right question, looking for absolute truth. We know that the models have certain biases. So to me, as an ocean person, if somebody asks me, what do you want machine learning to do for you? Not me doing something for machine learning. I would say if machine learning can help me, for example, fix the Gulf Stream separation problem, that would be a breakthrough for me. I don't care about, the truth is we have a problem. We know that the separation is incorrect, but I don't care about the absolute truth. If the machine learning can help me fix that, then that's great. And there are so many other biases like that. I mean, I think the day that machine learning helps me achieve that, then I would call it a success of machine learning. At least that's my personal opinion.
Yeah, I think Libby made an important point, and that's sometimes the solutions come from a completely different field. So to avoid us simply reproducing simple machine learning efforts, I think we have to connect to that community because we need tailored solutions. Otherwise, we are using it in a wrong way or for the false way.
We have 30 seconds, and I don't know if Bob can get it in 30 seconds. 28.
I think Gökhan hit it on the head when he said we need to know when we're asking the right question. It's all about the right question for the model and knowing when you should say, we don't know. So Gökhan's example with the fixing the Gulf Stream, if you've used machine learning to fix the location of the Gulf Stream and you don't understand why, and somebody asks you, will the location change? The answer is, we don't know. On the other hand, if you say, if you increase the carbon dioxide content of the atmosphere, will the ocean get warmer? Yes, we know a lot about that because it comes from lots of multiple independent sources that all support the same thing. We have a strong understanding of the physics and so on. So the real question in my mind is knowing when you're asking the right question, which is just a summary of what Gökhan said.
Okay, Bob, you went over your 30 seconds. So we actually have to cut it off now because we need to get into the lightning talks for the posters. Sorry, Gökhan. Yeah, good. So, okay, so thank you, everyone. Let's just give everyone who just spoke a round of applause. And just bear in mind that this little discussion was midway through the ML sessions. We'll have more talks tomorrow and a different discussion tomorrow, presumably. So now I'd like to introduce Alyssa Johnson, who has been single-handedly the most valuable person for this workshop. And she's going to tell us what to do for the lightning.
Yes, these are the lightning talks, and they are just that. They are lightning fast. You get 2 minutes. After that, I'll be waving my hands, making a big deal. Not everybody elected to do a lightning talk. I will announce your name, but if you are doing one, just be ready to hop up and come down. Our first speaker is Limeray. And I'm going to have you use the microphone instead of.
Okay, so the aim of the poster is to describe a project which started 6 months ago, so there are no results for the moment. It's funded for 4 years by the French National Agency. So the objective is to develop a modeling system that could allow to study the transition from hydrostatic to non-hydrostatic dynamics, more or less to go through all the sub-mesoscale currents all the way to almost Kelvin and Mohs instabilities. And maybe the main originality is to be able to represent both downscaling and upscaling across the sub-mesoscale current. And the underlying question is to look at the possible feedback, or maybe we don't care, I don't know, of non-hydrostatic processes on water mass mixing and ocean circulation. So for example, if you operate a model at 1 kilometer horizontal resolution with primitive equation, should you care about those very small scale processes? And we will apply, the objective is to go to realistic simulation and apply it to regions where we have a lot of data from Ifremer and the French Navy, where we know that there are very strong non-hydrostatic effects. Just very quickly, so the idea is to look at block structure mesh refinement and with local adaptation of model equations, numerics and physical closure in some selected areas of interest. So the building block is the Croc-Ocean model. It has already a primitive equation solver, Navier-Stokes equation solver, and a two-way nesting capability. So this two-way nesting capability for the moment works only for the primitive equation solver. So we will need to develop a few additional ingredients. So to be able to couple like a hydrostatic model with a non-hydrostatic model, how you define the interface operator and the two-way update in this case. You need to adapt the physical closures because the meaning of the closure is completely different from a 1 kilometer resolution grid to a order 10 meters, few meters resolution. And so you will need some kind of scale adaptive closure. And we will develop also academic benchmark to test some idealized situations before going to fully realistic. And there are questions about the good numerical method for non-hydrostatic zooms. So I don't go to the details. So the idea is to be able to develop this kind of simulations for very fine scale. And I think really the Gibraltar Strait is a very interesting example. Sorry.
All right, up next we have Prada. And if you need to change slides.
Hello, everyone. My name is Maheshwar Pradhan from Indian Institute of Tropical Meteorology. So this study is towards addressing some of the coupled model problems by revising the ocean diurnal cycle in a coupled model and the related flux feedbacks. Sorry. To describe one of the long existing problem was to simulate a realistic phase and amplitude of diurnal convection. And there are studies which try to improve that by means of atmospheric convective parameterization or cloud triggering functions. But there were problems mostly related to diurnal amplitude of precipitation. On the other hand, there are studies which indicated that the diurnal AC interaction can help in improvising the diurnal convection, as I mentioned here. So what approach I have followed is there are basically two processes. One is the diurnal warming and diurnal cooling of the surface ocean, which contributes to the diurnal skin temperature variability and the related flux scheme that in the default configuration, there was no diurnal skin temperature parameterization, and the flux scheme that was followed is Encalf algorithm. And in sensitivity run, so we have a diurnal skin temperature variability along with coherent flux scheme. So basically, I'm modifying the two-way air-sea interaction where the ocean feeds back to the atmosphere by means of skin temperature variability, and the atmosphere feeds to the ocean model in terms of the surface fluxes. And in my poster, I will show the improvements in across scale, that is ranging from diurnal to intraseasonal and seasonal scale. Thank you.
Great. Up next, we have Zhu.
Hello, everyone. I'm Jiang Zhu from the Paleoclimate Modeling Group at NSF NCAR. I came to this workshop to learn some oceanography. So far, it has been great, and thank you for that. The question I want to address in my research is, do eddy resolving simulations produce different temperatures in past and future climates? And we use a high resolution CSM 1.3. At this 10th degree ocean, we start to resolve the mesoscale ocean eddies. And we use this model to simulate a climate from the past, including the early Eocene greenhouse climate and LGM, the Ice Age climate. And we also have simulation of 4 times CO2 far into the future potentially. And one advantage of this paleoclimate simulation is that you can see we are using big differences, like big forces to produce very different climates from the present day. Looking at the early Eocene greenhouse climate, the global mean temperature could be 14 degrees C warmer than the present day. LGM, the temperature might be 6 degrees C colder than right now. And the answer to the question, yes. And on the left, we have the global mean surface temperature of different simulations. Our trick here is to first run low resolution simulation to near equilibrium, and then start our high resolution simulation. Focusing on those very warm climate simulations, you can see that the high resolution showing in solid lines, they are significantly warmer than the low resolution simulation, including this 4 times CO2 simulation. And the lower left, you have the spatial distribution of the SST. Top one is the early Eocene, so that's the one of the very warm simulation. You see that we have enhanced SST warming over mid to high latitude. A lower plot is from the abrupt 4 times CO2 simulation. You see enhanced warming over the northern hemisphere. And if you know why, if you are interested, please come to my poster and we can have a discussion over there. Thank you.
Great. Up next, we have Spence.
No, just one slide here, all the beautiful faces. Hi, my name is Paul. Thanks to the organizer for having us. I'm here on behalf of the Consortium of Ocean and Sea Ice Modeling in Australia. There's a few of us around me, Adele, Andy, Ashley, I forget. Our poster is really just about the success of growing our sort of grassroots community for the last 10 or 12 years or so. We're mostly a user group, but we've, have over 200 people contributing to our community, over 600 terabytes of model data that we provide to everyone. I think 10 or 12 different model configurations. Yeah, it's been very, very successful. And I think the key to it for us has been trying to make it really a lot easier for ECRs to do science. So just lowering the barriers to entry, again, by making lots of simulations available, over 100 simulations, making it very easy for ECRs to run a model. So I can get a new PhD student running a 10th degree global model in 30 minutes on our supercomputer. Also providing awesome analysis software or scripts essentially. So we're often having hackathons now, 2-day hackathons with 40 plus ECRs getting together to write code. And so, yeah, it's all about, I guess, our success of creating this community. But Most importantly, we're using the models that are created here in the US. So sincere thanks to our partnerships at GFDL and NCAR as well. We couldn't do it without you, and your efforts are really making a difference. Thank you.
Thank you. All right, up next we have Van Rokel.
All right, my name is Luke Van Rokel from Los Alamos National Lab. I'm going to present actually two topics in one. I'm going to try and cover our efforts in new ocean model development at the Department of Energy, and also wave modeling efforts that we've been working on as well, including a little bit of physics in there on what are the roles of waves in the coupled system. It was a really interesting study. As for the ocean model portion, Omega is the name of the new ocean model. You may ask, why in the world are we rewriting an ocean model and not just using OpenACC? DOE has decided that we need to have all of the architectures and not just one. So we can't just support NVIDIA GPUs through OpenACC, so we have to have Intel and AMD as well. So that requires a lot of different work. But we're making some good progress already. I can walk you through these, but what might point to is that the runs are about significantly faster. So we're going from order 1 there to 10 to the -3 in terms of performance. These are some different tendencies we have. We don't have the full shallow water model yet, but that's coming soon, in the next couple of weeks, in fact. On the wave side in the bottom left, this is some of the work that we've done, mostly led by a postdoc at Los Alamos on the role of waves in the coupled system. Be happy to discuss that. In the upper right are our efforts to emulate some of the more expensive portions of WaveWatch 3 that we're starting to have some success in and leaning toward using a more robust physics form of one of the source terms in WaveWatch that will be roughly the same cost as the one that's used now. In the bottom right, we've also worked as well on porting WaveWatch to GPU as well, getting about 30% speed up on NVIDIA GPUs. So if you're interested in any of that, be happy to talk about it.
Thank you. Up next, we have Bruce.
Thank you. Hi, I'm Stephen Bruce. I'm at Argonne National Lab. My poster is also covering two different topics. The first of which is ongoing work on a project that I have to develop a multi-scale coupling to help represent coastal water levels at high resolution more efficiently inside Earth system models. So coastal water levels require really high resolution, but they're driven by a lot of global processes that drive the thermohaline circulation. And so we're looking for a way to incorporate both those effects. In this coupling paradigm, it's trying to overcome the coarse grid resolution of standard OGCMs, the lack of the thermohaline physics in coastal models or coastal barotropic models, and the prohibitive expense of high resolution models that go down to coastal scales. And so the idea here is to extend temporal mode splitting so that we're solving the barotropic equations on a high resolution mesh and coupling them in a way that keeps those two modes consistent. The baroclinic drive and connects them to the baroclinic drivers, which are modeled at a coarser scale. Oops, other way. And then the next topic is efforts to be able to better represent coastal flooding in models with coarser grid scales. So we have this subgrid scheme that we've been using where we use high resolution DEM data and compute correction lookup tables that help us correct mass within our schemes. And we've ran this in a Hurricane Sandy test case where we only have a 1 kilometer mesh up the Delaware River. And you can see that incorporating these subgrid corrections is a big deal in terms of being able to represent the subgrid scale flow connectivities that we otherwise wouldn't resolve.
Thank you. Up next, we have Dukovsky.
Hello, I'm Dmitry Dukhovskoy from NovaPSL, and I will present in work that is part of the climate ecosystem and fisheries initiative, and some of people presenting here also part of this work. This is a cross-NOAA effort. The goal is to build nationwide operational ocean modeling and decision support system to predict ocean and marine ecosystem conditions from days to decades, and give a longer projections to several to a century. So the backbone of the system is a regional modeling system. So there are several regional models, and I will be talking about Northeast Pacific. So the domain is shown over there. Oops, yeah. Yeah, I will be showing several simulations. So the model is still under development, so it's early stage. So we are still testing the model, trying to understand how well the model can predict the seasonal forecast. At PSL, we run a seasonal forecast. So I will present several seasonal forecasts as well as several sensitivity tests. And the model is doing quite well in the low latitudes, mid latitudes, as I'm showing here. So it matches very well the world ocean atlas, for example, quite well. So this is the California current. But there are some problems in the higher latitudes, specifically in the Bering Sea. The model is too cold, so I'm going to talk about the problems in the higher latitudes and discuss possible causes of this cold anomaly in the Bering Sea. Thank you.
Thank you. I think this is one of the first lightning poster sessions I've done where people are actually under 2 minutes. Oh no. All right, Real.
So good afternoon, everybody. My name is Marco. I'm a researcher at the National Institute of Oceanography and Applied Geophysics in Trieste. In my poster, essentially, I show essentially the preliminary results of some run that we did in this domain that is in the northern part of Italy. Essentially, it's a mid-latitude area. It's characterized by very complex topography, multiple environmental gradients. For example, we have significant high chain mountains surrounding the relative flat areas. We have a significant river network. And also, for example, there is in this domain the Northern Adriatic Sea, which is characterized by significant earth interaction and deep water formation processes. Essentially, we evaluate the dynamics of the area from a climatic point of view, producing a new configuration on that regional Earth system model. REXCM-ES, so we can see different models, very different dynamics of different sphere of the climate system. So VMIT for the ocean, BFM for the marine ecosystem, REXCM5 for the atmosphere. We have the model also for the river dynamics, and we have a driver based on Earth system modeling framework, which manages the run of each component. So you can see here that this one is essentially the domain of the atmospheric model. Resolution is 3 kilometers, so convection permitting. This is the domain of the river network, the river model, and this is the domain for the ocean model. In this case, the configuration of the ocean model is non-hydrostatic. We did some preliminary run using this very high resolution configuration. We can see that, for example, the coupler version of the model slightly improved the representation of the precipitation of the northern part of Italy, northeastern part of Italy. The model tends to be also a little bit warmer with respect to the observation. The river dynamics is very well simulated by our river model, and also the ocean compartment. Here is just an analysis about the sea surface temperature. The model more or less is able to simulate the spatial pattern for the sea surface temperature, although it's a little bit warmer with respect to the reference data set. So if you have additional questions, if you want to interact with me, you can come and see my poster. Thank you.
Thank you. Up next, we have A. Morrison. There's 2 Morrisons at this.
Great, yeah, so I'm Adele Morrison. So a lot of global ocean models struggle to form dense water around Antarctica and then to advect that into the abyss. And so we've been quite lucky with this Access OM201 model over the last few years that you can see here. Okay. It's hard to line up. So the bottom water, the age there you can see, this is ventilating into the bottom of the ocean, and you can see it's following the known pathways of bottom water there. But we're really quite lucky with this model configuration. We never really tuned it to get this. And so what we've been doing now is probing a little bit to understand why we have such good Antarctic dense water formation on the continental shelf. It's one of the things we've been playing around with is the vertical resolution just in the very upper part of the ocean. So you can see in the top right there. The blue one is our standard configuration where we have a 1 meter top cell and there's 75 levels. And so what we've done is coarsened that resolution in the top 5 meters and also increased the resolution to 0.5 meter top cell. And so you can see in the bottom right there, this is the transport of those very dense waters across the 1,000 meter isobath around Antarctica. So those dense waters that flow down into the abyss. And so you can see there's like a 70% reduction or so in that dense water flow going from the 0.5 meter top cell to the 5 meter top cell. And I'm going to leave it a mystery as to what's causing that. Come chat to me at my poster and we can talk about it. Yep, thanks.
Thank you. Up next, we have Belle. Oh, it's not.
Yeah, exactly. Hello, my name is Diego. I'm not Mike Bell, and he couldn't be here, so I'm presenting for him. So, okay, we want NEMO to be able to use more generic vertical coordinate systems that do not represent the bathymetry as a series of steps. But in order to do so, we need NEMO to be equipped with schemes that can compute horizontal pressure forces accurately. So we focus on this work on 2 methods, the density Jacobian scheme of Shekeptin and McWilliams, 2003, and the forces on the phases firstly proposed by Lin in 1997. And the latter is quite interesting and attractive because it naturally extends to finite volume frameworks. So for both schemes, we use cubic interpolating polynomials, and we also allow for constrained interpolation in the case to address the challenges of very rough bathymetry. Yes, the quarter order accurate schemes for the case of the forces on the phases algorithm is one of the novelty of this study. So we test these 2 schemes in the standard C-mount test case, and we find that the 2 methods gives quite similar results that are better than second order methods. And then finally, we also assess the impact of initializing our simulations with grid cell mean values instead of point values, and we find small differences. If you're interested in the details, please come to chat with me.
Thank you. Up next, we have Biestok.
Thank you. My name is Arne Biastok from Geomar, Germany. And I would like to introduce you to a new project, a long-term project about 6 years called Worlds, in which we would like to explore the role of fine-scale worlds. And we mean, with fine-scale, we mean the resolved mesoscale down to the sub-mesoscale for the ocean dynamics in the upper 1,000 meter, for the air-sea exchange, the uptake of heat and carbon, and of course, hopefully to improve models. And we do that in not only my favorite region, but the Agulhas region, but also the region that Lizzy identified as being so important. And what is special about that project is it's a combination of 3 observationalists and me as a modeler, which means we can provide ground truths to the model data. And that's basically what we plan. There will be an extensive ship-based campaign with 2 ships and lots of autonomous instruments in the region in about 2 years to come. And then a big model strategy down to the kilometer scale, hundreds of a degree resolution based on NEMO and AGRIF, both in ocean only, coupled, and also with biogeochemistry. And the main reason why I bring it up here in this group here is all these data will be distributed in a fair and open data principles. And there's lots of room for collaboration, be it with the observations, but also in the modeling realm. Thank you.
Thank you. Up next, we have Zhang.
Hello everyone, I'm Wenda Zhang. I'm a postdoc at Princeton University. In this poster, I'm going to talk about our work on using energy backscatter parameterization to energize ocean mesoscale eddies in eddy permitting models. The eddy permitting models have been widely used in climate simulations. They tend to simulate weaker eddy energy compared with the eddy resolving models because the eddy energy tend to be over dissipated by the model's viscous momentum closure. And one way to resolve this is to introduce a backscatter parameterization, which can re-inject the energy from the dissipated energy from the subgrids back onto the resolved eddies. And in this work, we try to address a remaining question for such a parameterization, that is, in what kind of vertical profile should the subgrid energy be returned to the resolved eddies? To do this, we testified several different vertical mode structure, as you can see in the bottom figure, to prescribe to our backscatter. And additionally, we also try to constrain the vertical structure by solving that subgrid kinetic energy in 3D. And we did all these different approaches in an idealized simulation of MOM6, as you can see from the right figure. The left one is eddy resolving simulation, which we regard as our benchmark. The middle one is a quarter degree simulation. As you can see, it has much weaker energy compared with the high resolution case. While on the right one is the one with our backscatter parameterization. It significantly improves the kinetic energy to a similar level with the high resolution simulations. What we care is what difference can the vertical structure of the backscatter make to the large scale circulations? So, oops. The main conclusion is the vertical structure matters, especially in the highly energetic region like the Southern Ocean. As I shown in this upper figure, it compares the isopignal structures in the parameterized low resolution simulation and those in the high resolution simulation. The black lines are in the low resolution simulation, green lines are the high resolution simulation. If we backscatter energy into a barotropic mode, which is the first figure here, the isopignals tend to be overly slumped in the upper ocean, and we ended up having a reduced baroclinicity compared with the high resolution simulations. While the other two, we project energy, we backscatter energy to a more surface intensified mode, like a SQG-like mode, or we solve the subgrid energy in 3D. In these cases, we can preserve the baroclinicity of the large scale circulation, have a better isopignal structure matching the high resolution simulation. And then we find the reasons because the backscatter can change the vertical structure of the resolved eddies, and through eddy momentum flux that can feed back to the large scale circulation. And with a barotropic backscatter, it tends to cause some spurious barotropic structure in the large scale circulations, while with the SQG-like surface intensified structure, we can represent the surface intensified eddy momentum flux better, which can help preserve the baroclinicity of the large scale circulations. Thank you.
Thank you. And our last lightning talk is McLean.
Right. Okay, so the goal of this project was to explore the causes and impact of enhanced land ice melt around Antarctica and Greenland and sea ice in the Arctic Ocean. And because mesoscale processes and eddies were implicated, especially in cross-shelf transport in Antarctica and Greenland, we had to configure a new grid, global grid, that was higher than the standard 10th degree. So it was 8 kilometers at the equator, reducing to roughly 2 at the poles. And we're calling that the UH8-2, using POP2 and sea ice. And then the land ice melt was informed by observations. This is Bamba. We did 2 simulations, one with core and one with JIRA. The JIRA one is shorter. And in the Arctic study, that's the next slide, we do a comparison with the regional 1/25th degree HICOM sea ice simulation. So the first study, the lead author is here, and she'll also be at the poster. We were looking at a suite of UH8-2 simulations which we used to investigate the way we distributed that meltwater, either at the surface, which is the standard way it's been typically done, or whether we distributed it over the top 200 meters of the water column to better account for the fjord mixing. And the results were that we changed the surface circulation, we made it faster. We also increased the amount of freshwater transport off the shelf, and the mechanisms responsible for the freshwater transport were different. But Teresa can tell you more. Okay, and then in a second study that's collaborative with a number of people in this room, as I mentioned, we had both the UH8-2 and we had the 1/25th HICOM sea ice, a regional model. And what we were focusing on here on the left-hand side, we were looking at a pulse of Atlantic water, subsurface Atlantic water, that moved into the Eastern Eurasian Basin in 2017, and then peaked in about 2018. The middle panel shows the HICOM sea ice and UH8-2. And then by 2020, it started to diffuse across the Eastern Eurasian Basin. But during its peak, what we saw was a relationship with the ocean sea ice, the basal melt. And for the reasons for that, you'll have to come and talk to me at the poster.
Perfect timing. Thanks again to all of our lightning talks for the posters, and we're about to move into that. Do you want to give a wrap up for the day? I'll give a brief review of what's going on outside. We do have heavy hors d'oeuvres as well as a bar with wine and beer and sodas. That's all open to you as participants. And that is already set out. Feel free to browse that while you do the posters. It's meant to be kind of like a whole reception. Anything else for tomorrow?
I think, so remember, you're here to see the posters as well as to eat and drink. But let's just give everyone a round of applause who's going to be giving the posters and for the whole day's worth of speakers. So enjoy, and the bus leaves on the dot at 7:30. So do all your postering before then.